Looks good.
All right, awesome. Yeah, awesome. We're on live. Um,
Tell me when to start.
uh, oh, it's still loading. Okay, now it works. Cool. Um, so before we start the physics panel, I just wanted to welcome everyone to day two. Can everyone hear me? Yeah. Thank you to everyone who joined yesterday. We had an awesome time learning about microbes and nanotechnology, neurobiology, probabilistic combinatorics, and many other amazing STEM concepts. And today we're going to be diving into physics, computer science, and engineering. And so at the end of the day, we're also going to have multiple undergraduate students talk about their extracurriculars in STEM and opportunities that encourage them to pursue STEM and help them rise to the challenge of attending some of the top US universities. So we're now going to kick off with the physics panel, where we're going to get to peer into the proton, discover black holes colliding at the edge of the universe, quantum computers, and dive into the mysteries of the physical universe. So joining us bright and early is Dr. Richard Conn-Henry, an Academy Professor of Physics and Astronomy at Johns Hopkins University. Dr. Henry has made observations using the Copernicus and IUE satellites, as well as the Hubble Space Telescope and the Mariner 9 spacecraft, and was a co-investigator on Apollo 17 and the Apollo-Soyuz mission. He's the principal investigator in the study of the lunar material, and he's also the PI for the Hopkins Ultraviolet Background Explorer, which was selected in 1996 April as a NASA MIDEX program alternate project. So without further ado, please welcome Dr. Henry.
Howdy. You've heard it claimed that a picture is worth 1,000 words. But to our astonishment, we humans have discovered that an equation is worth 1,000 pictures. Hey, at least 1,000. How can that be? An equation? Surely you jest. Hi, I'm Dick Henry, and I'm director of NASA's Maryland Space Grant Consortium, and I'm also an Academy Professor at the Johns Hopkins University in Baltimore, Maryland. My PhD is in astronomy, but I've also taught physics for decades, endlessly trying to understand that mysterious subject. When I finally did understand, well, at least I think I understand, I wrote it up as an essay and I submitted it to the famous international journal Nature. And by gum, it was published. The Mental Universe. Just Google it. You see, while I'd always found mathematics easy and interesting, physics was, to me, incomprehensible. It didn't seem to fit the world I actually lived in. Equations, boo. But then I was incredibly lucky. I was hired as an assistant professor in a physics department. Hey, they hired me because they needed an astronomer, but that gave me the chance to teach physics, and with wonderful results. It did take a long time, decades, but I got there. So what is the result? I can share it with you all very easily indeed, because it turns out to be simple after you've gotten there. The universe is intrinsically mathematical in its very bones. If you understand math, which is easy, you can understand the universe. So exactly where do we start? You start with the Pythagorean theorem, which is the most important single result in all of mathematics, and as it turned out, the most important single result in all of physics as well. You all know the theorem. Heck, everybody knows the theorem. The square on the hypotenuse is equal to the sum of the squares on the other two sides. Even the straw man knew a, well, somewhat garbled version of that. So why is the Pythagorean theorem so important? It is because that theorem miraculously turned out to be the gateway to our understanding the nature of time. Time, which is by far the most mysterious feature of our universe and of our own existence. Well, who was it that discovered that about the ancient Pythagorean theorem? No, it wasn't Albert Einstein. It was one of Albert Einstein's former teachers in Switzerland, Hermann Minkowski. Yes, it is true, precocious young Einstein had in 1905 discovered his special relativity. Wow, indeed. But just 3 years later, it was Hermann Minkowski, a former teacher of Einstein, who discovered just what special relativity really meant. Relativity, Minkowski discovered, is nothing but a mathematically trivial extension of the famous Pythagorean theorem to include time as a fourth dimension. I consider that to be the biggest human discovery ever. You can write the 3D Pythagorean theorem as an algebraic equation, the sum of 3 squared terms. Why 3? 3 because space has 3 dimensions. You would add one more term, wouldn't you, if it had turned out that space had 4 dimensions? Of course you would. And parking would have been much easier. But space doesn't have 4th dimensions. It has only 3. Well, here's the enormous yet trivial secret. Instead of adding one more term, you use, for time, that 4th term, a minus sign instead of a plus sign. That's it, the greatest discovery in the history of physics. Well, that's the end of the story. The most important discovery about the nature of the universe ever made, mathematically trivial, yet incredibly consequential for physics, for engineering, for philosophy, perhaps even for religion. The nature of time. Simply a minus sign in the Pythagorean theorem. So, what great difference did Einstein and Minkowski's discovery make? For one thing, it is what allowed us to actually understand, at long last, what underlies the incredibly important earlier physics discoveries that had been made by Sir Isaac Newton. Just think what Newton had accomplished. He and his followers had discovered wonderful things. Yes, but all of them were things that they could not actually understand at all. Conservation of energy, conservation of momentum, conservation of angular momentum, and Newton's famous law of gravitation. Yes, but where did these wonders come from? Why were they true? Experimental tests, plus extremely detailed observations, showed all these to be true, but no one knew why they were true. Indeed, Newton was deeply embarrassed by his inability to explain the wonders that he had uncovered. Well, Hermann Minkowski's brilliant reinterpretation of Einstein's new special relativity as being nothing but an extension of the Pythagorean theorem to include time as an additional dimension, but with a minus sign, not a plus sign, allowed immediate rewriting of all of physics to include time finally in its actual and proper role. Nothing hard about it, just a great long bunch of mathematics. You don't even need to go through it all. You can just use the wonderful results. Hold it. Just a bunch of mathematics, algebra? Let's pause and think a bit about that. How can the universe possibly understand our mathematics, our algebra, much less use it, when algebra didn't even exist until we humans thought it up? And wait a minute, how the heck could naked apes like us think up algebra. Well, let's take a serious pause now and go back and review all of ancient human history. The naked apes, our ancestors, had been around for a long, long time. But until about 50,000 years ago, we Homo sapiens could not talk. But at that point, the FOXP2 gene appeared just in a small group of about 50,000 of us in East Africa. We were not the only people on Earth. There were a couple of million people, but every single person on Earth today is descended just from those particular 50,000 people and not from all those others, simply because our ancestors were the people that acquired speech. A click language. There are still today in Africa peoples who speak click languages, including a language that may be the original click language. Oh, just imagine that you were that child, the first child to say, pick up a stone, and think to say, while pointing to the stone. Another child mimics you. It's a fun game. Another child picks up a stick and says, the game continues day after day. And the first human language has appeared. Among the kids is, my bet, a turning point in human destiny. Not all the kids were able to keep up, but those that did became fluent, had hugely successful hunting parties because they could plan and coordinate and communicate. Within some generations, that whole tribe of humans had become talkers. Hey, we've never stopped talking since. I'm doing it right now. Fast forward to ancient Greece. All Greeks talked, obviously, but a few had also developed something totally new: geometry, diagrams, brilliant geometry over some hundreds of years. But none of them thought up what we now call algebra to represent that geometry with abstract and arbitrary symbols. Even so, one brilliant Greek, Pythagoras, in addition to creating his famous theorem, recognized that, quote, number is all things, which is what we finally are realizing today. For Pythagoras seemed to know that hiding within the wonderful geometry lurk numbers, algebra. Once finally discovered, and it did take a long, long time, meant that you could write the Pythagorean theorem without drawing any triangles. Algebra was essential in allowing that extension to the Pythagorean theorem that we today call Einstein's theory of relativity, because only very clumsy diagrams could sort of include time, and really only in a fake manner. But algebra includes time easily without missing a beat. Just that simple minus sign. For there are no minus signs in diagrams. There can be in equations. It's as simple as that. Victory. But wait, there's more. Recall that Newton and his followers did find conservation laws. Energy, momentum, angular momentum. Yes, but no one had any idea why these laws held true. Do any of you know who it was that made the crucial discovery as to why these laws are true? You don't know? then one guess as to the gender of the person who made this second most fundamental discovery ever in the history of physics. The person who found out why was an American mathematician named Emmy Noether. After Pythagoras himself, she is the greatest contributor to our understanding of the nature of the universe. For Emmy discovered why there are conservation laws, and it is utterly simple. Each conservation law exists only because there is a particular symmetry present for unknown reasons in our universe. And all it takes is simple algebra to show that what Emmy discovered is true, that is why conservation laws exist and must exist. Here is her result in words. 1, if you do an experiment of any kind and you repeat it later, you get the same result, and that is why energy is concerned. 2, if you do an experiment of any kind and you also do it across the room, you get the same result there, and that is why linear momentum is conserved. 3, if you repeat an experiment about rotating it some, you get the same result rotated, and that is why angular momentum is conserved. Well, wow, we now know why. Even today, we don't know why the universe has those symmetries, except that if it did not, we ourselves could not exist. Now, to make it even better, suppose you try one more thing. Instead of waiting or shifting or rotating your experiment, you create a mirror image version of your experiment. Well, I guess you expect that you'll get the same result, but mirror imaged. Hey, let's give that hypothesis a name. We'll label it. Oh, we do love obscure terminology, conservation of parity. If it turns out by experiment to be true, like the other ones did turn out by experiment to be true. And yes, indeed, for experiments that involve the gravitational force or the nuclear force or the electromagnetic force, yep, same old, conservation, this time of parity, as it is called in the jargon. It is just a word, but it is a real symmetry by experiment. But if your experiment involves the fourth of the four forces, the so-called weak interaction, for example, as seen in neutron decay, you get a different result. Non-conservation of parity, Nobel Prizes. Wow, our universe has a very peculiar structure embedded in its mathematical bones. There are no right-handed neutrinos. This is a fact. Now, let's go back to Einstein and Minkowski's great discovery of the geometrical nature of time, that minus sign. Well, Albert Einstein, bless the poor fellow, for about 1 year, he resisted his teacher, Hermann Minkowski's reinterpretation of Einstein's already famous relativity as being merely a trivial extension of the Pythagorean theorem. But fortunately, good old Albert did see the light. And indeed, he saw it so clearly that it was what led in 1917 directly to Einstein's greatest accomplishment, his experimentally verified theory of gravitation, called, for some reason, general relativity. Now, remember how embarrassed Newton was about his hugely successful theory of gravitation? He couldn't explain why it worked. Well, a light bulb had gone off in Albert Einstein's head. Maybe space-time is not flat, but is curved. You've heard that before. Then, if a great mass, such as our sun, was somehow, we still don't know why, the cause of that curvature. The planets would naturally follow curved paths, orbits. Okay, sounds like an idea at least worth trying. Just a bunch of math to work it all out. And hey, the heavy lifting had already been done by the pure mathematicians, Gauss and Riemann. Well, by gum, just a few years of effort by Albert during World War I, and bingo, Einstein's crowning achievement, his famous theory of general relativity. The equations are extremely simple. Here it is in words. Curvature equals mass energy. Wait a minute. Take a look at that. Careful. Mass energy is conserved, but curvature, it turns out, is not. That is, its derivative with time is not zero. Shucks. But Einstein persisted. He said, okay, let me tweak curvature to get something that is conserved. Well, would you have bet on that? I wouldn't. I'd have given up. But by gum, it worked. Wonderful. And that's where the story gets incredibly exciting. For World War I was on. Einstein auf Deutschland published his equations. Equations that he, Einstein, never could solve other than numerically, which Einstein had done to verify that they worked by showing that they explained perfectly the mysterious observed precession of the perihelion of the planet Mercury, the only deviation that had ever been discovered from Newton's problematic law of gravitation. Well, apart from what led to the discovery of Neptune by Leverrier. Well, then, wait for it, a miracle happened. On the German World War I Eastern Front, physicist soldier Karl Schwarzschild received his copy of the journal in which Einstein's general relativity was published, and Karl solved the equations. And they predicted black holes. The rest is history. And guess what? You'll never guess. Schwarzschild's solution that predicted black holes was a slight modification of the Pythagorean theorem. Oh my God, I'll stop there. I can't take it anymore. It's too exciting for me. Oh, wait. I've just realized that I have not yet mentioned quantum mechanics. And that might seem to you to be derelict of me. So let me deal with quantum mechanics, which most unfortunately is what almost everyone thinks is the most mysterious thing in all of physics. Oh yes, I myself certainly did feel that exact same way at one time. But fortunately, it dawned on me that surely quantum mechanics must be the result of the same symmetries that produced the conservation laws. And so it turned out. I spent a summer at Los Alamos National Laboratory, starting from scratch to see if I could produce quantum mechanics from nothing. And I succeeded. Quantum mechanics made transparent, published after thorough peer review in the American Journal of Physics. Hey, no joke, 4 referees, all 4 supportive. Well, that was long ago, 1990. That paper has only been referenced in more recent papers one single time. But that one reference was by, brace yourself, Isaac Newton, no less. Now you may think that that is impossible, but I assure you that it is true, for I should know. I was Isaac's co-author. And I am very happy indeed to be able to report that there is a later paper by a different author establishing exactly the same thing, namely that quantum mechanics is just a simple product of the mysterious presence of symmetries in the universe. That paper is by the late Moshe Shapiro, and I give a reference. Wow. At that point, I, of course, entirely lost all interest in quantum mechanics. I had turned quantum mechanics into a dull subject. And I must say, to me, it is bizarre that so many people, even physicists, still think that quantum mechanics is mysterious. Well, that's physics. Now for the big question, what does it all mean? My answer, sorry, I haven't any really defensible idea as to what it does all mean. However, I do assert that I do know for sure what it does not mean. Experiment has shown that there is no universe out there in the conventional sense. Bishop Berkeley was correct. There's nothing out there despite all our observations. Yes, of course, we make observations. You're making them now. But they are not observations of anything, as in anything. By experiment, we know that there are no things. What there are observations, and those observations are, of course, in our minds. They are purely mental, looked at closely, and we have looked at them closely, extremely closely. There is nothing there, as in no thing there. There are no things. There are only observations. I like to call them records. The universe is clearly and most definitely not material, since there is no material. So they must be mental, because my mind, and you will agree, your mind, do vividly perceive them. What are we to make of that? What I make of it is that you and I are incredibly, indeed almost inconceivably, fortunate to exist, to experience the magic of life. I am so grateful. Whatever the universe actually is, in actual practice, the astronomer's universe out there is utterly hostile to life of any kind. Our planet Earth is a lifeboat in an ocean of destructive high-energy radiation. Particles accelerated from our sun, also particles accelerated by the magnetic fields in the galaxy of stars where our sun enjoys its existence. So do take care of planet Earth and do learn physics, the key to understanding the beautiful world that you are enjoying this very day. Oh yes, my own research. I have published dozens of investigations of the cosmic diffuse ultraviolet background radiation from our universe. My interest in it today centers on the possibility that a component of it originates in the very slow decay of the dark matter particles with the emission of ultraviolet photons that are capable of ionizing hydrogen. The idea is that that is how the universe managed to achieve its present extremely high degree of ionization, following the universe's recombination just 380,000 years after the Big Bang. Next up on this, I hope to make observations using an instrument that is on board the New Horizons mission, which is now well beyond Pluto. We'll see. So, any questions from anyone?
I have okay. I have a rather abstract question, but what was it like working with like the Hubble Space Telescope and like all the Copernicus and IUE satellites? Like what's your favorite part about it? And yeah.
The Hubble Space Telescope, oh my goodness, my goodness. I was a graduate student at Princeton. Lyman Spitzer there was the inventor of the concept of space telescope. And when I was at Johns Hopkins University and I was invited to go down to NASA headquarters for 2 years to be deputy director of the astrophysics division, we managed to get Jimmy Carter to fund the Hubble Space Telescope. And then I went back to Johns Hopkins, and extraordinarily enough, instead of the Hubble Space Telescope going to Princeton, which everybody thought it would, it ended up on my own campus. I had nothing to do with it. I had tremendous colleagues. And I've observed with the Hubble long ago. It's wonderful having it still up there working.
That sounds awesome. Also, if you're watching from the live stream, I know there's like a little bit of a lag, but oh yes, okay. Someone actually asked something on the live stream. They asked, what do you do on a day-to-day basis?
Oh, on a day-to-day basis, I stay in this house. And on a day-to-day basis, I work away on plans for using the New Horizons mission. They've got an ultraviolet spectrometer on board, which if I can convince the system to allow me to use it for my observations, should be able to analyze that diffuse ultraviolet background. And most people, the overwhelming majority of astronomers, believe that the ultraviolet background is simply backscattered light from hot stars in our own galaxy. And I'm convinced, for whatever reason, that is not the case, that a good fraction of it is in fact a dark matter decay. And the nature of the dark matter is the most outstanding, huge problem in physics today. Nobody knows what it is. But I'm not the only person who thinks he or she knows what it is. There's dozens of us around the world, and we all have different ideas, and we all think the others are wrong and we're right. And that's what makes physics and astronomy so exciting. And in the end, hopefully we really will find out what the mysterious dark matter actually is. As I say, I think it's a light particle. I think it decays with a very long lifetime, and with the emission of 2 photons. It would have to be 2 photons because the dark matter is not electrically charged, we know that. And those photons are what cause the reionization of the universe. Almost all the hydrogen in the universe is ionized. Almost all of it, 99.9%. And nobody really knows what caused that ionization. It's simply extraordinary. That problem has to be solved. And the dark matter would be a twofer. So I just hope I get to do that.
How can you get into like physics and astronomy?
I'm sorry, the sound that's coming through here is very unclear to me. Clearer?
How could you get into physics or astronomy from an earlier age?
That's a good question. I suspect what happened, we used to go up to Georgian Bay, and one morning I woke up and my parents said, "Oh, Richard, there was the most wonderful display of northern lights. Wonderful." And I said, "Why didn't you wake me up?" And they said, "Oh, we thought you needed your sleep." I think that's what turned me into a scientist. I've really been an astronomer since I was a kid. I have a telescope. Oh boy.
Did you see the comet on the
No, I did not see the current comet. At my age, I just turned 80, and I am in perfectly good health, but I don't go out and look at the sky anymore. Did you see the comet?
Yes.
Yeah. Was it good?
Yeah, it was pretty cool. It was bright.
I love the fact that comets have 2 tails. I mean, that's absolutely marvelous. The ion tail that points directly away from the sun, and then the dust tail that is influenced by the solar wind. That's how the solar wind was discovered. It's really wonderful stuff. I was also on Apollo 17. Oh, I had so much fun on Apollo 17. Believe it or not, my senior colleague and I had a ultraviolet spectrometer on board the lunar orbiting mission part of it. And on the way back from the moon, we got invited into the famous control room for Chinese food on the last sleep cycle while the astronauts were sleeping on the way back from the moon. And I knew that they were sleeping and the thing was rotating, and I was the one who decided what angle it would be rotating at, because the spectrometer was observing my targets on the Apollo 17 mission. I've had an exciting life. I told you, I think in the blurb, that I'd hitchhiked across the Sahara Desert and went down the Nile on a barge. Wow. Have fun while you can. I'm having fun right now. And I thank you so much for inviting me to talk.
Thank you so much, Dr. Henry. We do have a few more questions for you, but we do have to move on because it's 8:35. Do you think you could, I could send them to you later, or just you could answer them? Okay.
I don't think I'll be able to
Dr.
be
Gleiser just said.
available later, unfortunately.
Okay, no,
I'll turn my
that's totally
sound
fine.
off now.
Sorry?
Shall I turn my sound off now? I guess I should. Mute.
Oh yeah, thank you so
Bye.
much.
Thank you
Well,
again.
first, thank you so much, Dr. Henry. Okay, your questions will be answered, Perry Ivan and Jay Kennedy, but by Dr. Gleiser. Okay, bye, Dr. Henry. Thank you so much. All right, so now transitioning. Let me just find. Sorry, just give me 1 second. Okay, nope, where'd it go? Oh, here we go. Try to spot. All right, everyone, please welcome Dr. Marcelo Gleiser. He is an Appleton Professor of Natural Philosophy and a Professor of Physics and Astronomy at Dartmouth College. In 1994, he received the Presidential Faculty Fellows Award from the White House, and he's also a 2019 Templeton Prize laureate. Without further ado, please welcome Dr. Marcelo Gleiser as he dives into the mysteries of the universe, what we know and what we don't know.
Hey, hi everyone. Wow, you guys don't even take a break between talks. You're very brave. I'm very impressed. That's pretty cool. And it was a very nice lecture by Professor Henry about his work and what he's done. I could address some of your questions. When we come to our questions, you can ask them again, and I'll be happy to do my best to answer them. So that would be great. But let's go on because we don't have a lot of time, and so let's make sure that we talk a lot about what I do and how it's that interesting to you as a potential future career, right? So let me put on my share screen here because I want to show you my transparencies that I prepared for you, because everybody loves a pretty picture. And can you see that? Just Diana, give me a thumbs up in case you guys are sharing. You can see my shared screen. Yes?
Yeah.
All right, cool. All right, so so what I'll do in these 20 or so minutes is essentially tell you a little bit about the history of the universe. There may be some overlap with Professor Henry's talk. I didn't watch the whole thing, but hey, it's always nice to learn more stuff, right? And it's very descriptive, and there's no math at this point anyways. And so let me introduce myself. So Marcelo Gleiser is my name. I am a theoretical physicist. I work mostly on what is called the interface between particle physics, so the study of the very, very small, and cosmology, which is the study of the very, very large. And you may say, how is that even possible? How could someone be studying both the very small and the very large at the same time? And the reason for that is that if your main area of interest is this area of physics that we call cosmology, which is the study of the universe as a whole, then you learn very early on that the universe has a history, right? It has a big bang, sort of like the origin of everything. And at that moment that we don't quite understand at all, but at that moment in time, matter, energy, everything was very concentrated, very high densities, very high pressures, very high temperatures. We don't really have the physical tools to describe that. But once the universe starts expanding and cooling off, and time starts to roll forward, so to speak, then we do have a lot of understanding of the physical processes that took place early on in the universe. And very, very early on, the universe was so hot that there were certainly no people, no stars, no molecules, not even atoms, not even protons and neutrons. Everything was broken down in the smallest possible constituents, which are the particles that make up all of matter. So essentially, the early history of the universe is a history that is told by the wedding of particle physics and general theory of relativity, which Professor Henry mentioned that. I think that's when I joined in. He was talking about Schwarzschild and his solution of the black hole, right? Essentially, the idea that there is a singularity in space if you have a concentration of mass that goes beyond a certain value, which is the Schwarzschild radius. But the point is that so essentially this theory of general relativity that describes the history of the universe as a whole that Einstein proposed in 1915 has been married to the physics of the very small. So we call it kind of romantically, we call it the inner space, outer space connection, right? And that's pretty much where I've done a lot of my research, which also bifurcates into another area, which is the origin of life on Earth and the possibility of life elsewhere, which is generally called astrobiology. So I will try very briefly to talk a little bit about all these things as we move on. So let me start by playing the slides for you guys. So we have here these two pictures, right, which I think are very cool because on the one where you see the stars and the sky, you know, it's a vision that we all have if you're lucky enough to live far away from the big city where you do have bright skies, and if you have a pair of binoculars, you'll be able to see not just the New Eyes comet, well, not anymore, but whenever it was showing up, but you'll also be able to see a bunch of stars that you cannot see with the naked eye, right? So the stars that appear to the naked eye are definitely not all the stars that exist. And a lot of science, and this is something which is really, really very important, is in a sense a way that we found through time, we meaning humanity, found through time to amplify our connection to nature. And we do that by amplifying what our senses can perceive of reality, right? Because if you think about it, you can only see a very small spectrum or very small window of the so-called electromagnetic spectrum, right, which is between the red and the violet. Everything else, you know, the microwaves, the infrared, the ultraviolet, and all the other frequencies of light are invisible to the eye, which doesn't mean they don't exist. It just means that you need the right tools in order to open up those windows to this invisible reality that is all around us. And that's exactly what science does. You know, it sort of amplifies our perception of the world and of the universe, right? And so on the side here, you have the stars, and everyone has gone out one day in life or more, if you become a scientist, and wondered what is going on. You know, why are there so many stars? What are stars? How do they come to be? What is the relationship between those stars and ourselves and our own star, the sun? And can we use science to make sense of all these questions? And then, of course, you start asking, why are we even here? You know, what is the meaning of our being in this planet at this moment in the history of the universe? So these are sort of like questions that sound philosophical, even metaphysical, but that are now very much part of what science deals with, you know, the big questions of existence from a scientific perspective. And the other image that I have here, I don't know if you can see that with your screens, but basically you have here a tiny little point of light, right? And this beam that is kind of highlighting it. Well, that tiny little point of light is planet Earth seen from Saturn. This picture was taken by Voyager 1, a NASA probe that was sent in the 70s to kind of fly by the outer planets. And Carl Sagan, the great Carl Sagan, had this great idea of let's turn the camera of Voyager 1 when it's going by Saturn to take a picture of the Earth seen from Saturn. And this is what you see. So this is where we are, right? If you're if you lived in Saturn and you could take a picture of it with a good telescope, that's why you would see this tiny little blue dots. Doesn't look blue here, but that's what it really is. And that is our planet in this vastness of space. And so you got to wonder, and people have wondered about our origins and about where it all came from the beginning of time, right? As soon as our ancestors were running around the African savannas, they were looking at the skies, they were thinking about the meaning of life and trying to make sense of everything. And really, if you think about it, the whole history of science, right, is asking questions that these people were asking before, which is, where did we come from? And indeed, if you look at a bunch of different religions, right, spread across history and across the whole planet, pretty much all of them have some sort of narrative of creation, right? I mean, where did the universe come from? Where did the world come from? Where did life come from? And these are the questions that motivate cosmologists and that motivate the people that study astrobiology, or the origin of life on Earth and elsewhere in the planet. So in a sense, we are heirs to the same questions that have been asked for thousands and thousands of years, but we now have this advantage of having the tools and the mathematics to actually probe them in a very, very deep way, right? And this is why, since I was kind of young, like even before like being in college for sure, and I was fascinated by the power of science and human reason to ask these questions and to provide answers, not always complete answers. We still have all sorts of mysteries out there. And Professor Henry mentioned one, which is very important, which is the mystery of dark matter, right? The fact that 26% of the stuff that fills up the universe is unknown to us. We know how much is there because this dark matter has mass, and because it has mass, it can bend space according to the general theory of relativity. So we know it's there, but we don't know what it is. And then only 5% of the stuff that fills up the universe is made of the normal things that we consider matter, like the electrons, the quarks that make up the protons and the neutrons, and the photons that make up very little of this whole stuff, and neutrinos. So all of that makes less than 5% of all there is. There's this 26% of what is it? But then if you do the math, say, wait a second, 26% plus 5%, it's 31%. What happened to the other 69%? Well, that is called dark energy, which is an even bigger mystery than dark matter. And that one is essentially what's making the universe not just expand, but accelerate in its expansion, right? So that is kind of like, what the heck is this? What could be possibly making the fabric of space itself stretch out like if it were a rubber sheet, and that is the mystery of dark energy. So if you make the calculations and say, wow, so despite everything that we have learned about the universe, we really still don't know 95% of the composition of what's out there. Now, if that's not enough mystery to motivate someone young to go into physics, to go into cosmology and astronomy, I don't know what it is. I mean, this century is definitely the century where at least the mystery of dark matter, I am very optimistic. I don't know if they are decaying, if the radiation is or not decaying dark matter particles, but I think that we have now the observational tools to really make progress on that question. So my guess is that in 10, 20 years, we should be understanding the nature of dark matter very well. Dark energy is a very big question still. There are all sorts of different ideas about what it could be, even ideas about maybe our theory of gravity that we use to describe the very large scales in the universe, the general theory of relativity, may need to have some fixing. But we've learned these things, and I always put these two pictures, like the big and the small. Oops, let me go back. This one here is the Horsehead Nebula, right? It's a place where there are all these stars being made, stars being formed by the power of gravity to contract big clouds of hydrogen and all the other atoms that are around there. And then when the temperatures at the core of these stars reach about 150 million degrees, they begin to ignite and start forming uh, radiation. They go from hydrogen to helium. It's called nuclear fusion process. And then the star is born, so to speak, right? And this has happened to us meaning us, our solar system, about 4.5, a little more billion years ago. A big hydrogen nebula was contracted because of instabilities that happen due to other stars exploding in our neighborhood. So the universe is a very dynamic place. Stuff is happening all the time. Stars are being born, stars are exploding because they're dying. And this amount of stuff that is thrown out into space is actually where all the matter that is made into your bodies, your carbon, the calcium in your bones, the iron in your blood, all this stuff came from dying stars that exploded billions of years ago. So if you think that you're young because I'm only 15, I'm 20, I'm 30, I'm 80, you're not young. This agglomeration of matter is young, but you're actually billions of years old. I mean, the stuff that you're made of is really old. It's just this new conformation of matter that you call yourself that is young. And so about 5 billion years ago, the solar system was born, the sun and all the planets. And each one of these worlds is completely different from the other. So I have a picture here of Enceladus, which is this spectacular moon of Saturn, which is truly mysterious. It has all this ocean that is frozen on top, but some cracks in it. You have these geysers that erupt with some ice being spit out into the atmosphere. And there's a lot of stuff going on. There is oceans underground, underneath all of this, and they are sort of models, perhaps, not necessary for life as we know it, but for biochemical processes that could help us understand our own history in this planet. So we have learned a lot of stuff, and this is a picture that I love, is a map from NASA of the whole history of the universe together, right? So we start here with the Big Bang, right? Time is going from left to right. We don't really know what is going on here, right? My research very much is about this physics that is the gray zone here, where we don't quite know exactly what was going on, the big expansion of the universe. And the point is that as the universe expands and it cools, eventually stuff starts to happen, matter starts to agglomerate, and you have atoms forming, first hydrogen atoms when the universe was about 380,000 years old. And then you start forming the first stars when it was about 200 million years old, and then the galaxies, and at billions of years, 1 billion years or so, you start really forming the older galaxies are beginning to cluster together. And you have a whole history of how galaxies go together and cluster with one another because of gravity. So it's kind of like there is a hierarchy of clustering. So the moon is attracted to the earth because of gravity, and then the earth and the planets are attracted to the sun because of gravity, and then the sun is in a galaxy because of gravity. So there's a beautiful picture of a galaxy here, a spiral just like ours. And then galaxies are attracted to one another because of gravity, and they form these giant structures which are millions of light years across, hundreds of millions of light years across. And you come up with these beautiful pictures. For example, this one is called the Hubble Deep Field, one of the Hubble Deep Field pictures. Each one of these blurs is clearly a galaxy, but what's really spectacular about this is that each one of these fainted little things is also a galaxy, just deeper away. And so you start to think, wow, each galaxy here, right? Hold on. Each galaxy here has hundreds of billions of stars, just like our Milky Way does. And each one of the stars we now know has planets, pretty much all of them do. So you start to calculate and say, wow, there are trillions and trillions and trillions of planets and moons. Just Jupiter has more than 65 moons. And all of these, in principle, could be harboring life. So you're talking about the big scale of things, but then you start to think about, well, is there a place for life elsewhere in the universe? And how would you know, right? So we start to think about it. And then we start to realize that as we look out into these spectacular worlds out there, there's even a sub a subdiscipline in astronomy nowadays called comparative planetology, which basically is I'm looking at all these different new planets that we're discovering around other stars and studying them in comparison to each other, their mass, the distance from their star, the temperature, the chemical composition, etc., and comparing that to the Earth. And the more we learn, we realize that the Earth is a very, very special place. Not just because it has water or carbon, all of that stuff, but because it has properties that allowed not just for life to emerge about 3.5 billion years, but for life to exist for a very, very long time, almost uninterrupted. There were some very big cosmic cataclysms. One of them, I'm sure you guys know, the one that killed the dinosaurs and about 50% of life on Earth, which was 65 million years ago, but there were some much worse ones before that almost sterilized Earth completely. But life persevered, right? And this is a spectacular picture of a solar eclipse taken by the International Space Station. So here in the bottom, you have the Earth, and you start to wonder, wow, our species, can do a lot of damage to the world, but is also a species that reversed, in a sense, the history of how planets behave. Because if you look at how a planet behaves, it's a very passive thing. Stuff falls onto the planet, right? You have radiation falling onto the planet, you have asteroid, meteorites, and sometimes comet collisions, etc. But now, because of what we have done with science, because of what our technology is able to get, all these primal materials that exist on Earth and convert them into technologies, we're able to actually start to spit out matter into the universe. So it's sort of like the anti-accretion phase in which our own technology, our own creativity now has a planet in this giant Milky Way that we know is able to have an intelligence that is capable of spitting stuff out into the space so that we can understand better our origins. So it's a beautiful story of creativity, discovery, invention, always trying to answer the fundamental questions of existence, right? And one of the things that we realize, and this is a very, very important message, and it's a message that is extremely important for your generation, is that certainly life can exist elsewhere. There's no reason why it couldn't, because the laws of physics and chemistry are the same across space. So yes, there could be other planets that have life, but we can tell you that life as we know it, super complex, multicellular, and especially with organisms that are capable of designing technologies, is going to be very rare, right? If it weren't that rare, we would probably have known about it, despite the enormous interstellar distances that make space travel hard, right? Our civilization is very young. There could be civilizations that are millions and millions of years old. We don't know about them. So for all practical purposes, even if they do exist out there, we know that, first of all, we are kind of alone in our bubble here, in our bubble of space, in our distances. And because of that, and because we understand the preciousness of life, we have the moral duty to protect our planet, to protect other life forms. For example, one of the questions that I saw before was about, are we going to be able to go to Mars and essentially transform Mars in a place for us to inhabit? This is a possibility which is hundreds and hundreds and hundreds of years away from us. We have much more serious problems to deal with the next few decades about how we relate to our planet and the resources and the other living creatures in the planet. So we have to be alert to the fact that we should be focusing a lot of our attention right now in our own planet and the beauty of the life that exists here, as opposed to focusing too much energy on, yes, let's go out there and not pay attention to the problems that we have here. And this is a mission for you guys. This is a mission for you guys to use science, to use technology, to do what's the most beautiful thing about science, which is not just to answer our big questions about existence, which is also to alleviate human suffering, right? And we're all in this together. And I hope that in this brief presentation, I gave you a few pointers of what you could be thinking about in terms of a career in the future. And of course, I'm very happy to answer questions.
Thank you so much, Dr. Gleiser. Let's see if there's. Oh, I know there was one more question from before that we didn't get to. Let me see. Oh, someone asked, this was from Dr. Henry's talk, but someone asked if you could, how do you integrate / use the Pythagorean theorem in physics, and where do you put the negative number?
So here's one application of the Pythagorean theorem in physics, which is a beautiful one, which is in the special theory of relativity. Believe it or not, to understand the special theory of relativity of Einstein, you don't really need a lot of math. You only need the Pythagorean theorem and some basic understanding of things moving about with certain speeds. And if you do that, you can actually show, using the Pythagorean theorem, for example, time dilation, the fact that if you have a moving clock, it's going to tick a little slower. And if I had more time, I could show you, because I teach a course here at Dartmouth that people call Physics for Poets, where I describe to them time dilation using the Pythagorean theorem in something which we call a light clock, which is basically a big room that has a mirrors on the bottom and the top, so the light can go tick tock, and if this thing starts to move, the light is actually going to go on a trajectory which is not just up and down, but it's going to go like this, as you see the light blob going up to the top mirror. And so you form a triangle, and to calculate the length that is traveled by the light that is in this moving clock, all you have to do is use the Pythagorean theorem, and lo and behold, you get time dilation, showing that a moving clock actually ticks slower, from the point of view of the observer that is seeing it moving. So that's an obvious application. And honestly, there are quite a few others. I mean, the Pythagorean theorem is quite essential indeed in physics, okay? But there are many, many other kinds of mathematics that you use in physics. I see a question here from Harry. Can you show us some mathematics? Basically, at least in theoretical physics, physics is the art of solving partial differential equations, with varying boundary conditions and initial conditions. Like every problem that you can think of in physics, from the equations of quantum mechanics that describe how electrons jump around different levels of an atom, to a spring oscillating, a mass oscillating on a spring, to equations that describe the curvature of space around a star. All of these equations are equations that use what we call partial differential equations. So basically you have a function that has more than one variable. You have to take derivatives with respect to all these variables, including time. And by solving those equations, you figure out, depending on your initial conditions and the boundary conditions that you have, what will happen to your system. Okay, so if you want to know what is the equation that calculates the propagation of temperature in a room, so you heat up a room on one side and you want to know what the gas is going to do or a surface is going to do as it heats up, that's the diffusion equation, and you calculate that using partial difference. So they're all over the place. And that is why, I guess, Galileo, when he started to kind of invent this whole thing, he said that mathematics is the language of nature. He was actually inspired by Plato, who came much earlier than him. And Plato was inspired by the Pythagoreans that came much earlier than him, 650 BCE. But the notion is that we humans have this incredible ability to find mathematical patterns in nature, and we use that to describe to the best of our ability what's going on.
Oh, someone also asked, is it possible that planets such as the Kepler 452b could develop intelligent life in the future similar to Earth's history?
Well, I can tell you this, no two planets in the universe, and that's quite a statement, no two planets in the universe will have exactly the same kind of life. And the reason for that is that the history of life in a planet, how it evolved from very simple unicellular organisms on, or just stays a unicellular organism, depends very much on the planet's history, in the sense that if you look at what happened to life here in the last 3.5 billion years, the evolution of life is very much contingent and codependent on the history of all the collision impacts that happen on Earth, all the big cataclysmic events, the giant eruptions of magma that existed during the cooling of the planet and because of tectonic plates moving about. So and this is a beautiful thing, every planet that has life will have a different history because the planet has a different history. So we should not think that there'll be something similar to us. In fact, we should say, kind of proudly, really, we are the only humans in the universe. Because even if you have other forms, even similar, with this left-right symmetry that we have, bipeds, etc., they will certainly not be just like us because the history of their planet is not going to be just like us, which opens up this incredible space of possibilities for the histories of life in other places. So intelligence is not a necessary outcome of life. This is something very important, and people tend to confuse that. One of the greatest biologists of all time, Ernest Mayr, he always said that life is about adapting to an environment. If the environment changes, those who have better adaptations will persevere, and this is what natural selection is, right? But there is no arrow of complexity in life that tells it that it needs to go from very simple to intelligent. That's not what life is about. Those were contingencies that happened to us here. So, for example, if the so-called asteroid that hit Yucatan Peninsula 65 million years ago, which I told you about before, had not hit, dinosaurs could still be around. And there's no reason to believe that they will be very smart because, they were around for 150 million years before this, and they had not, as far as we know, developed language, radio telescopes, poetry, symphonies, or anything like that, right? So if life is well adapted to an environment that doesn't change, it doesn't necessarily change or become more complex. So if you look at the many steps for life in a planet, you realize that it is really hard to predict. And in fact, I forgot to put this, which are some of the books that I have written for general audiences, but they're pretty heady books, And this particular one here, A Tear at the Edge of Creation, talks a lot about life in the history of life on Earth, the importance of asymmetry in physics and in biology. So this would be a good one if you guys want to learn a little more about this stuff.
Yeah, definitely. Anyone else? Any last thoughts? Questions?
I'm pretty sure there's some questions that haven't. There's one beneath the one he just answered.
We also use a version of Pythagorean
No,
theorem. That's a comment. Yeah.
Oh.
Yeah, that's a comment.
Mm-hmm.
Okay. Well, I wish we could
good.
talk more. Yeah, both of your talks were very fun to listen to, but we are on a rather tight schedule because we have so many events today. Awesome.
Yeah.
Dr. Holtz just commented the link of the book if you're interested.
Oh, cool. All right. Thank you. Well, thanks
I'll put it
everyone.
in the YouTube chat too.
And if you have any big
Thank you
pressing,
so much, Dr. Gleiser.
My pleasure. If you have any big pressing questions, find out my email. It's very easy if you know my name, and fire them on. And I'll try to answer them to the best that I can. Okay? All right. Talk to you soon, guys. Bye.
Hi, thank you so much. Okay.
You're very welcome.
Now. Oh, I like this background. Okay. Spotlight. Awesome. Well, next up, joining us is Dr. Jens Koch, who is an associate professor in the Department of Physics and Astronomy at Northwestern University. His research interests in theoretical condensed matter physics include strongly correlated quantum systems, quantum information processing with solid-state devices, as well as transport and coherence and nanoscale systems. don't want to say too much. So without further ado, please take it away.
Will do. I assume you can hear me. All right, then I'll share my screen here. Let's hope that this works as well. So now you should be able to see my screen. Is that right?
Yeah.
Excellent. And so Diana, there's one part where I'll try to show a video, and if that doesn't work for some reason, you just have to cut me off and we'll do without, all right? So Diana and everybody, thank you for having me here. Thank you for the introduction. It's an honor and privilege to speak to all of you today and share some of my excitement about physics. You know, the simple truth is you are the future, right? Soon enough, you will shape this world with your ideas. And so I think getting you interested in science is incredibly important. And I'm very happy to try and do that. So my plan is to tell you the story of quantum computing, or at least a shortened version of it. In fact, there's much more here than one can fit into a single talk, but that's okay. So I'll give you at least a flavor of what quantum computing is. You know, with that, let's get started. So what is quantum computing? What is a qubit? What does superconductivity have to do with that? And hey, why do we care about any of that at all? So this would be the critical moment where Diana will try this video. There's somebody more famous than I am for sure, who can tell us a little bit about what quantum computing is about. Let's see whether this works.
I can't hear the audio, but I can see the video.
Say again, Diana?
Oh, I said I can't hear the audio, but I can see the video.
Okay, so this is not working. That's too bad. All right, but I'm prepared for that. So this is actually a video of Justin Trudeau trying to explain what quantum computing is all about. It's sort of amusing if you've never seen it before, because the colleagues around him kind of smile and pretend to be proud that I guess he learned all of this by heart. I'm not sure how much he understands of it. And so some of the things that he says are here, and we'll actually go through them one by one. So one piece that he mentions is that our regular computers, our regular computer bits, in fact, are either 1 or 0, on or off. And that is certainly something that most of you have heard about before, right? A bit is the smallest unit of information. It's a binary variable, meaning that it can take on just 2 values, 0 or 1. And at the very core of our computers, everything boils down to 0s or 1. All the information is processed in that way. And Mr. Trudeau then continues to say that a quantum state can be much more complex than that. So let's take a look at that and see what that might mean. And for that, I'd like to introduce you to the concept of a qubit, which is short for quantum bit. And that's really just a quantum version of the bit as you know it. I'll represent a qubit by the circle with 2 horizontal lines that they're meant to represent energy levels. There's a lower one, there's an upper one. And then, you know, in quantum mechanics, we like to decorate our states with these funny brackets. So there's a state that is called 0, there's a state that is called 1. That's all very similar to a bit. And you might ask, well, this is very symbolic. What could a qubit be in real life? And in fact, there are lots of researchers who use different kinds of systems as qubits. So you could select electron energy levels in an atom to work as a qubit. You could use an electron spin. You can use photons as qubits. And what I'm particularly interested in my group is to use superconducting circuits as qubits. So 0 and 1, that looks very similar to the classical bit. What's special about a quantum bit, about a qubit? So in fact, this symbol here on the left-hand side is just our name for the state of the qubit. And you see on the right-hand side, there's something peculiar. This qubit does not have to be in state either 0 or 1. It can be in both states at the same time. Quantum mechanics allows for that. And in fact, these two quantities, alpha and beta, they're complex numbers, and they regulate how much 0 is part of that state and how much 1 is part of our qubit state. And since complex numbers, just like real numbers, are from a continuum, every qubit can actually take on an infinite number of states. So that certainly makes a quantum state more complex than that of a bit. And that is amplified when you think about more than one qubit. So let's start with one here, and let's add a couple, a whole bunch if you wish. I'll call the number of qubits, I'll give that the symbol capital N. And the state of this entire system of n qubits is complicated. So there are all these different states. The first one here is where all the qubits are in the ground state and the 0 state. This one here is the last qubit is in the 1 state, all the others are in the 0 state, and so on. And you know, there are as many different choices here as there are binary numbers between 1 and 2 to the n. And so there are, in fact, 2 to the n complex numbers that have to be specified to represent the state of an n qubit system. And last year, Google does research on qubits, and particularly superconducting qubits, and they presented a quantum processor with 53 qubits. And if you want to store that information encoded in these 53 qubits on a classical computer, you need a lot of memory. In fact, you need 140,000 terabytes worth of memory to store all these complex numbers. So that's pretty impressive. And so Mr. Trudeau then continued to say in the video that is missing here, but he says quantum mechanics allows us to encode more information into a much smaller computer. So that's what's exciting about quantum computing. Now, I wasn't born in the US, but have lived here for a while. I understand that in this country, size is very important, but I'd like to convince you that size is not everything. So what about this much smaller computer? If you think about your desktop computer or your laptop, then that is actually not much smaller than a quantum computer today, which might look like this. This is one of the quantum computers at IBM. In fact, the thing where the quantum computer is hiding is this cylindrical vessel. That's a dilution refrigerator, which just makes these qubits very cold and behave more quantum mechanically. And so that size comparison is not so much in favor of the quantum computer. But in fact, maybe the better comparison is between this quantum computer and a supercomputer, which needs a huge room. And so that is certainly bigger than the quantum computer. Now, I wanted to argue that size is not everything. A very important aspect of computing is runtime, right? So here's once more the supercomputer on the left, and then on the right, you see Google CEO with, well, their version of the quantum computer. This is, again, a dilution refrigerator, which is now open. So you see all the wiring that goes down to the qubits. And the Google team invented a somewhat contrived computational task for this quantum computer to solve. And they did so, and they estimated that this huge supercomputer at Oak Ridge would need about 10,000 years to solve that computational problem. And the Google machine could solve that problem in 3 minutes and 20 seconds. So runtime is an important aspect of computing, and quantum computers can do certain tasks a lot faster than our current computers today. And so let me try to say a few words about, what makes a quantum computer faster, what makes a quantum computer tick. And one aspect of this can be understood in the following way. So let me represent this quantum computer as a simple machine that takes some input here and then it'll spit out some output. So this could be a simple quantum algorithm of some kind. And so let's suppose that we feed in the state 0. And what the computer will spit out is, well, it will apply this algorithm U to our state 0, and out comes U applied to state 0. Simple enough. Now we can rinse and repeat and stick in state 1, and out comes the algorithm applied to state 1. So far, that looks very much like what you could do with a classical computer. Now the clue is here. Instead of sticking in 0 or 1, you can stick in this combination of 0 and 1, a state that has both of them at the same time. And out comes, well, one component where the algorithm has been applied to state 0, and another component where the algorithm has been applied to state 1. So this is what people call quantum parallelism, where the quantum computer, in a way, processes all possible inputs at once. Now that sounds fantastic. It turns out that life is a little bit more complicated. There's some legal footprint to this. One can show rigorously that this ingredient alone would not yet be sufficient to actually make anything faster. I'm not going to prove that. I'm just telling you this as a bit of information. So a second ingredient that is required for quantum speedup is a property of quantum mechanics, which seems a little bit mysterious, but we've gotten used to it. So let's see what we can do with 2 qubits. The simplest kind of state for such a system of 2 qubits is what is called a product state. So qubit 1 is in its state, and qubit 2 is in some other state, represented by the 2 different colors here. An entangled state is different. In an entangled state, the 2 qubits share this overall state with each other. We can't really say qubit 1 is in one state, qubit 2 is in the other state. They share this overall state. And I like to compare that with the situation that we sometimes see with dog owners and dogs, which somehow become very similar. And if the owner does something, the dog does something. If the owner looks one way, then the dog looks the same way. So that's a little bit like what entanglement is about. Now, I told you that in my group, we are working together with experimentalists on developing circuits that will act as qubits. And if you think about a circuit, then maybe this is what you have in mind. Now, this circuit would be horrible for a quantum computer. And that has to do with something that you're all familiar with. So if you're sitting there with your laptop, you can maybe put your hand on your laptop, and what you'll notice is that it's warm, right? Why is it warm? Well, because there's Ohm's law, and Ohm's law says that electric energy in a resistor is converted to heat. All our metals are resistors, so our computers produce heat. And that is a very bad thing if you want a system to behave quantum mechanically. So some people say that quantum mechanics is fragile. Whenever stuff happens like emission of heat to the environment, then most of the quantum effects actually go away. And that is why it's so useful to build these circuits out of superconductors. So if you take a metal like aluminum or niobium, you cool that metal down, then it will become superconducting and it will lose all its ohmic resistance. So if you have a loop of aluminum in the superconducting state, you kick on a current, then that current will go around the loop forever. And if you build your circuits in this way, then they do behave quantum mechanically, and they're a little bit like artificial atoms. So they have discrete energy levels, just like a hydrogen atom does, and you can manipulate by shining certain types of light on it, in this case, microwaves. So you take a microwave generator and you send a microwave signal to the circuit, and that way you can perform algorithms and read out the state of your quantum processor when you're done. One thing that I'd like to mention briefly is that you can actually play with a quantum computer yourself. This is something fairly new still. So IBM has a quantum computer where you just go on this website displayed on the top right. You open a free account with them, and there are lots of tutorials if you feel like you don't understand quantum computing yet. So they have a lot of information there, and you can actually carry out your own quantum algorithm of your choice on a small quantum computer. They're not very big yet. They're not hugely useful yet because the number of qubits is limited. But we're making progress towards larger quantum computers. And so let me finish with a couple of slides telling you about what are quantum computers good for, right? That's an important question. That's why we're interested in them. So one example has to do with encryption and breaking encryption. So RSA encryption is one flavor of encryption which is safe currently because it's hard to decompose integer numbers into their prime factors. Now, for 15 equals 5 times 3, I managed to do that in my head, and that's no problem. For 21,809, I'll probably take a little bit longer. But then if you make this integer number larger and larger, it becomes exponentially hard to find the prime factors. And that is behind why RSA is secure. And it turns out that quantum computers can accomplish this task of prime factor decomposition very efficiently. That's known as the Shor algorithm. What else are quantum computers good for? They can perform certain types of database searches a lot faster than our regular computers today. So quantum mechanics is good at that as well. They can solve linear algebra problems faster and more efficiently. And you know, solving systems of linear equations is something that is needed all over in science in many, many places. One modern example, one exciting example being machine learning algorithms, which do require linear algebra along the way. So if we had a quantum computer, we could also enhance machine learning and make that more efficient and faster. And then finally, another example is with a quantum computer. It's actually very easy to simulate quantum processes, something that is hard with our classical computers. And so you might be able to use a quantum computer to predict chemical reactions and to predict properties of chemical compounds, which really would revolutionize drug development and various other aspects. And so I see that I'm not quite running out of time, but I'm roughly on time. So I hope that this gave you a flavor of quantum computing. I think you now all know more than Justin Trudeau about quantum computing. And finally, I thought I'd end with a slide that shows some of the aspects of being a physicist and some of our activities. I'm really looking forward to questions from you. So again, it seemed like most of you like to post your questions in the chat. If Diana allows, then I'd also be very excited to actually get to meet you, so to speak, and have you ask your question in person.
Hi, okay. Sorry, my dad just walked in. Oh, someone just asked, what are the little brackets that you use to represent states for?
The little bracket, yeah. So there's of course a story behind everything. So this little bracket, its true name is a ket. I believe it was introduced by Dirac, the famous physicist and mathematician Dirac. And this ket comes with a partner, which is the bra, and together they are a bracket. And so it's just a fancy way of denoting a quantum state. All of quantum physics essentially is linear algebra. So you know, if you're familiar a little bit with vectors in, say, 2-dimensional or 3-dimensional space, probably you denote your vector by putting a little arrow on top. In quantum physics, these states are actually vectors, but in a different type of vector space. And instead of putting arrows on top, we decorate them with this funny ket symbol. It's just notation, really.
Oh, someone asked, would you say that it is important to learn Python for this type of science?
it's certainly useful. I think learning some programming language is useful, not just in physics, but in various sciences and even for regular life. I have this little piece of Python code down there in the bottom right, because we, in my group, we've developed an open source Python library for superconducting qubits. We're very proud that this has been online for download for a while now. The last time I checked, we had about 15,000 downloads so far. And so, you know, a lot of the work that we do as physicists can be done with pencil and paper. But as soon as problems become a little bit more difficult, right, then there's some programming, some numerics involved to solve the problem that way. And so that's an important skill, I would say. Yes.
Oh, someone asked, how does the US stand in quantum computing? Heard that China's way ahead of us.
All right. Well, there is competition for sure. But the US is very much aware of that competition. So you may have heard of the National Quantum Initiative, which has started to pour billions of dollars into the field to stay and be competitive. The most recent effect of that bill is, I believe in the next 2 weeks or so, the DOE, the Department of Energy, will announce which of the many proposals are going to be funded and create large national centers for quantum information science. So there's a lot of funding that is being invested into this field, which is very exciting. There's lots of opportunities for young people to join the field and become quantum scientists, quantum engineers. We're definitely looking for you guys to become interested and join us.
Awesome. Someone also said or asked, how much does it cost to build a quantum computer?
Oh, quite a bit of money. I don't know how to do this calculation really. What I can tell you maybe a little bit about is how much does it cost an assistant professor to get their lab started these days. So the dilution refrigerator that you need, assuming that you're interested in working with superconducting qubits, that dilution refrigerator costs somewhere in between $300,000 and $500,000. And then, you know, there's about that much that also goes into microwave equipment. So you need fancy microwave generators and devices that shape the microwave pulses to allow you to talk to your qubits, to manipulate their quantum state and read that state out. So there's a price tag, and I think overall there's to build a large quantum computer that will cost quite a bit more money. But you know, I think as far as quantum computing is concerned, we're sort of in the age of the very first classical computers, right? Where classical computers filled entire rooms. They consisted of vacuum tubes, and in the beginning, the CEO of IBM at that point claimed that worldwide we'll probably need 5 computers, and that's enough. And now look at us where we are with all of our computers surrounding us daily. And I think that's at least the way I view the status of the field. We're really just at the very beginning.
Awesome. Oh wait, there was one more question from the YouTube. How do you get involved with quantum mechanics early on?
How do you get involved? That's a good question. You know, I'd be happy to dig out some books and make recommendations. I think my question back would be, what do you already know? Do do you know a little bit of linear algebra? That's a very good prerequisite to have. But there are other books that are more at a general level and tell you about history and general concepts of quantum mechanics. And I think that can be a nice starting point. Or if you're adventurous, right, then you can really just open an account on the IBM website for their quantum computer and start playing with it. It's a beautiful situation where, you know, when I started doing research in this field, there was no such thing. If I wanted to play with a quantum computer, I had to, you know, visit experimentalists and see whether they would be interested in carrying out a certain experiment that I thought could be cool. But these days you have access to these processors. IBM has a very nice collection of introductory tutorials, how to understand qubits and manipulate them. And so I think that could be another exciting way to enter the field.
About whoever just asked about the link for the IBM website, I also put it in the YouTube chat, and I'll also just comment it in the comment section. Oh, and we have one last question, and then we have to move on to Dr. Holtz. But we had a question of, do you take any high schoolers
Oh yeah,
to help you with your work?
Definitely.
Oh.
We've actually worked with 2 high school students from the local area here in the recent past. They have, under our guidance, they've played with the IBM machine, and they also helped us with our superconducting qubit library. So they knew a little bit of Python. So there are definitely opportunities.
Okay, awesome. Sorry, this question I've seen like multiple times, but because someone asked, what happens when we use minus sign in place of addition? Or what?
Minus sign in place of addition. In the context of quantum mechanics? This sounds like a very general question.
Yeah. It gets bigger. Like, all right, there's no follow-up. So, all right, thank you so much, Dr. Koch. I hope everyone really enjoyed learning about quantum computers. And now we're going to move on to Dr. Holtz. So I'll hand it off to Kailash, who's our amazing physics competition writer, to introduce.
Thank you, and thank you, Dr. Holtz, for coming. Just a little bit about him. Dr. Daniel Holtz is a professor of physics at the University of Chicago in the Department of Physics, Department of Astronomy and Astrophysics, Enrico Fermi Institute, and the Kavli Institute for Cosmological Physics, and he pursues research in astrophysics. He's a member of LIGO, the large-scale physics experiment that first successfully detected gravitational waves in 2015 and provided experimental evidence of Einstein's theory of general relativity for the first time in history. Dr. Holtz has published over 100 papers on a variety of topics in astrophysics, astronomy, and his work with LIGO, and is here to speak with us today about some of his research, as well as his path to becoming a professor. Thanks for being with us and speaking to help inspire the next generation of scientists and researchers.
Thanks for having me. I'm just sharing my screen. There we go. Okay, so hopefully everyone can see that. Thank you very much for having me. And thanks for that very generous introduction. Let me, I'm just gonna make sure I have a clock here so I don't run out of time. So I was gonna give a short overview. I mean, you've heard a lot of different things already this morning. I'm gonna give an overview of LIGO and some of the interesting results there, just to give you some flavor for what's going on in this field, this brand new field. And then at the end, I'll spend a little time on more general things about at least my path to being a physicist. So to get started, you've already seen this picture from Marcelo. This is the Hubble Deep Field. And I'm talking about something that has occurred a long, long time ago in a galaxy far, far away. Here, there's actually quite technical. It's, on the order of 40 megaparsecs, which is over 100 million light years away. And over 100 million years ago, two neutron stars collided. And the story I'm telling you is about the echoes of this collision and how we got to hear those echoes. So to give you a little background, and I should say, this all happened, what for me is very recent, just a few years ago, after roughly a century of preparation. So here's the basic thing you need to know, and this is at the highest level. The theory we're talking about is general relativity, and it's already been mentioned. Both special and general relativity had already been mentioned. And the basic idea of general relativity, this is our theory of gravity. It's that space and time are linked. And so there's space-time, there's this fabric of space-time, and everything occurs in space-time. And you've probably heard that space-time is warped, like the sun warps space-time, and that's why the Earth goes around the sun. That's how we think about gravity. It's a geometric thing. It's a very powerful idea. But that warping can get stronger and stronger, and eventually, in some sense, become infinite, and that's what we call a black hole. The warping is so strong that light can't escape anymore. Now, something you may be less familiar with is that space-time itself can wiggle, and that's what gravitational waves are. And I'm just going to spend a couple of slides just to give you some intuition for why that happens. I think it's relatively easy to see that there must be something like this. And so here's the picture I want you to have in mind. This is a duck on a pond. And the pond, if the duck is not moving, the surface of the pond is still. Okay? If the duck starts to move, you get ripples in the surface of the pond. Okay? And if you measured those ripples, you could actually figure out, oh, there's a duck, the duck seems to be over there. Here's how fast it's going. You could probably even figure out how big the duck is. There's a lot of information in the pattern of these ripples. The duck, if it moves, generates ripples. There's no way around it. Okay? Gravitational waves are exactly the same thing. You just replace the duck with two neutron stars or two black holes going around each other at close to the speed of light. And then you replace the surface of the pond with space-time itself. And then otherwise, it's pretty much the same thing. As the neutron stars, say, accelerate around each other, they generate ripples in space-time, and those go out to the edges of the universe, and they carry information about what has happened there, how massive those neutron stars are, how fast they're going, where they're located. By measuring the ripples, you can figure out a lot about what's happened. And in fact, those gravitational waves are the way the universe keeps track of where everything is. Whenever anything moves in the universe, it suddenly gets, if you get up and you go to the other side of the room, you emit gravitational waves to tell the entire universe you've moved. Because the whole universe has to know how the gravitational field has changed. Okay, so those are gravitational waves. Now, it took us about 100 years. Einstein first predicted these in 1917. And he thought they would never be detected. Lots of people thought they would never be detected. Even more recently, I think even 20 years ago, you could find people who thought were extremely unlikely to ever detect these. So the question is why? Most people are convinced that gravitational waves exist. Why would it be so hard? And the trick is the scale. And this is one of these things that happens in physics where it's really hard to wrap your mind around what's going on. And you're probably used to, okay, we've talked about how old the universe is, how big it is. These numbers are big. This is another really big or really, really, really super tiny number. And so here's, just to give you, again, some intuition. When gravitational waves pass through things, they cause the distances to oscillate. So right now, gravitational waves are, whatever room you're in, gravitational waves are passing through, and the walls are getting closer and farther apart. But it's by a tiny, minuscule amount. And the relative amount, the fractional amount, is equivalent to, if you look at the distance between us and the nearest star, not the sun, but the next nearest, which is, 4 light years away. At the speed of light, it takes you 4 years to get there. Light is pretty speedy, so that's pretty far away. That star is oscillating by the width of a human hair. And we want to measure that. And that's why it's hard. Most people would say, and I think if you think about it, there's this star super far away. It's oscillating back and forth by the width of a human hair. We're going to measure that. If I told you that, you would say, that's insane. It's impossible. It's not going to happen. And a lot of people have said that. The trick is that we built a detector and we actually detected this. And that story is really remarkable. And there's an incredible amount of physics and engineering in that story. I'm not going to spend a lot of time on it. The basic idea is that you shoot photons, just light, down 2 tubes. There are shiny mirrors at the end of the tubes. The light goes out both ends and comes back, and you see which photon gets back first. And you kind of compare that, and that's called a Michelson interferometer. And if you do that, and it's a very fancy laser and very fancy mirror, there's a lot of very fancy stuff in here, you can actually get to the sensitivity where you detect gravitational waves. Okay, so that's a really fascinating story. I'm going to skip over it just to say we actually built this machine. We actually built 2 of them, and now there are 3, and there'll be a 4th soon. And you can ask more about that later. Okay, so on September 12th, 2015, we first turned on kind of the latest incarnation of these machines, a kind of more sensitive version, the most sensitive version we'd ever had. 2 days later, this is what we heard, and I'm gonna play you the video, and there should be audio as well. So you turn on your, turn up your speakers. This is just a plot where it's just time, and you can think of it as, we detect the wiggling of these mirrors. If you take that and then you just put that signal directly into your speaker and increase the volume by about 20 orders of magnitude, that's what you're going to be hearing directly. And you'll hear it just comes as a thump. I'll play it twice, and then I'll shift it to higher frequency so you can hear it a little clearer. So here we go. So that thump we heard in these 2 detectors that are very far apart at the same time, and it was actually pretty loud by our, the fact that you can hear it above the noise, that whoosh in the background is just noise. And then suddenly there's this thump in 2 detectors. That thump, that's black holes colliding. And we analyzed it, and we realized it's black holes colliding, and we could figure out all this stuff. And it was incredibly exciting because this was something that had been predicted basically a century before, and we got to hear it. And by analyzing that sound carefully, we figured out it's 2 black holes. The black holes are crashing into each other at almost the speed of light. Each black hole was 30 times the mass of the sun. So you take our sun, you take 30 of those, and you squash them down into something, 100 kilometers across, something like that. And then you take 2 of those and you crash them into each other, and it makes this sound that we heard. It's really amazing. And just as an aside, the amount of energy being radiated, the power of these 2 black holes, it's louder. There's more energy at that moment than all the stars, all the light from all the stars in the entire observable universe combined. Another one of these things that should just blow your mind. Okay, but that was just the beginning. We got a Nobel Prize for that, and it was lots of excitement, but we've continued to operate, and we heard something even more exciting. And so this is to give you some sense of what that was. So what I'm showing here, these are just the drawings of the sounds, if you like. It's just a waveform. This is just time at the bottom, and this is just oscillations. You can think of it as oscillations in a speaker. So it's just the sound, and these are the sounds we've heard. That this green one at the top is the one I just played for you, and that was a thump. It went whoom. That was it. very short, a fraction of a second. And we've heard some others. At this point, we've actually heard something like 50 of these. I'm just showing a few of them. And some of them are, slightly higher frequency, but they're all kind of basically thumps, and all of these are black holes. Okay. On August 17th, 2017, we heard something very different. Okay, and I'm going to show you that. And so you can see these things here. Now, if you look down at the bottom, I'm now going to show you what we heard on August 17th. Okay, here we go. Now, you can tell this one is a little different. It's going on much, much longer. And it actually goes on much, much longer. The others were thumps, they lasted a fraction of a second. This one lasts over a minute. So I'm not going to have you sit here, but this is a good time to turn up your speakers because this gets really good, I think. So here we go. We're going to jump ahead. And remember, this is what we're hearing in our gravitational wave detector. Okay, so that is what we heard on August 17th. And that is totally different. You can tell just by listening, it's totally different. It's much higher frequency. And that means it's lower mass, because when you go to smaller objects, they can get closer and go around each other faster. And so they merge at higher frequencies. So the farther along you are in this plot, the faster you are when you merge, when the two objects crash into each other. And that means the smaller the mass. And so this is really tiny compared to those 30 solar mass black holes. And in fact, we think these were two neutron stars. Okay, so that's already amazing because that's a whole new class and we got very excited about that. Story doesn't end there. The story continues. Here's another plot. And again, there's some sound here. And so I'm just going to play you. At the bottom is what we heard in our gravitational wave detectors. At the top is what we detected in gamma rays. So very high energy light. There's satellites, including the Fermi satellite, up, orbiting the Earth, and those are observing gamma rays. And here I'm going to play both at the same time, synchronized. Okay, that ding is a peak in gamma rays. So these two neutron stars crashed into each other, close to the speed of light. There was a pause of about 2 seconds, and then there was a burst of gamma rays. And that's remarkable. That's called a gamma ray burst. And those happen roughly every day, but some of them have been very mysterious. Now we know, oh, that's coming from two neutron stars crashing into each other. Okay, story doesn't end there. We then pointed a bunch of telescopes and discovered a new star that appeared on the sky. And I don't know if you can see it, there it is. Probably doesn't look that impressive to you, but that's a brand new star. We call it a kilonova. And that was also a result of these two neutron stars crashing into each other. They threw out all this material, very hot material, radioactive material, and it got super bright, and then it dimmed over a few weeks. And we found it on the sky and got to measure the details of that. So this whole story is pretty amazing. Here's a movie. This is an artist's conception. We have a lot of data, but this is kind of to get a close-in view. And the point here is that we're seeing light and we're hearing gravitational waves from the same source. And that's never been done before. And it teaches us all sorts of things. And so I'm just going to talk briefly about some of the things we've learned, and then we'll go from there. Okay. But it's given us profound insights about general relativity, nuclear physics, astrophysics. Tons and tons of papers. Thousands of scientists have gotten excited about this. It's really been one of these transformative events in science. Okay, one thing we learned right away is that, how fast gravity goes compared to light. And so the idea here is, well, you heard that ding from the gamma rays, And then that happened just 2 seconds after the gravitational waves, the merger. And that tells us that light and gravitational waves travel at basically the same speed, because they've been traveling for 100 million years and they arrive within 2 seconds. And in fact, what we think happened was the gamma rays were emitted 2 seconds after the merger, and then they both travel at exactly the same speed. That's a remarkable measurement. It hadn't been done before, and it ruled out a lot of the modified theories. For example, Marcelo mentioned that you can modify gravity, change gravity to try to explain dark matter and dark energy. This means it's much harder to do that because gravitational waves and light go at the same speed. So there's a whole class of modifications that you can't do. Okay, so that's one thing we learned right away. Another thing we learned by looking at the properties of that star, we figured out that this must be where most of the gold in the universe is made. So, you know, if you have any gold jewelry, any gold around you, that was almost certainly made in binary neutron stars. The collision that we just observed makes 50 times the mass of the Earth in gold and just shoots it out into the universe. So that's been a big mystery. Where is gold made? We helped figure that out. We also got to measure the age of the universe. This is something I'm most excited about because this is something I'd worked on a long time, wanted to do. And then we had this event and I could do it. I won't go into any details except that we actually got a measurement with this first event. And, you know, it's incredibly exciting. And what's most exciting about it is that as we go on, we'll do even better and better. And this is something people are arguing about a lot in cosmology. It's one of the hot topics in cosmology, and we'll be able to kind of figure some stuff out. Okay, I'm just going to mention as a side, so I'm at the University of Chicago, and I have a group, and here's a picture, a recent picture of the group on a social gathering. We're all, the angle makes it look like we're close, but we're not. We're all distanced, and wearing masks and being very careful. But this is, you know, the group, and we've all worked together for a few years now on all of this science, and it's really been extremely fun. Okay, so I think I have about 5 more minutes, so I'll spend just a little time on some background, since it sounded like you might like to hear a little bit about my path. So I tried to put together some sense of this. My path has been pretty random, to be honest. I have not been super like, oh, I'm going to be a professor and that's all I care about and off I go. I've just, you know, been fascinated by things, as I'm sure all of you are, and just like to ask questions and figure things out. And I had a teacher in high school who was amazing and just encouraged me to keep asking questions. You know, after a while, most people get sick of you asking questions. Often because you get to a point where people don't know the answers, and that's frustrating. But he loved it, and he got excited by that, and would just continue to encourage me to ask more questions and go try to figure things out. And so I continued to do that in college and had lots of interests and just pursued them, and kind of had this circuitous route. I went to graduate school, and then I worked at a national laboratory for a while, and then I decided to come and be a professor, and now I'm a professor, and it's great. But mainly just because I get to think about things and continue to ask questions, and that's my full-time job: ask questions and try to figure things out. It's pretty awesome. You know, how do I actually spend my time? I teach classes, undergraduate and graduate classes. I mentor graduate students, so I help them get their PhDs. I spend a lot of my time doing research. You can see some of my papers up here. These are some of the recent things I've been working on. I spend a lot of time talking, going to meetings. You know, we used to be at the board a lot, you know, trying to figure things out. Now it's mostly through Zoom. There's a lot of computer coding. Then I also spend a lot of time, there's other stuff. When you're a professor, you spend time kind of helping run the department and engage in the community. I also, in some of, you know, my spare time, I help set the time of the doomsday clock, which is something I really care about, but it's a different, you know, issue. But I encourage you to learn about that. because it's a group of scientists that are just concerned about the future of civilization. This was founded by Oppenheimer and Einstein shortly after World War II. And unfortunately, these concerns still persist, including climate change and nuclear annihilation. But that's a depressing topic, and so we'll skip that for now. I also spend lots of my time doing other things. Life is really full. Now, I will say just because I think everyone goes through this. My career path has not been direct and straight. It's definitely had lots of ups and downs. There are definitely moments where you're like, I'm not sure I'm up to this. I can't figure anything out. I don't know if this path is going to lead anywhere. Maybe I'll go do something else. For a while, I really thought I should go work at Google. There are lots of different things to do. The main thing for me has just been I keep asking questions because that's what's fun. And things have really worked out. And what's great is you just keep learning from everyone around you, teachers and friends and collaborators, and especially lately students. And it's really been wonderful. I have to say this path is just, it's so fun. Every day you just wake up and it's like, what do I want to think about today? And so, yeah, that aspect has really been, so just thinking about this and writing this talk has reminded me I feel very lucky that way. Anyway, okay, I'll end there.
Wow, thank you so much, Dr. Holtz. That was very fun. Does anyone have any questions for him? I actually have a question as well. You mentioned that before when you were talking about LIGO, that you guys are now making a fourth one, and we could ask about it later.
Yeah. So so what we're doing now is we have 2 LIGOs. There's one in Hanford, Washington, and Livingston, Louisiana. There's actually a 3rd gravitational wave detector in Italy, outside of Pisa in Italy, called Virgo. And then there are 2 more new ones being built, one in Japan called Kagra, and one in India called, right now, just LIGO India. And so eventually we hope to have 5 of these detectors. Now, right now, actually, all of them are being upgraded. LIGO India and Kagra are still being built and refined. The hope is that in about maybe a year and a half or 2 years, we'll turn them all back on, and then we'll start listening again, and we'll see what happens. So there's this whole kind of path forward, and the next decade should be quite fascinating. I should also mention that in addition to the ground-based detectors, there are also plans to put a gravitational wave detector in space. And right now that mission is called LISA, and that's being led mostly by the Europeans, and that would be phenomenal. And that's about a decade away. And that, instead of detecting what they consider tiny black holes, only 30 times the mass of the sun, that one detects million solar mass or more, billion solar mass black holes, the black holes that lurk at the center of galaxies. It detects those crashing into each other, and it can listen to them out to the edge of the universe. So that's a completely different sort of thing with gravitational waves, which would also be phenomenally exciting. Yeah.
Awesome, thank you. Someone also asked in the chat, does the distance between each gravitational wave increase exponentially as they travel further away from its source, just like in the ponds? And can you use this data to calculate how far away the source is?
Yeah, that's an excellent question. And so, this is just a version of the inverse square law. So, the binary emits energy in gravitational waves, and it's basically the inverse square law says as you get farther and farther away, the amount of energy in the gravitational waves gets less and less. And that's very clearly predicted. And so what it means, and this is specifically when I had that one plot about measuring the age of the universe, that is using this effect by very carefully measuring how loud the gravitational waves are in our detector, we can figure out how far away the binary neutron star was. And that lets us measure the expansion rate of the universe and therefore infer all these profound things. So yes, so energy is conserved, and by utilizing that, we figure out a lot about the universe. Yeah, excellent question.
Awesome. Someone also asked, are there specific locations on Earth better suited to detect these waves? If yes, what characteristics make them better suited?
Yeah. So yes, there are definitely better and worse places to detect these sorts of waves. And it's, these, you can think of it as it's extreme, it's very sensitive, right? We talked about the star at the width of the human hair. It's very sensitive. So you need to be in a place that's extremely quiet. So you can't be near a big city. You can't be geologically active. For example, one of the detectors was put in Livingston, Louisiana, kind of in the middle of nowhere, in the middle of a big forest, which seemed like a good place, except they're logging in that forest, and the trucks driving around and the trees crashing down cause noise, and that's a problem and has to be compensated for. So you try to go to places that are quite isolated and very geologically stable. And so there have been a number of places around the world that have been identified to be, very positive that way. But finding these locations is a big deal because, if it's too loud, all you're going to hear is, traffic on a highway. Or for example, if you're too near the coast, you hear waves crashing on the coast. Where too near is 50 miles or 100 miles, it would be deafening. And so you really have to get away. These detectors are very sensitive. Yeah, good question.
Okay, I think we can take one more question because we have to get moving with our very tight schedule. Mark asks, did the detections from the colliding neutron stars affect our efforts to make a grand unified field theory?
Yeah, okay, so that's a question about, can we unify the forces and understand fundamentally, all of physics? And yes, I mean, there are certain things that it gives us clues about, especially if your goal is quantum gravity, where you want to join relativity and quantum mechanics to have one theory which describes everything we've observed in the universe. Right now, as you probably know, there's quantum mechanics, which works extremely well. We just heard a beautiful talk about quantum computing. That all works fine. Then there's general relativity, which describes cosmology, black holes, all the big stuff. That works totally fine. But we know the theories don't play well together. And we need a theory that kind of fixes that and does it all. And so that's something we're looking for. Needless to say, here's a case where we have quantum mechanics. The light is being generated by quantum mechanical processes, and relativity, general relativity, gravity, which is generating the gravitational waves. So it's a natural place where we get to combine that. And so I gave you the example of the speed of light. Just knowing that gravitational waves, gravitons, if you like, travel at the speed of light, that they're the same, is a major advance. One of the things I looked at, I thought was just super fun, was you could also use this to figure out the number of dimensions in the universe. And so just by taking this binary neutron star, we figured out that the universe has 3 + 1 space-time dimensions, 3 spatial dimensions and 1 time dimension. Now you're probably thinking, you just look around your room, you can tell there are only 3 dimensions plus time. But we use this system to determine that the universe, that's true out to 100 million light years away. That even on cosmological distances, there are still only 3 + 1 space-time dimensions. And that's, very, very interesting. And we used it by comparing how loud the gravitational waves were to properties of the light. So yeah, I mean, we're learning an incredible amount about, physics, basic fundamental physics from these sorts of detections. And I should say, this is just the first one. We hope to do many, many more. And so there's a lot still to learn. Great question.
Awesome. Thank you so much, Dr. Holtz. I hope everyone enjoyed that talk and all of the previous physics talks. I certainly have. Right now we have to move on to Dr. Aidala. So thank you again. And let me just now spotlight
Yeah, thank
Dr.
you, everyone.
Aidala. Thank you, Dr. Holtz. Okay. My Wi-Fi is a bit flaky, so all right. Awesome. Kailash, you can take it away.
Thank you. Dr. Christine Aidala is a professor of physics at the University of Michigan and a researcher in the field of high-energy nuclear physics. Her research primarily focuses on quantum chromodynamics, analyzing the theoretical strong nuclear force between the fundamental particles that make up protons and neutrons. She works in a large-scale experiment at the Relativistic Heavy Ion Collider in Brookhaven National Laboratory, named PHENIX, investigating the interaction between protons and heavy ions. Dr. Aidala is a recipient of the 2015 Sloan Research Fellowship, as well as the 2015 Career Award from the National Science Foundation, and is here to speak today about even smaller components of protons, which are quarks and gluons. Thank you, Dr. Aidala, for coming here. We appreciate it.
Yes, thank you. So we've been hearing about very large distance scales, cosmological distance scales across the universe. Now we're going to switch to very, very small distance scales, as my research focuses on the internal structure of the proton. So protons are a fundamental building block of everyday matter. Every single atom and all of the everyday matter in the world around us is made of or includes protons. Here I show just simple schematic diagrams of two elements, an atom of hydrogen, an atom of carbon. The proton, we can look at the hydrogen atom. Proton carries a +1 electrical charge. This is counterbalanced by the -1 electric charge of the single electron. We go to a carbon atom as another example. We have 6 protons balanced by 6 electrons. We also have in the nucleus of a carbon atom 6 neutrons, which are very similar to protons in many ways, but they're electrically neutral, which is why they're called neutrons. So how did we first discover the nucleus of an atom? Well, we've got to go back a little more than 100 years. So there was a series of experiments done in Manchester, England between 1908 and 1913 by Ernest Rutherford, Hans Geiger, and Ernest Marsden. You might have heard of Geiger's name before because the Geiger counter is named after him. It's a device used to detect particles from radioactive decays. What they did was they scattered something known as alpha particles, which were produced in the radioactive decay of the element radium. They scattered them off of a thin gold foil. So think aluminum foil, just a little bit more expensive and harder to buy in the supermarket. So alpha particles are charged. They have +2 electrical charge. And what they saw when they did this experiment with the alpha particles, going through the gold foil, most of them went through and were only deflected just a little bit. And this actually was consistent with the hypotheses of the atomic structure of the time. The most popular hypothesis about atomic structure at the time was known as the plum pudding model. It said that the positive and negative charge centers inside an atom were distributed approximately evenly over the volume of the atom. And so if you have a positively charged alpha particle passing through a gold atom, then okay, it would have some positive charge centers nearby, but also some negative charge centers nearby. And it wouldn't get repelled too much or attracted too much. It would just get deflected by small angles. However, I think this is a nice illustration of how important it is to repeat your experiments. They did this tens of thousands or hundreds of thousands of times. And what they saw was that about 1 in 8,000 bounced off at a sharp angle. So maybe at a right angle or even back toward the beam direction. And this was a surprise at the time. What it said was that the electric charge centers, the plus and minus charges in an atom, were not equally distributed over the volume of the atom, but in fact, there was a positively charged core at the center. So when the positive alpha particles came in, most of the time, because this was concentrated all at the center of an atom, most of the time they didn't come that close, and so they were only deflected at these small angles. But the times when they did come close to that positively charged core, which we now know to be the nucleus, they were repelled very strongly and could bounce back at sharp angles. And so now if we just think of the size of the nucleus relative to the size of an atom, just rounding to powers of 10, I'm going to round this 1 in 8,000 to about 1 in 10,000, right? So the size of the nucleus is only about 1/10,000th of the size of an atom. This is why about 1 in 10,000, 1 in 8,000 of these alpha particles went nearly straight through. They were using gold foil. So gold has a total of 197 protons and neutrons in the nucleus. So now if we think of the size of a single proton, just the nucleus of a hydrogen atom, this is going to be even smaller. So it's about 1/100,000th of the size of an atom. In terms of meters, we heard a lot yesterday about nanoscale science, 10 to the minus 9 meters. Now we're a million times smaller distance scales, about 10 to the minus 15 meters or 1 femtometer. So the radius of the proton is about 0.8 times 10 to the minus 15 meters. So we skip ahead a little more than 50 years, and now they were doing very similar experiments with different people, obviously, very similar experiments at the Stanford Linear Accelerator Center in California. A very similar idea to those Rutherford, Geiger, Marsden experiments from the early 1900s. They scattered electrons off of protons, and they saw that many bounced back sharply. And they, just using conservation of momentum, they saw that those scattered electrons were not bouncing off the whole proton, they were bouncing off of some kind of subcomponents. So this revealed that protons were not solid lumps of positive charge. They had some kind of constituents, and we now call these constituents quarks, as has been mentioned by a couple of speakers today as well as yesterday. And if you're interested in learning more about particle and nuclear physics, I have this website here, particleadventure.org, which I would highly recommend. So the simplest model of the proton is 3 quarks, 2 up flavored quarks and 1 down flavored quark. Flavor is a property of subatomic particles that's related to the weak nuclear force and radioactive decays. I'm not going to be talking more about that here. But these quarks inside the proton are not completely free. They are bound by force carrier particles, which are called gluons. And gluons are, in fact, named after glue because they stick, they bind the quarks together inside the proton, also inside neutrons. There's also something known as C-quarks that are present inside the proton. These are short-lived quark-antiquark pairs that come out of quantum mechanical fluctuations, sort of blipping in and out of existence. And this little table here shows the 6 types of quarks, 6 flavors of quarks. So the up and down are the ones that are most relevant to the proton as well as the neutron. The next one that was discovered came as a surprise and was called strange. By the time the charm quark was discovered, people had predicted it, so they were feeling pretty happy with themselves. This wasn't a surprise, and they gave it a more positive name, let's say, charm. And then the heaviest 2 are known as top and bottom. So if you think about it, an atomic nucleus is made of protons and neutrons. Heavy elements have a lot of protons, and we know that the protons are all positively charged, and the neutrons are electrically neutral, so they're not canceling out that positive electric charge. The electromagnetic force should cause those protons to repel one another. And it is causing repulsion. However, the strong nuclear force is overcoming this repulsion. Protons and neutrons interact via the strong nuclear force carried by these gluons. And the strong nuclear force is much stronger than the electromagnetic force, about a factor of 100. And about 10 to the 38 times stronger than gravity, so thus the name. However, it has a very, very short range of about 10 to the minus 15 meters. So this is a key difference. We'll come back to that in a minute. First, let me talk about what kind of charge particles need to have to interact with the strong force. So the strong force acts on particles that carry what's known as color charge. So quarks carry color charge, plus gluons themselves carry color charge. So if this is in contrast to electromagnetism. So in electromagnetism, you can have electrically charged particles that attract or repel if they have opposite signs, like signs. And this repulsion or attraction is transmitted via exchange of photons, so the particle manifestation, particle form of electromagnetic waves. The photons themselves, though, do not carry electric charge. They are electrically neutral. So in the strong interaction, the gluons, which are the force carrier particles that are similar to the role of similar to the role of photons in electromagnetism, these gluons also carry charge, color charge in this case, strong force charge. So why is it called color? It's not something we can see. And it's called color because back in the 1970s, when people were first understanding the strong nuclear force, they saw that you needed 3 different charges to make a neutral particle. So if you compare this to electromagnetism, there are just 2 different types of charges, 2 different types of electric charges, which we call positive and negative, or plus and minus. When we combine those, they make an electrically neutral particle. For the strong force, they saw you needed 3 different charges to make a neutral particle. And they thought, well, what should we call them? And they thought of red, green, and blue light combining to make color neutral white light. And this is what led them to call this type of charge color. And so the theory, the quantum field theory describing the strong nuclear force is known as quantum chromodynamics, with this chromo referring to color charge. Note that quarks also carry fractional electric charge, which I think is probably something very deep that we have not understood yet. So I told you that the proton is made of 2 up quarks and a down quark. So up quarks actually carry positive 2/3 electric charge, and down quarks carry minus 1/3. So we have plus 2/3, plus 2/3, minus 1/3, gives us a total of 3/3, so plus 1 charge of the proton. The neutron instead is made of 2 down quarks and an up, so minus 1/3, minus 1/3, plus 2/3 gives us our electrically neutral neutron. So we actually never see quarks or gluons directly, and this is something very special about the strong force that gives us a lot of rich things to study, but also can complicate our lives and create some challenges as well. So the quarks and gluons are always confined to composite color neutral particles. They can either be in groups of 3 quarks, so in any instant, one of them would be red, 1 green, and 1 blue. The gluons are always being exchanged between those quarks, so you wouldn't say, oh, the down quark is the red quark. It's exchanging gluons, and the gluons actually can change since they carry color themselves. They can swap the color of a quark, but in any given instant, in say a proton or a neutron, one of those quarks is red, 1 green, and 1 blue. These are called baryons. Bary is a Greek root meaning heavy, the heavy particles made of quarks. They can also come in groups of 2, so a quark-antiquark pair, where in any given instant, the quark is carrying a color and the antiquark is carrying the corresponding anticolor. And these are called mesons, or middleweight particles. If you do try to pull 2 quarks apart, the energy between them increases until you produce a new quark-antiquark pair. This is through the famous equation E = mc². And I like to think of this as an elastic band. So if you are pulling apart an elastic band, then the farther you pull, the more force there is trying to pull you back. And so this is similar to the strong force. And as you're pulling farther, you are storing more and more potential energy in that elastic band. And at some point in the case of an elastic band, that energy stored, potential energy stored in the elastic band is gonna lead to the band breaking. So if you try to pull 2 quarks apart, then we have energy between them carried by gluons, or a gluon field. And at some point, that potential energy stored in the gluon field can create a new quark-antiquark pair. We're changing this potential energy into a new massive particles through E = mc². And then those the new quark and antiquark will go and bind with the original ones, forming the particles that then I can observe in my detector. So always these bound states with quarks inside them, never a free quark. So if you can't see individual quarks and gluons, how do you determine the proton structure? Well, in general, what we do is we do inelastic scattering. We shoot a high energy beam, for example, of electrons at the proton to break it up, and we try to understand what happens. The electron exchanges a photon with a quark because quarks carry electromagnetic charge. Remember that fractional electromagnetic charge, as well as color charge. Electrons do not carry color charge. And so it's the only way that an electron can interact with a quark is because the quarks do carry this fractional electromagnetic charge. So if we look at this diagram here, we have an electron beam coming from one direction, a proton beam coming from another. Here I've tried to just sort of schematically indicate the simplest picture of a proton with these 3 three quarks. So what we're going to do is we are going to break up this proton. So it's inelastic scattering with a proton. However, it's going to be elastic scattering with one of the quarks inside it. Because it's elastic scattering with one of the quarks inside it, we can actually use conservation of energy and momentum to infer information about the quark in the instant when it's scattered from within the proton, just by measuring what happened with the, like where the energy and angle of the scattered electron. So in general, if we're trying to measure what's inside the proton, I said the proton radius is about 0.8 times 10 to the minus 15 meters. We are going to need to go to very high energies to see such small, to probe such small distance scales. So if you think of the electromagnetic spectrum from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, these all correspond to different wavelengths and different energies. So we're increasing in energy going from left to right on this diagram, and the higher energy corresponds to smaller wavelengths. So if you think about using an optical microscope, something you might use in a biolab, you can use optical light, just regular light, to see microbes, protozoans, bacteria. And that's because the wavelengths of visible light, which are about 0.5 microns or 500 nanometers, about 400 to 700 nanometers, are small enough to resolve the features of those distance scales. If we want to study molecules, atoms, atomic nuclei, protons, and inside of protons, we're going to need to go to smaller wavelengths and therefore higher energies. So as was already mentioned in some talks yesterday, we can study the molecular structure of matter using ultraviolet light. Ultraviolet light has wavelengths of about 10 to 400 nanometers. So this corresponds to molecular distances. We want to study atomic structure. We got to go a little bit smaller and a little bit higher energy to X-rays, where the wavelengths are about 0.01 to 10 nanometers. Now I want to go to nuclei and protons. Remember we said that 1 in 8,000 bounced back in that original Rutherford scattering experiment. So we're rounding to 1 in 10,000. So if I want to study nuclei, I'm at a distance scale of 10,000 times smaller than studying an atom. If I want to study just a proton, I'm about 100,000 times smaller than an atom. So what we need to use are high energy particle accelerators to see inside them. And we'll be taking advantage of something called wave particle duality in quantum mechanics, which Professor Terry Odom actually mentioned in her talk yesterday. And in just one sentence summary, what the internal structure of the proton looks like depends on what energy scale you probe it. So that what energy scale is going to correspond to the distance scale. So if you are using low enough energies, long enough wavelengths, you're going to see basically the proton as a whole object. At intermediate, so slightly shorter wavelengths, slightly higher energies, you're going to be able to resolve this 3-quark structure of 2 up quarks and a down quark. And if you go to much higher energies, corresponding to much smaller wavelengths, you're going to be able to resolve this quark-anti-quark structure, these quark-anti-quark pairs fluctuating in and out of existence. So let me switch gears and talk about my experiment. So I work at the Phoenix experiment at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory on Long Island, New York. And I'm part of the LHC Beauty experiment at the Large Hadron Collider at CERN in Geneva, Switzerland. This facility goes across the French-Swiss border. You can just see the Geneva airport right near the Large Hadron Collider Beauty experiment. So the Relativistic Heavy Ion Collider is the only active collider in the United States. This is a satellite photo, and you can see this ring here. It's not the accelerator beam pipe. We don't have it out in the elements. This is the road that drive to the different buildings and facilities along the 2.6 mile, 3.8 kilometer circumference ring. This is New York City here, Manhattan, Brooklyn, Queens. It's about an hour and a half east of New York City. And here's an aerial view. By 2030, so relevant for any of you who might be interested in going into nuclear or particle physics, this will be transformed into a brand new facility known as the Electron Ion Collider. All of my work, because it requires these very large accelerator facilities, these are done at national and international scales, not at single universities. These aren't tabletop experiments. You have things that are multi-kilometer, multi-mile scales. And so even though we're 10 years before first data is expected from this brand new facility, the Electron Ion Collider, we already have 238 institutions from 32 different countries that have said they want to be involved and that are getting involved in the design work that's going on right now. So the Relativistic Heavy Ion Collider is actually a great place to work if you want to study protons in the strong force. We're studying several different systems, strong force systems, or protons, of course. This is my focus. And we have the ability to polarize, to control the spin direction of the proton beams there. This is a completely unique capability of this facility worldwide. We're also studying nuclei, and nuclear matter is so hot and dense that the quarks and gluons are briefly deconfined in what's known as a quark-gluon plasmon. We have two colliding beams going in opposite directions around the circle of ions, ranging from hydrogen, so protons, through uranium nuclei. And the facility is called the Relativistic Heavy Ion Collider because people were concerned that residents in the area would be very concerned if they had a nuclear collider, since people sometimes get nervous about nuclear physics. But these ions have all the electrons stripped off the atom. So we run a lot with gold beams, for example. This is gold plus 79, so it's not really a chemist's ion. The Relativistic Heavy Ion Collider has been running since the year 2000. It involves about 1,000 scientists coming from universities and laboratories around the world. The detectors are sort of building size, the scales of these. You can see a person working on the Phoenix detector while it's opened up for maintenance. Here's the beam line where one of the beams come in and the other as it passes out. They're going opposite directions through this single beam pipe. About 4 stories tall, 40 feet long, about 3,000 tons. We have different detector subsystems for measuring different kinds of produced particles or different information about them, such as electric charge, momentum, energy, or particle type. The Large Hadron Collider over in Geneva, near Geneva. Again, here's the airport. It's been running since 2010. It involves about 10,000 scientists total from around the globe collaborating on the 4 experiments. In terms of the data volume, the whole facility is collecting about 90 petabytes per year. So this is not something you study with pencil and paper. It's very computationally intensive. The Large Hadron Collider Beauty Experiment, I didn't tell you before, but the top and bottom flavor quarks, some people prefer the more poetic terms, truth and beauty. So my colleagues insist that this is not the LHC bottom experiment, it is the LHC beauty experiment. It's optimized to study the beauty quark. And here I show you just a visualization of a proton-proton collision. These are the particles or representations of the particles came out and what we measured in the different parts of the detector. This produced what's known as a Z boson. This decays to 2 muons, which are these 2 green tracks here. And then there's a quark jet, which sort of looks like these almost twisted black lines, or these different particles produced by a high energy quark. Remember, we said that you can't just see the quark by itself. If I have a really high energy scattered quark, it's going to produce many particles, and that's what this cluster of particles is here. The Large Hadron Collider is about 100 meters underground. So our detector is about 100 meters below the French countryside. We look at we record about 10 million proton-proton collisions per second. It also has beams of protons like the Relativistic Heavy Ion Collider, but we cannot control the polarization, the spin direction. And for a few weeks a year, this facility runs nuclear beams also. However, the collider runs at higher energies than the Relativistic Heavy Ion Collider because the focus is on searching for new particles rather than studying the proton and the strong nuclear force. And here you can see a photo from this past November. I got to go with my kids down to underground to the experimental hall. It's great to be able to go together. So before I have just one slide on my path, I just want to offer thanks to my group members, my postdoc, PhD students, undergrads, and visiting scholars, as well as acknowledge the the Department of Energy and National Science Foundation for funding my work. A few words on my path from high school. So for high school science and math, I took AP Physics B. My high school didn't offer a calculus-based AP Physics. I took AP Bio, AP Calc BC. We had both AP Calc AB and BC, but my high school at the time didn't have AP Chem or any other AP Science or math courses. I was in the math club. I was a mathlete from 7th grade on. So I was definitely interested and involved in math already in middle school and high school. I went on to college. I double majored in physics and music. I now get to teach a course on the physics of music at the University of Michigan, which has been really nice to draw on some of my music background in my job as a professor of physics. I didn't get involved in research until the summer after my freshman year in college. So I didn't have any opportunities like that in high school. So if you're not in a position to have such opportunities, you really shouldn't worry about it, but definitely try to find ways to get involved in college. I worked in an experimental nuclear physics lab on campus. So this really, it seemed interesting to me, and the professor had an opening. So this was how I got involved in experimental nuclear physics. That first research advisor suggested I apply to summer programs at national labs. So after sophomore year of college, I ended up getting an internship working at the Relativistic Heavy Ion Collider at Brookhaven National Lab more than 20 years ago now. And that was what sort of launched me into this field, although I did a few different things in nuclear and particle physics for a few years in between before coming back to it. And there is a program, it's got a different name now than when I did it, but the Department of Energy's Science Undergraduate Laboratory Internship Program open to undergraduate, to college students interested in science to do summer and also semester programs at, I think, 17 different national labs in the United States. From there, I continued in experimental high energy nuclear and particle physics, doing other research projects during college, and then pursuing a PhD in physics. So just a summary, even though protons are a fundamental building block of everyday matter, we still have lots to learn about the complex behavior of the quarks and gluons inside them. High energy particle accelerators are tools that allow us to probe the structure of very tiny objects. So in my case, I'm probing distance scales less than 10 to the minus 15 meters. And there's a community of a few thousand people around the world that's working to unravel the mysteries of the proton and the strong nuclear force that holds it together. Thank you.
Thank you so much, Dr. Adala. Does anyone have any questions for her before we start physics competition? Okay, let me check out the YouTube. Oh,
I can see the chat. Did you do a performance education major in music? So it was actually a general music degree. So my university had a music school, but it was a graduate music school. So for undergraduate degrees, it wasn't a Bachelor of Musical Arts. So it wasn't a performance degree. So I had performance credits, but it was a general music degree.
I have one question. Which one, or what has been your favorite research project out of all of the ones that you've done?
That's a good question. Probably, I guess it's even hard to define a project. I mean, I think I've really enjoyed working with the Phoenix experiment. I've actually, these are long-term experiments. I've been on it for 19 years now. And I think what was really exciting about that in particular was discovering for the first time in 2014 that the gluon spins contribute to the total spin of the proton. That had been there's still aspects of proton polarization and proton spin that remain a puzzle, but that was a big announcement in 2014 that the gluons are contributing. So that was definitely a highlight of my time working with the Phoenix experiment at the Relativistic Heavy Ion Collider. Another thing is, it's not really a project, but in general, one of the aspects I like about working in high energy nuclear and particle physics at these international facilities is really the international aspect, the international cooperation aspect, the fact that I get to work on a daily basis with colleagues from all over the world, which when the pandemic started, emailing my colleagues in Wuhan to ask them how they were doing, just made it feel really different than if I hadn't been working with people from that particular city even. And there have been a lot of things over the past 20 years that have come up with world events where it's been interesting and really eye-opening to be able to talk directly with people who are living and working in these different regions of the world. My data, I see hang on, let me scroll up in the questions. how do the detection instruments work? Do they actually view the particles in their paths, or do they hypothesize like guess them? So different types of detectors get different information about the particles. So for example, charged particles can ionize a gas. Like if I have a charged particle passing through regular gas, it'll knock off some electrons, and then we can collect those electrons and we say, aha, a particle passed right near here, because I see that some electrons got knocked off. We can also, charged particles also bend in a moving charged particles bend in a magnetic field, and the radius of curvature in that magnetic field gives us information on their momentum. So they view the particles, but not in the sense of with our eyes. We're collecting, charge, electrons knocked off the atoms. So there's this really clear signature that we collected those ionization electrons. But you're not seeing it with your eyes. You're then reading charge out of an instrument to say we collected some electrons. Another question is, what is your day-to-day work life like? So I spend a lot of time, I'm a university professor, so some of my time is teaching undergraduate and graduate courses. I spend a lot of time with my research group members, mentoring graduate students on different research projects and undergraduates as well. I've had a few high school students over the years that have worked on some hands-on detector development projects in my laboratory. And so I've had a neutron detector development project for like a new way of detecting neutrons using liquid argon, for example, and that's on campus at the University of Michigan, even though my accelerator facilities are all off campus. And I spend time going to take shift for maybe a week or so at a time, or going to collaboration meetings and going to different conferences. My PhD students will go for months or years at a time to the experiment, typically. Another question is, how well is it to get a grant these days, better or improving? So I guess I've been mostly fortunate, at least, in being able to get financial support to do my research. So most of the financial support I get directly is to pay the salaries of the researchers working in my group, and to travel to the experimental facilities, because we need to travel to go to the experiments. And then to travel to talk about the work at scientific conferences around the world. So I think it's been okay for me. It's actually really exciting that the Electron Ion Collider was just announced as a new project approved by the government about 6 months ago.
Thank you so much, Dr. Aidala. We're going to start the physics competition soon. So I think that was the last question. But I hope everyone really enjoyed the physics talks. I know I really did, even though, I'm like more the biology side. Yeah, all of the physics speakers were so awesome. So thank you all, and thank you, Dr. Aidala. Now we're going to split everyone in breakout rooms for the physics competition. So if you're not competing, you can just leave the breakout room you get assigned to, or just stay in the main session, or just leave. After the physics comp, just so you guys know, we'll have a biochemistry demonstration. So yeah, all right. And ready.
Hi, Dr. Kuehler. We're just running a little late, so Diana told me to tell you that, just in case. We're running late. We're in the physics competition right now, so I just wanted to let you know. But welcome. Thank you so much for coming with us today.
No worries. Just let me know. I need to warm a couple of things before we start. So if you give me 3 minutes sign, I will have everything ready.
Yeah, it will probably be like that or about like 5 minutes. So in general, like you have a little time to prepare if you need it.
So you think we're going to be starting in 5 minutes?
Probably. I'll double check just in case. Give me
Yeah, don't worry. Let's do this. When you are finishing in the other side and just in that point, give me a heads up and I will warm my things.
Okay, sounds good.
Yeah. And just one little thing.
Yes?
My last name is pronounced Cuellar.
Cuellar? Okay,
Yes.
got you.
Thank you.
Yeah, of course, of course. Catherine, did we finish the competition? Did Diana finish hers or no?
I'm not sure, but guys, we're just waiting right now for the other one to finish. So yeah, so don't leave.
Yeah, okay. I'll ask her. regardless of if the competition is ending, we're going to start in like in 1 minute, if that's okay with you. All right, we're just going to start, even though the other competition isn't really over. So Dr. Swalar attended college at the National University of Columbia, where she became interested in crops biology. She moved to Mexico for graduate studies at UNAM's Biotechnology Institute, where she obtained master's and PhD degrees in 2001 and 2008 in 2008. In grad school, she focused her attention on cell wall proteins, and carbon metabolism. In 2009, she was also accepted in the postdoctoral program at UC Davis, where she continued her studying in plant adaptation to stress and entered the world of genomics and large data set analysis. Please give a warm welcome to Dr. Swalar.
Thank you, Sophie. I'm gonna share my screen and I'm gonna show you a couple of things. So, as Sophie said, my name is Sonia Cuellar Ortiz. I work at Smile Science Workshop, where I am a mentor for teenagers that wants to learn science and do some research in science. Today we're going to talk about shape, function, and proteins and how those things are related. I want to call your attention. I have here in the presentation this white screen. If you have the opportunity, you could use that space to pin the screen in which I'm being shown and increase the size of that screen so you can see me a little bit bigger than in the small squares, more screens of the divided screen. That is because I'll be showing you the presentation, but I also want to see, I'll be doing some things with my hands and I want you to be able to see them. So thanks again for inviting me. And I'm gonna start by setting an experiment. We are gonna talk about the experiment over the time of this talk, but I want to begin by setting the experiment because it will take a little bit of time for the things to happen. So I want to be sure that at the end, we can observe the results. So for doing that, I have here 2 cups that I hope you can see. I labeled them. This is cow milk and this is almond milk. I have half a cup of each one here in my cups and it's warm. It should be warm enough that, let me remove this, it should be warm enough that when I touch it, I feel it warm, but it's not hot. I'm not burned. I can touch it. And what I'm gonna do is add to each one of those cups, I'm gonna add half a tablet of rennet. This is a substance that is used for making cheese. It used to be extracted from the guts of calves, but now is prepared using transformed bacteria. So we don't need to feel bad about the little cows when we use rennet, because they are not involved in this anymore. We use bacteria for that. So I have here half a pill that I already crushed to powder, and I'm gonna add it to the cow milk. And I'm gonna crush the other half of the pill to add it to the almond milk. Let me see. Have it here, so I'm just gonna crush it. And the only reason I'm doing this is to make it easy to mix with the liquid. I'm gonna use those squares to mix very well. And I will leave it aside to do its work while we talk a little bit about this subject. We will go back to this, but it takes some time. So we will keep talking for a minute, and then we'll back to observe what had happened there. Now, I want to talk about what we just did. What we use is this rennet I was mentioning. It's a commercial product, and is actually a protein. What is packed there in those tablets is actually a protein that it used to be called a renin. And this is the three-dimensional representation of that protein. Proteins, as you know, or most of you, I think, may know, are the product of putting together, aligning together many different amino acids. So you have a sequence of amino acids that I have represented here. In this case, are the first 30-something amino acids to the renin protein. The protein actually has 281 amino acids, so they didn't fit here, but this is just the first, and this will be the sequence of the different amino acids. So methionine, oh, I lost my cursor, methionine, aspartic, guanine, cytosine, leucine, valine, valine, leucine, leucine, aniline, valine, phenylalanine, so on. That's the same that I have, a representation of that. It will be what I have here in this pipe cleaner with beads. And so, as you can see in the pipe cleaner and also in the sequence of the protein, we have different amino acids repeat in different order. And that order is what we call the primary sequence of the protein. And it's very important because it is dictated from the genetic information. It comes from the information that is stored in DNA. And it determines the function and the structure of the protein. And the way that works is those amino acids have different properties. One very important of the different properties that they have is they may be what we call hydrophilic or hydrophobic. Some of you may know hydrophilic means it likes water. Hydrophobic means it doesn't like water. So here in the sequence of the renin protein, I have highlighted the ones that are hydrophobic in purple, and in white, the ones are more hydrophilic. For my pipe cleaner model here, I will say that the orange beads and the pink beads are hydrophobic. And the reason why that's important is because all proteins are in the context of a cell that is an aqueous environment. There is a lot of water around there. So the hydrophobic residues don't want to be close water. They rather be close together. So they are gonna try to be close together. So in my model protein, pink will try to be with other pink or with orange. And sometimes the tension of the protein don't allow them to be that close together, but they still will try. And that trying, that property of being hydrophobic and the other hydrophilic, in combination with other properties of the amino acids, but that very importantly will determine the three-dimensional shape of the protein. And that three-dimensional shape of the protein that is given by the interaction between hydrophilic and hydrophobic amino acids is very important because the function of the protein depends on that three-dimensional shape. I'm gonna stop sharing this screen because I'm gonna start sharing a different screen here in which I'm gonna show you the three-dimensional structure of the same protein we're talking about. We call it a chymosin. That's a more technical name. Renin was the name that was used at the beginning of this 20th century when it was described, but this is chymosin. This is the enzyme I'm talking about, and this is the three-dimensional representation of that protein here. This is a representation that we like a lot because it's showing different parts of the protein, parts that we call lamins and ribbons and helix and coils, and all of that have a meaning. I'm not going to go into those details. I want to show you, for example, that here I have highlighted in white. I hope you can see here this area that is white. That is what we call the active site of the enzyme. This protein is actually not just a protein, it's an enzyme, which means that it has a chemical function. It does something, it transforms something. And it does it in this active site that I have highlighted here in white. As you see, is kind of in the internal part of the enzyme, but it has this groove, the substrate can go into and reach that area. All the protein is important for the function, but the actual chemical reaction happens here. This is, by the way, I'm using here the software that it was developed by the University of California, San Francisco. It's a free software, it's called Chimera. And I'm using a database that is called Protein Database, PDB, and it's a free database. You can access there all the proteins that had been, their three-dimensional structure has been elucidated. The three-dimensional structure is there. I want to show you other things that we can do when working with this visualization of the three-dimensional structure. This is a different visualization. It's not now it's showing the different atoms, not the ribbons and arrows, but it's showing the atoms. And you can see that is the enzyme there, and it has this kind of crescent moon shape. This is the groove that the substrate needs to get into. I hope you can see there in white inside, in the middle of the protein, is the active site. And I can use this to also see the, oh, sorry. I should have, where is it? I need to select this one because I can ask the software to show me now the surface of the protein, not the atoms, but how the surface of the protein will look. And this will be the surface of the protein. Those atoms that you see there kind of outside of the surface of the proteins are actually molecules of water that are necessary for the protein to configure it in the proper child. And I could also use this to see in the surface where are located the amino acids that are more hydrophobic and more hydrophilic. In this representation, in blue, the more hydrophilic residues, the more hydrophilic amino acids, and in red, the more hydrophobic. So as you see the surface of the protein, this all will be, the black here will be all water, it's inside of a cell or an aqueous environment at least. And so that means the surface of the protein exposes a lot of hydrophobic residues. There is some hydrophilic there that are kept in place by the structure of the protein, but most of the surface of the protein that is interacting with water is actually hydrophilic. And that is very important because that will keep the shape of the protein, will keep the groove necessary for the substrate to get in, and the active site that is here inside. Now, why is that related to all those things that I've been telling you about milk? Why I'm talking about milk? Well, I'm talking about milk because the chymosin is this enzyme that I've been showing you. And what this enzyme does is an enzyme that cuts casein. As you may remember, proteins are in many different kinds. Proteins are the ones that form our hair or nails or muscles and skin. All of that is proteins, but there is also a specific and very important group of proteins that are called enzymes and are proteins that have a chemical function. They do something. In this case of the chymosin, what chymosin does is cuts casein. And casein is important in this subject because casein is the most abundant protein in milk. I don't have my cardboard of milk here because it's very warm today. I don't want it to spoil, but I put a little milk in this bottle just to be able to show it to you. I know you all know milk, but just to remind you, milk is this white liquid that is very nutritious. And is nutritious because it's rich in protein, but it's also rich in other ions that we need, like calcium and phosphate. And the thing with this milk is very, very stable. I can shake it and it will still be milk. I can centrifuge it and it will still be milk. We can boil it and it will be milk. We can freeze it and if we let it go back to room temperature, it will be milk. We can actually dehydrate it, remove all the water, and it will become milk powder. And when you rehydrate it, add water back, that milk powder will form this white liquid that is, it has all the casein on it. Is well, all the other components of milk too, but importantly the casein, that is what it gives the white color to the liquid. Milk is a very, very stable substance. And that's very important from the biological point of view because we mammals use milk to feed our babies, or human babies, or cow babies, or any other mammal. Offspring is fed in this white liquid, and it needs to be very stable so we can carry it with us and have it available for feeding babies. So all that is very good. And I think I'm not saying nothing that you already don't know. You know milk, you know that it's stable. You may not know that we can dehydrate it and form powder and then rehydrate it later, but you know milk. Milk is a very stable substance. The thing with that is casein is actually a very hydrophobic protein. When we have the sequence and we analyze the sequence of this protein, is actually very hydrophobic. You may remember from the slide I showed you before, oh no, that was the kinosine. But casein is actually very, very rich in hydrophobic residues, a lot more than many other proteins that we normally find in liquid form. So that creates question. How is possible that this very hydrophobic protein is actually in water all the time and is very stable there in water? My jar is dripping. So how that happened? And that's a question that we have for a long time, and just in recent decades start to clearly answer. Actually, we don't have yet a three-dimensional structure for a casein. In general, crystallizing hydrophobic proteins is not easy, and you require a crystal of the protein to be able to use X-ray diffraction and dilucidate the three-dimensional structure. But we know a lot of things. Even though we don't have the three-dimensional structure of casein, we know a lot of things. We know, for example, and that is an explanation, that casein in milk is actually in these micelles. This is an actually microscopy picture. The diameter of this micelle is around 120 micrometers. And these structures are what is soluble in water. Those micelles are represented here in this diagram, and they are composed like this. This is the micelle, in which, as you see, is a very complex structure that has molecules of casein of two different types. The K-rich casein that is presented here, that is actually a little bit more soluble because it's in contact with some ions, and that is surrounding the other casein molecules. And all of them are kept together by interaction with calcium phosphate. So this partially explains why milk is so nutritious. It's carrying calcium, it's carrying phosphate, it's carrying the casein. And this structure explains how it's possible that this very hydrophobic molecule is actually very stable in water, because those micelles themselves, they are just exposing the hydrophilic part. So the micelle itself is hydrophilic. The components of the micelle are not necessarily as hydrophilic. And that is very important in relation to our experiment. I want to show you here what happened to our experiment. Let me see, how much time do we have? Yes. So this is the cow milk, and this is the almond milk. As you can see, almond milk is pretty much the same that it was at the beginning. The cow milk, I hope you can see, is not running. It's not running because it has changed. I'm gonna disturb this a little bit to show you what is happening is the protein has coagulated or is in the process of coagulating and is separating from the liquid. I actually have here another cup in which I did exactly the same that I did with this one just an hour ago. And so it's just a process a little bit more advanced. And I wanted to show you this because I hope you can see that the solids are now separated from the liquids. This is the process that we use when we are gonna make cheese. We separate the solids in the milk from the liquids. Let me see, I hope you're seeing it there. And this is because now the chemosine have disrupted the molecules, the micelles of casein. The micelles of casein are not anymore in their hydrophilic form. So now the casein is separating from the liquid. I hope you can see the liquid there. If not, at least I hope you absolutely can see that this is not a liquid anymore, as the almond milk is still a liquid. This is moving like a liquid. This is not moving like a liquid. This is the one I prepared an hour ago. This is the one I just prepared with you. So what is happening here? Something is changing the structure of the proteins in the milk and is actually draining the chemosine, because that is what we add. And what the chemosine actually does is it cuts the molecule of casein in two parts actually. So this is, of course, is a schematic representation. Things don't really look like that. But if you cut the casein molecules, now they don't have the three-dimensional structure that they need, and they start exhibiting more of the hydrophobic residues. That means that they want to come together, and then they coagulate. They are not anymore able to form this structure that will easily and happily interact with water. They form these structures, or many different variations, this is irregular, in which a lot of hydrophobic areas are being exhibited here, and those means that the protein separates from the liquid. What is happening there, if I go back to my model with the pipe cleaner, is remember that the rules for the model is the pink and orange are hydrophobic, so they want to be together. And because of that, they are keeping this three-dimensional structure of the protein. Of course, that is not the only force that is there keeping the three-dimensional structure of the proteins. There is other things related with the other amino acids, but that is a very important component. So if I come here and I cut, and I'm gonna cut here whatever place, but chemosine actually cuts in a very specific place. Now, the two resulting peptides cannot keep this three-dimensional structure. They still have the same hydrophobic residues and they are attracting each other, but the structure is not stable anymore. That is what chemosine does. And because the structure is not stable anymore, now the protein is exhibiting a lot of hydrophobic residues that before were protected inside the protein. And that means the protein is not able anymore to happily interact with the water and be this liquid there and start separating from the liquid and forming the solids. If I allow this process to keep going and I use cheesecloth, for example, for filtering this may later become in cheese and I will separate what is called the whey. It's the liquid of the milk. So here, what we have done is a home experiment in which I hope you can see that there is an enzyme that is working. That was the enzyme that comes in the renin, the chemiosin, and that enzyme is working to change the three-dimensional structure of other protein, the casein, and because it changed the three-dimensional structure, it changed its properties and its function. Its ability to work as milk now is becoming curds that can later be cheese if you want. That is not happening in almond milk. And as you saw, I put the same renin, both were the same boiling temperature, and it's not happening. I want you to stop for a second and think why the renin will affect the cow milk, but will not affect the almond milk. You may have different hypotheses, and I'm sure all of them are very interesting, and we may be able to develop even homemade experiments to test your hypothesis. I can tell you that is related to the fact that almond milk and cow milk are different. They are different in the source, but they are also different in the components. There is no casein in almond milk. There is other proteins, of course. It's not that there's lacking of proteins. It has proteins and it has fats and sugar, the same like milk, but not the same protein. And enzymes, when they work, they are in most of the cases very specific. In the case of chemiosin, chemiosin can cut casein, and it doesn't cut whatever, it cuts in a specific place. And that is why it has this effect over the milk, but it doesn't have any similar effect in almond milk. You can coagulate other proteins different than casein. Actually, many proteins will coagulate when you heat them, when you boil them. A lot of the things that we do when we are cooking is coagulating proteins that are in our food. And that is just the effect of the temperature. But casein and almond milk, actually, the proteins in almond milk actually are not that susceptible to coagulation by temperature. However, they are susceptible to coagulation by other process. If you feel like it, if you want, this is a totally home experiment. You can at home test the effect of the temperature in this experiment. You could test the effect of the pH by adding baking powder or lemon juice or vinegar to your experiment and see what happened. That I'm sure if you are interested in this kind of things may lead to interesting things. This is the kind of things that we do in those days in small science home experiments because we are working in Zoom. But when we are able to go to the lab, there in the lab, of course, we can use this same kind of experiments, but we also can do a lot of things, other things that are a little bit more sophisticated. We can use spectrometry for measuring the activity of enzymes, chemiosin, but other enzymes too. We can extract and enrich, purify proteins. Here in the picture, I'm showing you the extraction and purification of green fluorescent protein that happens to be very nice to see, but we can use the same kind of techniques for extracting and purifying different proteins. And well, we can extract other substance DNAs and nucleic acids and other things that we do in the lab. We actually have a lot of fun while we do that kind of things. In those days, we are having that fun in Zoom sessions but we also can do it in the lab when we're allowed to go to the lab. I think I am close to my time.
Yes.
So I want to thank you all. Thanks for inviting me. And if there is any questions or comments, I would like to take them.
Yes. So please be brief with your questions because we're running a little late and the next speaker is already here. So if you have any questions, I would ask it right now. Okay, it doesn't seem like anyone's asking. So thank you, Mrs. Ortiz.
Thank you for inviting me.
Yes.
Bye.
Okay.
Thank you. So we'll get started on our STEM World Computer Science panel. So our first amazing guest is Dr. Anshul Khanduje, who is a professor of genetics and computer science at Stanford University. Dr. Khanduje completed his PhD in computer science from Columbia University. He has led analysis efforts for two of the largest functional genomics consortia, which are the Encyclopedia of DNA Elements and the Roadmap Epigenomics Project. The Khanduje Lab develops statistical and machine learning methods to analyze large-scale genomic data. I am very excited to hear about his research and use of machine learning and AI to analyze genomes. Without further ado, please welcome Dr. Khanduje.
Hello. Can you confirm that you can hear me?
Yes, we can hear you.
Excellent. Okay. So thanks very much for the invitation. I hope everyone's having a good weekend. So my lab's at Stanford, and we are part of the genetics and computer science departments. I'm going to talk to you today about how we use machine learning methods, particularly deep learning, to try to understand the control system of the human genome. So my lab works on the interface of biology and computer science, and it's a very exciting and interesting area. And I'll show you how we can use the combination of these technologies to understand basic biology, as well as to understand the genetic basis of diseases. All right, so jumping right in, I want to start off with what the human genome is. The genome is a long DNA biopolymer. It's made up of four units: adenine, cytosine, guanine, and thymine, ACGT. Believe it or not, it was only in 2003 that we as humanity actually obtained the first draft reference sequence of the human genome. By that, I mean the entire sequence of the genome, how long it is, what all the letters are. And we realized that the genome is actually, the human genome is about 3 billion nucleotides long. What's very interesting is, this was, of course, the Human Genome Project that almost spent over a decade trying to figure out the draft sequence. And it effectively cost about $3 billion. So the effective cost of sequencing one reference human genome, so this wasn't the genome of one particular individual, it was sort of a representative genome for all of mankind or humanity, that cost $3 billion for 3 billion nucleotides, right? So that's about $1 per nucleotide. Now, if you fast forward to today, there's been an absolute revolution in high throughput DNA sequencing technology. And in 2003, we started off with one sort of average reference genome for all of humanity. And now we can sequence individual genomes for exponentially lower costs. So today, you can sequence a genome in about a week, and it costs about less than $1,000. Also, the sequencing machines. So this shows like the super exponential growth in the number of genomes being sequenced since 2003. We are expecting by 2025 to have pretty much sequenced, already several countries have sequenced their entire populations. I expect that anyone who wants to get their genome sequenced voluntarily would be able to do it. It would be a routine part of similar to how you get a birth certificate, you would potentially get a human genome by the year 2025. What's also been really interesting is the devices used for genome sequencing, which are often called high throughput sequencers. They start off being these giant apparatuses that filled entire football fields. And now they reduced over the years. This is 2008, this is 2009, this is 2012. These are like sewing machine models. They're pretty tiny. They can fit on your desk. And the latest is this Oxford Nanopore sequencer. It fits in your hand. And if you look at it, it kind of looks like a USB device, right? You see this thing right there? That's because it is a USB device. It actually just plugs into your computer. You can swipe some specimen and start streaming DNA sequences right into your laptop. So this has really revolutionized what you can do with sequencing technology in the wild. So imagine there's an outbreak. As you know, we're living through a pandemic. There have been previous epidemics and pandemics in very remote regions. For example, the Ebola epidemic that happened. Imagine having to go and set up an entire lab there to just sequence, viral genomes or human genomes. It's much, much easier now because you're able to do it with these pretty small devices, which are very high throughput. So there's been an absolute revolution in terms of the cost, in terms of the throughput, and in terms of the size of the technologies. And I'm going to run you through how one of the most popular technologies works. This is called sequencing by synthesis. And the way it basically works is, DNA is a double-stranded polymer, right? So it has two strands, and they are complementary, which means the A's pair with the T's and the C's pair with the G's. So if you take one of the strands and you strip the other strand off, right? And you have a bunch of free-floating nucleotides, these A, C's, G's, and T's. Let's say the different colors. If I take this stripped down single-stranded template of DNA, and I take a bunch of free-floating nucleotides and I add an enzyme called DNA polymerase, this enzyme will actually complete the complementary strand, okay? One nucleotide at a time. And what's really interesting is if I'm able to add different fluorophores to these nucleotides, so let's say my C's emitted a blue color, and my G's emitted a yellow, and my T's emitted a red, and my A's emitted a green, once they complemented with another strand, you can imagine that as the DNA polymerase is actually completing the synthesis of the strand, you will start seeing colored light, right? You will see blue, and then blue, and then blue, and then red, and then yellow. And so if you follow the sequence of colors, as DNA polymerase is sequencing this single-stranded template, you could potentially read out the sequence, right? And that's the trick that sequencing by synthesis uses, okay? Now, of course, you don't want to do this one molecule at a time. You want to do this in an extremely high throughput fashion. And so the basic trick is you take the DNA from a person's genome, an organism's genome from the cell. You fragment it into millions and millions of little pieces. This is referred to as shotgunning the genome. And then you take these little fragments and you immobilize them on a template, on a surface. Okay, so each of these form templates. So you have millions of these templates on the surface. And then what you do is you add DNA polymerase with these colored nucleotides. And the main difference is that the DNA polymerase is synchronously completing the templates across the entire slide. Okay, so millions of different templates are all being simultaneously completed in a synchronous fashion. So in the first cycle of sequencing, the polymerase will add an A at this template and a G at this template, and you have a microscope sitting on top that's visualizing the template. And what it basically sees is something like this. So imagine you just had two templates. You typically have millions, but just imagine you have two. At each cycle of sequencing, if you look at those two pixels through the microscope, you would see, through the camera, sorry, you would see different colors, right? So in cycle one, you see yellow and green, then you see red, and then blue and yellow, and so forth. And so then you get a sequence of these colors at each spot, at each template. And once the sequencing is done, let's say there are 100 cycles, you get a set of 100 colors for every spot, a sequence of 100 colors, and that basically gives you the sequence, okay? So that's the trick behind high throughput sequencing. You take these billions of DNA molecules, you immobilize them on a surface, you synchronously sequence them with fluorophore nucleotides, each of them having different colors, and a camera reads off each pixel at a time, basically decoding and telling you what the sequence is. This is really cool. It's really fast and really high throughput and very accurate. And what you can do is start using this to basically just sequence individual genomes. So now no more, let's not talk about the reference human genome for all of mankind or humanity. Let's talk about individual specific genomes, right? So your genome and my genome. And why this matters is that all of us have 2 copies of each chromosome. So we have 22 pairs of autosomes and then 2 sex chromosomes typically. And so what happens is each of us has two copies of the genome, as shown right here. And all of us differ at specific positions. So for example, this individual here has a T at this position and an A at this position in the 2 copies, okay? Another individual might have an A and an A, another individual might have a T and a T at this position, okay? And so these are called genetic variants. These are positions at which our genomes actually differ. This is what actually makes us different from each other. Identical twins would have exactly the same genomes. That's the only case where 2 individuals have exactly the same 2 copies of each nucleotide. But what we can do is now start sequencing individuals and sequencing their diploid genomes, these pairs of genomes, and trying to identify all the positions in the genome where we see genetic variation between individuals. And most of this variation is not harmful. It is in fact very good for us. It creates the diversity that we see. And by sequencing a healthy individuals, we can start doing really interesting things like ancestry inference, tracing back our history, very interesting things just to study basic biology, genetic variation, and so forth. Now, another interesting application for disease is you can use the same technology to sequence not just healthy individuals. So here we are showing a collection of healthy individuals, often referred to as controls, but you can also sequence a bunch of individuals who have a specific disease, okay? And these are called cases. And so now what you'll see is that specific positions in the genome, the controls have particular patterns of nucleotides, and the cases have other patterns of nucleotides. And by comparing at each position in the genome, you can do a statistical test. Basically, you just enumerate how many individuals have one particular pattern, how many individuals have the other pattern, and the third pattern, right? And if the healthy individuals have a very specific enrichment of one pattern with respect to the diseased individuals, then that particular genomic locus, that variant, has likely something to do with the disease. It's basically genetically associated with the disease, right? And so this is a very powerful way of mapping genetic variants that have some association with the disease, which may cause predispositions to disease, okay? And here's one example for Alzheimer's disease, which, as you know, is a neurodegenerative disorder. This is referred to as a genome-wide association study. It's basically this, but you perform this kind of test, this kind of table for every genetic variant in the genome, okay? And so far, we've found millions of genetic variants in the genome by sequencing human populations. And so here what you're seeing is the output analysis of a genome-wide association study for Alzheimer's disease. On the x-axis is the whole genome, okay, 3 billion positions. On the y-axis is the statistical significance of association. This just tells you basically how strongly associated each genetic variant is with the disease, in this case, Alzheimer's. Each dot on this plot is a genetic variant. And so you see most of the genetic variants have very low association, right? So they're not having anything to do with the disease, but then a bunch of them really skyrocket right up here. And this kind of plot is referred to as a Manhattan plot because, as you can see, it kind of looks like the skyline of Manhattan, right? You have these skyscrapers popping out of thin air. And these are the genetic variants that are likely predisposing individuals to Alzheimer's disease, okay? So it's a very powerful way to map. You can take any disease of interest, any trait. It doesn't have to be a disease. It could be like hair color, eye color. You can do the same kind of studies. You sequence a bunch of individuals which have one property of the trait versus another, or one disease status versus the other, and you perform these association tests, and you can map these genetic variants associated with the disease. So this is really powerful because now we've been able to map thousands of genetic variants that associate with all kinds of diseases, complex diseases, type 2 diabetes, cancers, Alzheimer's, you name it. The issue is, once we've identified these variants or these loci that do interesting things, we don't know what they actually end up doing. Like, okay, we found an A and a C that associate with Alzheimer's, but how is it predisposing you, right? So that's where we come in. My lab really focuses on decoding genome function. And by that, what we mean is if you take a particular letter in the genome or a particular word in the genome, our goal is to try to figure out what it actually does. Like what is its function? What is it encoding? Okay, that's called functional genomics. And it's very complicated because when you're interpreting the genome, you remember that the human body humans are multicellular organisms. So we have a whole host of tissues and cell types within those tissues in the body, tens of thousands of different cell types. And what's amazing is for me, for example, if you take any single individual, all the cells in that individual's body have the exact same genome sequence, okay? Even though they have entirely different functions and morphology, they have the exact same sequence. So the big question is, how does the same sequence manifest into all this beautiful diversity of cell types and function? And so when you're interpreting the genome, you can't just interpret it in a vacuum. You have to interpret the genome in the context of which cell type or tissue you're interested in. So for example, if you're thinking about Alzheimer's disease, it is a disease of the brain, and that means how to interpret the genome in the context of brain cell types, okay? So this complicates the whole picture. So to understand the function of the genome, we first have to start dissecting genome biology a little bit, okay? So let's take the cell, let's get into the nucleus, let's unwind some DNA, and let's start looking at what are the different kinds of functional elements in the genome. So many of you have heard of, I'm sure you've heard of genes. The human genome has about 20,000 genes that encode for proteins. So you can read off the sequence of the gene, and it literally is a code for a protein. It produces, you read off the DNA sequence, and it exactly translates into a corresponding sequence of amino acids that form a protein. So there are 20 to 25,000 protein coding genes in the genome. But the protein coding sections of the genes only account for 1.5% of the 3 billion nucleotides. Okay, so all the proteins in the genome, in the cell, are produced from 25,000 genes that occupy the protein coding parts of it, occupy only 1.5% of the 3 billion nucleotides. So what does the rest of the genome do? And how are these genes actually controlled? The secret to having different cell types and tissues and function is to express different sets of genes in different cell types. So you can have 25,000 things, but you can combine them in many, many, many different configurations, thereby giving rise to very, very distinct cell types and tissues. But now if I want to activate gene A only in brain and not activate it in liver, there needs to be some control system, right? Telling the cell, how is this gene active in cell type A, or activate it now, don't activate it now. And so where is this control system? What's really cool is the control system is also in fact encoded in the genome. There are a bunch of genomic elements called regulatory control elements. These are little sequences of DNA, and they are the on-off switches. They tell the genes to turn on and off, or they contain sequences that tell genes to turn on and off. And if you look at the anatomy of any of one of these control elements, what actually happens is they are bound by a variety of different proteins. So a bunch of these proteins that are produced by genes actually have regulatory function. So they go back and bind these control elements. And when they bind these elements, they basically activate genes or repress genes, okay? So the whole language of these proteins, these regulatory proteins that bind DNA, and a whole other collection of biochemical flags. These are like methylations and acetylations, all kinds of biochemical flags that can be added and removed on the DNA. And that makes the DNA dynamic. So even though the DNA sequence is static across all the cells in the body and across the entire lifespan of an organism, the way the genome is expressed and controlled is dynamic. And the way that happens is through the dynamic binding or unbinding of collections of proteins to these regulatory elements, and the addition and removal of these various kinds of biochemical marks. And what's really cool is we can use high throughput sequencing technology that I showed you before to profile all of these different biochemical events across the entire genome. So we can perform experiments that give us these beautiful digital readouts across the entire genome. At each nucleotide in the genome, we get a readout of whether a particular protein is bound. For example, this black protein right here, is there a biochemical modification or not? And so we see this really beautiful painting of the genome sequence. And this painting, this sort of multi-dimensional painting of the genome by all of these different proteins and biochemical marks is cell type specific. Each cell type has a different painting of the genome, okay? And that really represents its dynamic instantiation. So if I have all of these different paintings of the genome in different cell types and tissues, I need to map these. And so what the National Institute of Health did is they, just as they funded this massive Human Genome Project, which was a beautiful, large collaborative effort across many different countries and universities and industry and academia, same way the NIH funded two other large consortia, one of which is called ENCODE, the other is called the Roadmap Epigenomics Project. These started off immediately after the Human Genome Project and recently have completed major portions of their goals. And what they've ended up doing is these projects are profiling these hundreds of different molecular markers, these paintings, as I showed you, right? Different proteins binding DNA, different biochemical modifications, hundreds and thousands of these across the entire genome in hundreds of different cell types and tissues, okay? So we end up with this amazing teracube of information, digital readouts, which tell us which molecular flags are present at which position in the genome in which cell type. And this is a terascale cube of just numbers. And so we need to figure out what it means. And that's where we come in. And that's where computer science comes in and machine learning. And these data sets are massive. And just as Google and Facebook use machine learning to study, the massive amounts of data on the internet, similarly, we can use machine learning to start understanding patterns in the genome by analyzing these kinds of teracubes of information. Okay, so what did we learn from this? The first thing we learned is we are able to now paint the genome. So this is one small portion of the genome, okay? And this is a gene called PAX5. You may ask, what does PAX5 do? One way to answer this question is to perform these experiments in hundreds of different cell types and tissues and paint the genome. So we literally color the genome, each position in the genome, with a different color, and the colors correspond to these different markers of activation, repression, proteins, binding DNA, different biochemical markers. And what we're showing you here is a compressed representation of all these hundreds of different markers. So wherever you see red, it's an active control, red or yellow, it's an active control element. If you see green, it's the body of an actively expressed gene. And if you see gray, it is just a repressed region of the genome, okay? And now we can do this in every cell type or tissue in the body. So what I'm showing you here is 5 or 6 cell types. These are embryonic stem cells, different types of embryonic stem cells. And you can see that this gene PAX5 is gray in color, right? So it's repressed. It's not really being activated. Now, as I move to different cell types, so there's the same piece of the genome, and I'm seeing how it's being painted now in blood cells, okay? T cells and B cells. And then I can do this in hundreds of other cells. Epithelial cells, brain cells, muscle, heart, smooth muscle, digestive, cancer cell lines, all kinds of stuff. And notice what happens to this gene in very specific cell types. These are specific types of blood cells, immune cells. You see the start of this gene, the control element turns on, it goes from gray to red, and the gene body fires, right? It goes from gray to green. And so this way we can really not just get genome sequences, but we can start figuring out dynamics of gene activity and control element activation, all these beautiful yellow things that are popping on and off in different cell types and tissues. And so we get this beautiful dynamic map of genome activity in hundreds and thousands of different cell types and tissues. And what we realize is for the first time, we're able to map the control circuitry of the genome And just 25,000 genes are being controlled by more than 2.5 million control elements. Okay, and that really gives rise to the complexity of the human phenotype. It's not that we have many more genes. We have just 25,000 genes, but we can control precisely how those genes are expressed in different cell types and tissues. And there are millions of control elements turning on and off in different cell types and tissues, controlling the activity of these genes. So this is great because now we're able to map the precise elements in the genome that are controlling gene expression for the first time comprehensively in hundreds of cell types and tissues. But the big question is, how is the DNA sequence of these elements encoding this information? And so that's where machine learning comes in. Okay. And the key thing to remember again is if you take any of these control elements, they're bound by these proteins, right? You must be wondering, how do the proteins figure out they're supposed to bind these locations, right? The genome is huge and vast, and why does this protein, green protein, come and bind this specific spot in the genome? It's because these proteins recognize very specific sequences of letters. We'll refer to these as DNA words or motifs. And what's amazing is that these control elements have their own language. Just like we have languages with words and syntax and grammar, the genome has its own language. It has a whole bunch of these beautiful DNA words that are found in these control elements in very specific syntax and grammars. And that really drives specific combinations of proteins to come and bind those words, thereby activating genes. Okay, so our goal is to decipher the language of the genome, the words and the syntax and the grammar. So how do we do that? Well, one way to do that is to basically convert this whole problem into a machine learning prediction task. Okay, and the basic idea is, given one such high throughput sequencing experiment, right, where I get these readouts of, let's say, this protein binding DNA across the whole genome, one such experiment gives me a beautiful readout of the likelihood that the protein is bound at those locations. Okay, so what I can do is I can take the whole genome, which is 3 billion letters, I can chunk it into little bins, let's say of size 200 base pairs, 200 letters. And each of those base pairs, right, each of those sequences, sorry, get assigned a value, a label. And the label tells me, is that region bound by the protein or not? Or it tells me some real valued number telling me how strongly the protein is binding that region. And so what I end up with is a machine learning problem called a classification task. Think of this as similar to like how when you search for images on Google, they are able to very quickly like label images like cats, dogs, elephants, whatever it is. It's the same kind of problem here. Instead of mapping images to labels, as Google does, we're trying to map sequences to labels. Our labels are not cats and dogs. Our labels are, is a protein binding the sequence or not? And so we have millions of these sequences across the genome, right? Every chunk of the genome is a little sequence, and the experiment assigns it a label telling you, is that sequence bound by the protein or not? And this is a beautiful machine learning problem called a classification task. Our goal is to take a bunch of sequences Si and to map them to corresponding labels Yi through a function, a mathematical function that takes these sequences and somehow transforms them into a label. Okay, and this is called a supervised classification task. That's where neural networks come in. So neural networks are basically machine learning algorithms. They are very powerful pattern detectors. What they can do is take one type of input, like an image, and map it to some other type of output, like a label. In this case, our inputs are sequences of A, C's, G's, and T's. The neural network has a whole bunch of these neurons. Neurons are just pattern detectors, and there are layers of these neurons. And these layers of these neurons learn increasingly more complex patterns as you go up the layers. The neural networks are kind of based on this loosely, not very strongly, but loosely based on the structure of the brain and neurons in the brain, neural circuitry. Neurons are basically pattern detectors, and the neurons that are closest to the sequence right here, they learn very simple sequence patterns. And the neurons in the next layers take the patterns from the previous layers and learn more and more complex patterns. Okay, and the last layer of the neural network tries to predict these profiles from the experiments. Okay, either a binary label telling you that the protein is bound or not, or it tries to predict the actual signal. Another good analogy to think about this is like a text to speech converter. Remember, like, so you have a lot of these software that can take text and generate speech out of it. That's also usually a neural network. In this case, our text is the DNA sequence, and our speech is the signal that's coming out of the genomic sequencing experiment that's telling us whether a protein or some biochemical marker is present at a particular position or not. And these models are incredibly accurate. So firstly, they learn patterns from the sequences de novo, right? And secondly, they can very, very accurately predict these patterns. So here I'm just showing you some examples. These are observed, these are the experimental patterns, right here, this red one, and this one is a predicted pattern from the neural network. You can almost not make out the difference. The neural network is just able to take the sequence of that region in the genome and predict this beautiful profile coming out of an experiment. Now, this gives us huge power because now that we have this model that has taken sequence and can learn to predict what these profiles are, we can start interpreting these models. What are the patterns the models are learning? And what we do is we take the model that is trained, and then we interpret which nucleotides in the input sequence are actually giving rise to the predictions. And what we can do is take any genomic sequence, here's a regulatory element, it has thousands of nucleotides, and every nucleotide in that sequence gets a score. And the score tells us how important that nucleotide is to predict this output. And you can see that in this particular regulatory element, most of the nucleotides are not doing anything particularly important, but this one is. And we've identified a DNA word, this TGCAT thing. This is the binding site of a protein called OCT4. Okay, so this is amazing. The neural network can just de novo take raw sequences, map them to these experimental profiles, and using computational methods that we've developed, we can interpret the models and identify the DNA words and their syntax. That means who comes next to who, what's the spacing differences, what should be the arrangements, and so forth. And we can do also very powerful in silico experiments, mutation experiments, where you can mutate these sequences and try to understand how important they are for biological function. So I'll show you one example of how we actually validate these predictions. I'm sure many of you have heard of CRISPR experiments, CRISPR-Cas9. So CRISPR experiments are these new genome editing technologies. These sequencing readouts that I showed you before, think of these as ways to read the genome, right? Because we're able to sequence the genome, we're able to read all of these biochemical markers, but can you also write the genome? Can you actually edit the genome? CRISPR is one of these technologies that allows us to go into cells and actually edit DNA sequences in actual cells. Of course, we don't do this in humans. That's a no-no. We do this in like cell lines in the dish, or in cells in a dish. But here's an example of what how we can use the computational models to predict what a mutation would actually do to these biochemical profiles. Okay, so here's a predicted profile from the model for one particular DNA element. Here's the DNA word that the model predicts as being important. And if we perform the experiment, this is what it gives us. So this is coming from an actual experiment. This is what the model predicted. Okay, and you can see they're quite remarkably alike, right? I mean, there are slight differences, but they're really similar in terms of shape. Now, what we can do is in the computer, we can mutate the sequence. We can convert these TTs to AG. And now the model predicts this red profile. Notice what happens. The red profile is much smaller at this position. And there's also attenuation of the profile at this position. Now, this is computational, okay? There's no experiment. The neural network is predicting what would happen if you had a mutation at this position. Now we can actually go into the cells and mutate these two nucleotides and then measure the readout. And this is what we get, okay? You can see it again is beautifully corresponding to what we see the model predicts. So this is amazing because now we have a model that you can make millions of mutations in the genome sequence, and the model can computationally predict what would happen to all of these molecular readouts. And so using this strategy, we can now take all the 3 millions of genetic variants that we found in the genome, and in each cell type, we can predict the effects on different kinds of molecular readouts, thereby giving us a way to figure out function of these variants. So in the last 1 minute, I'm just going to really quickly show you how we do this for Alzheimer's disease. I'm going to skip this slide. Again, this is the Alzheimer's genome-wide association study. You have all of these loci, right? These genetic variants that show really strong predisposition to Alzheimer's. What we can do is take the brain and perform these kinds of experiments that I just showed you, these molecular profiling experiments, in all the individual cell types in the brain. The brain is a complex tissue made up of many, many different cell types. And here's one such example of a genomic region. We are seeing different types of cell types in the brain: neurons, microglia, which are the immune cells of the brain, astrocytes, oligodendrocytes. There are hundreds of different cell types in the brain. And you can see the same region of the genome can have different activity in these different cell types, right? So you can see, for example, this region is very specifically on only in microglia, right? You can see a strong signal in microglia, but it's off in all the other cell types. We can fit our neural network models, and then we can take those genetic variants that are predisposing individuals to Alzheimer's, and we can use them you can push them through the model to see what they actually do. And here's an interesting prediction. Here's one of these genetic variants. These typically have these kind of weird names, RS some number. In microglia, in these cells, microglia cells, what our neural network predicts is that this genetic variant sits within a DNA word, this particular DNA word, GGG, CGAGG. It is the binding site of a protein called KLF4, very important protein. And when this G is mutated to an A, which happens in the diseased individuals, notice what happens. The model predicts the DNA word is decimated, and the binding of this protein is decimated, and the nearby genes get dysregulated. Okay. And so we are now able to interpret genetic variation. We're able to tell that this variant is important for Alzheimer's, but we know what it's doing to some extent. At least we can predict what it's doing. It's disrupting this DNA word, which is a binding site for this protein. And it's the A that specifically does the disruption, right? So we even know which letter, which mutation actually creates the disruption. So we can do this for all the millions of variants in the genome and start interpreting what all of them do, how they break DNA words, which proteins bind to them that are dysregulated, which genes nearby are dysregulated, and in which cell types the dysregulation is happening. So here's the cool thing. Even though Alzheimer's is a neurodegenerative disorder where our neurons basically end up dying, this genetic variant is not actually affecting neuron function. It is affecting microglia function. Microglia are the immune cells of the brain, which interact with the neurons to keep the brain healthy. Okay, so this gives us very specific predictions to go after therapeutically. Okay, and so just to summarize, we can use large-scale molecular profiling experiments with DNA sequencing technology to decipher genome function. Machine learning models or molecular profiling data can be used to interpret and decipher functional DNA words and syntax. The language of the genome can be validated using genome editing experiments. Molecular profiling data and machine learning models can be used to decipher mechanisms of disease-associated mutations. And hopefully I've convinced you that computational biology is a highly interdisciplinary science that is awesome. You get to do computation, you get to use really amazing concepts from computer science and machine learning, and at the same time, jump back to the wet lab, go back to actually doing beautiful experiments with real life cells, use some of the greatest technology that exists today with high throughput sequencing, and really make inroads to understand disease mechanisms. And with that, I'll just end by saying that all the hard work that I just showed you today has been largely done by my students and postdocs in my lab. So all credit goes to them. And none of this happens in a vacuum. The government, particularly NIH, funds a lot of this work. And so I thank them for their contributions, and also our countless collaborators. Science is no more something that can be done by any single individual, any single lab. It is a collaborative effort, and it's a ton of fun to work with a whole bunch of really smart individuals. And with that, I will end. Thank you.
Thank you so much, Dr. Koundaje. That was awesome. We don't have time for questions right now because we're a little bit behind. We're very behind schedule, just with all of the events since, we've had events since 8 a.m. this morning. So if you're watching the live stream, just know we're a little bit behind.
Yeah, no problem. What people
Yeah.
can do is either just type on the chat if you have a question. I'll stick around for a bit, or you can. I'm on the Slack as well, so I can answer questions there.
Okay, thank you so much. Thank you so much, Dr. Kandaje. Now we're going to transition to, we're still going to be talking about proteins, but we're going to transition to Dr. Spangler. Let me give you a spotlight. Awesome. Okay, welcome Dr. Spangler. She is an assistant professor in biomedical engineering at Johns Hopkins University, and she's going to be joining us today to discuss her work with engineering proteins. Dr. Spangler earned a BS in biomedical engineering at JHU and went on to conduct her PhD research in biological engineering at MIT. So without further ado, don't want to spoil too much, so Dr. Spangler, please take it away.
Thank you so much, and thank you for this incredible opportunity to present to all of you today a little bit about my lab's research. I was really excited to see in the previous presentation some interest in, sort of the genomics and ultimately what goes into making proteins, and also how computational work can integrate with experimental work to create really cool science. And sort of continuing along that theme, I'm going to tell you a little bit about how my lab is using molecular engineering, specifically engineering things at the level of proteins to be able to modify the way that human physiology works. And particularly, we're very interested in how we can modify the immune response. And so without further ado, let me get into my slides. So many of you are probably familiar with the rapidly growing protein therapeutics industry, but interestingly, it's not actually that old. And in fact, not that much older than I am. And well, I guess I'm pretty old, but I'm not really that old. So the first protein therapeutic was actually first approved in 1982, which is, again, not really that long ago. We're talking about, 38 years ago. And I don't know if any of you can guess, but it was recombinant insulin, which is, of course, what many diabetics take and are dependent on to replace that hormone that's lacking in their body. And in that 38-year span, right, from 1982 to today, there's been a huge explosion, right, of this market of protein-based therapeutics or molecular therapeutics, which are also called biologics. And there are over 300 biologics that are currently approved for use in humans, with a growth rate for biologics in the biologics sector of 3 times that of the overall pharmaceutical market. So as our population ages and various environmental and lifestyle factors come into play, there's an overall increase, right, in the demand for therapeutics. And to be growing at 3 times the rate of the entire pharmaceutical market is quite alarming. But when you think about a protein in nature, right, it doesn't care about your drug, right? Natural proteins are not pressured or evolved in any way to make good drugs. And in fact, there's a number of limitations, right, inherent properties of proteins that actually make them horrible drugs, right, terrible. And so the first limitation is what's known as pleiotropy. So when you're a protein, as we just heard in the last presentation, there's a lot of genetic information, right, DNA, that's encoding all of that information, or encoding everything that it takes to actually make that protein, right, and express that protein. And so that can be expensive. That takes a lot of energy, right, for all the processes of transcription, translation, and how do you, minimize the effort is by reducing the number of proteins that you have present in your body, right? So each protein is pressured by nature to be jack of all trades, right? Do a lot of different things at once in a very small genetic package. And that's great if you're a protein in nature, right? And trying to be very efficient. But that's terrible if you have a therapeutic, right? Because then it's going to be able to activate multiple different receptors on various cell types and have all kinds of effects all over the body, not necessarily, right, the effect that you would want. Let's say you have a drug that you want to target cancer, but if it's targeting all of your healthy cells all over the body as well, then it's not going to be able to perform its function for two reasons. First, it gets diverted, right? So the protein gets sponged up and soaked up, right, by all of these different healthy tissues as sort of a decoy, and it can't actually get to the location that it needs to treat the disease. In addition, by affecting those different healthy cells and having some sort of cytotoxic or cytolytic function, there's going to be a plethora of off-target effects, right? Meaning that it can have a lot of different side effects, which in many cases can be dangerous and lead to death of the host individual that's being given the drug from the therapeutic rather than from the disease that they have. The second limitation, which is common amongst protein therapeutics, is what I'm calling expression and stability issues, right? So in terms of recombinant expression of proteins, which my lab does a lot of, it's sort of the bane of our existence in many ways. Sometimes proteins express great and you're very lucky, but mostly proteins, right, again, they're evolved to be expressed in your body. And when you try to produce them outside of the body, right, some sort of exogenous way, you can get very low yields for production. They can be prone to aggregation or they can absorb to surfaces. And as a result, there are difficulties in manufacturability, and there can be a problem known as immunogenicity, right? So immunogenicity refers to an immune response against the particular drug that you're delivering, rather than, again, against the disease, right? A lot of drugs are meant to activate the immune response, but activate that to kill a particular disease like a pathogen or cancer, not to actually activate the immune response against the drug itself, rejecting that drug and leading to potentially overactive immune and autoimmune pathogenesis. Finally, proteins have very poor what are known as pharmacokinetic properties, which refers to the rate at which they're cleared, essentially, what your body does to the drug and the rate at which they're cleared from the bloodstream. So when you administer a drug, typical protein of less than 50 kilodaltons, it will be cleared from your bloodstream in less than 5 minutes. And that's great if it's a diagnostic drug, right? If you're just trying to look at and localize that to a particular site of disease and then have it cleared. But that's terrible if you want to have a long-term sustained effect, right? In terms of a therapeutic. So again, that will lead to a transient response and inefficient delivery to the target organ. Okay, so I've stated all the problems, which is always, the first step, right? Figuring out what the problem is. But what's the solution, right? How do we solve this? And so my lab is very interested in how can we take what nature has given us and redesign, right? Rejigger those proteins, or inspired by nature, build entirely new proteins that nature's never even seen before that could be useful as therapeutics. So the way that my lab does that is we have sort of this three-pronged approach. And the first prong is what I'm referring to as molecular engineering. Now, molecular engineering is sort of a loaded term that can mean a lot of different things to a lot of different people. What my lab takes it to mean is using these processes of molecular evolution. So all of you, I'm sure, are familiar with, sort of the Darwinian concept of evolution, right? How we came from other forms of life and have evolved over time. So we can actually simulate this process on a very small scale and on a very rapid scale in a test tube. And the way that we do that is using a display platform. So my lab uses the display platform of yeast, which a lot of you deal with on a daily basis in the bread that you eat. This is just simple baker's yeast. And what we do is we take these yeast and we zap them with different proteins, and we create what's called a library. Now, not a library where you read books, although I don't know that anybody uses libraries anymore in the digital age, but a library in the sense that it's a panel of different variants. So you start with a protein shown in red, And you make a bunch of different mutations shown in green and orange and cyan. And then the idea is that each one of those variants, right, is expressed uniquely on a different yeast cell. And then you come in with your bait, right? So when you go fishing, right, you want to have a bait to pull out the things that you want. And it's exactly like that. You go fishing in this library against this gray protein here, that's your target, and you pull out all the things that bind, you wash away all the ones that don't. And through these iterative cycles of directed evolution, right, which is, again, essentially a simulation of the process of evolution on the level of proteins, you can actually pull out the clones for the different sequences that represent those proteins that have the function that you want, right? So this is a really exciting concept, and it actually won the Nobel Prize a couple of years ago, back in 2018. But my lab obviously didn't discover that. We're not the first people to use this. So what's our unique angle, right? What do we do differently than people that are, you know, doing straightforward or random protein evolution? So what we do is we try to integrate insights that we have from structural biology. So crystallography, cryo-EM, NMR, all of these different techniques and technologies that have been used to understand protein-protein interfaces have really catalyzed new opportunities in the field of molecular engineering, where we no longer have to just kind of randomly assign, right? How do you choose what goes in this library? Now we can actually build smarter libraries that can get us better, right, and faster to the solution for interesting proteins that we want to create. And the arrow goes both ways in that once we actually discover these new proteins, right, that have the function that we want, we can solve their crystal structure and get at how they're working and how we can potentially make them better. And this is great, having this sort of symbiotic relationship with structure and molecular engineering, but we obviously want this to go somewhere, right? It's all about the translation, right? And about the next step. And particularly my lab, being at Johns Hopkins University, has a unique opportunity to integrate with clinicians and medical professionals who are able to bring these and translate these technologies into patients. And so my lab really works on spanning the space from the discovery of new molecules, designing and engineering them, and then ultimately being able to develop them in the preclinical and ultimately clinical settings. So in terms of their functional evaluation, we do that often in mice as, you know, sort of a simulated model for how the drug or therapeutic would act in a person. We also actually take our own blood and look at our immune cells and see how our different interventions and therapeutics impact those cells. And ultimately, the goal is to be able to translate these into phase 1 clinical trials. I think at a lot of institutions, you'd sort of say, okay, we can figure that out and, you know, long-term kind of outsource. But what's fantastic, again, having the resources and opportunities at Johns Hopkins is that we have the relevant patient populations as well as the infrastructure here to do that all in-house. And in the 3 years that I've been here at Johns Hopkins, I've actually been involved with 7 different patents of molecules, one of which we've licensed and another of which we're building up in-house to develop into clinical studies, hopefully by the end of this calendar year. And so again, I think the opportunities to really use these fundamental protein engineering technologies to take those all the way to the clinic is really what motivates a lot of the research that we do in my lab. And then the final arrow goes back, right? So once we actually, again, discover these new molecules and these new technologies, and we put them into people, we learn something, right, from the actual implementation in humans. And we can feed that information back into the process, right, the engineering process, to improve the therapeutics that we design. So what kind of drugs am I looking to, you know, sort of create, and what sort of diseases am I going after? Well, as I mentioned at the beginning, we have a particular focus on immune diseases, and on a very high level, right, you can think of the immune system as a balance between immunostimulatory cells, things like CD8 positive T cells, NK cells, natural killer cells, other types of effector immune cells, saying, go, 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 kill those pathogens, right? Kill COVID-19, kill, or, kill cancer, right? And there are certain diseases, as the ones that, for example, the ones I mentioned, where you would want to actually increase the number of effector cells, right? To, again, bias the immune response to kill disease. Conversely, there's diseases where you would want to go in the other direction, right? Things like autoimmune disorders, diabetes, Crohn's disease, colitis, MS, right? Where your body is attacking your own healthy organs. And you would actually want to repress that pathogenic immune response. Also, if you're doing transplantation medicine, if I want to give somebody an organ transplant, I want to make sure they're immunosuppressed because I don't want their immune system rejecting the new organ that's going to save their life. So how do we use protein engineering, right, to create proteins that will bias the immune system, right? This is sort of our mission for targeted disease therapy. So then the next obvious question is, well, what diseases do you work on? And I often spin around the question and I say, well, what diseases don't we work on, right? Because when you're working at the protein level and at the level of, sort of molecular engineering, that applies to everything, right? The proteins are the building blocks of all forms of life. And so we actually work, rather than, sort of taking a particular disease and saying we're a flu lab, or we're a cancer lab, or, we're a Crohn's disease lab, right? We actually turn where a lot of labs, have a particular disease target, and then they have a bunch of different approaches to sort of target that particular disease. We turn this paradigm on its head and say, we have this common approach of structure-based molecular engineering. And now we can apply this to a range of different diseases. And again, just to give you, sort of a high level overview of some of the projects we have ongoing in the lab, we have everything from activating the immune system in breast cancer, pancreatic duct adenocarcinoma, projects in HIV, malaria, flu. More recently, we have a project on COVID-19. Conversely, we have projects where we're trying to suppress the immune response. We have active grants in diabetes, skin transplantation, colitis, and also in tissue engineering, which has a lot of synergy with the immunoengineering field. So, I want to, in the last couple of minutes, just give you one quick overview of a project that will show you and illustrate for you how all of this works together, right? How does structure-based molecular engineering lead to therapeutic design and ultimately, disease therapy and immune disease therapy? So I'm going to talk a little bit about a project that we have ongoing where we're trying to engineer using actually computational protein design methods in combination with molecular evolution, new cytokines that will affect immunotherapy. So cytokines are soluble proteins of the immune system, and basically they're messengers that communicate information from the outside of the world into cells. And the way that they do that is by interacting with and dimerizing or binding together these transmembrane receptors. And the extracellular portions, as you can see, of these receptors coming together leads to their intracellular portions bumping into each other, setting off a cascade of events that ultimately will determine what the cell does, right? When you're a cell, you don't have that many choices in life, right? You're going to die, you're going to grow, you're going to move, you're going to, proliferate. But all of these different things that a cell can do and cell fate outcomes are controlled by cytokines, right, which communicate information into the cells at the protein level. A particular cytokine that we're very interested in is known as interleukin-2, and this was the first cytokine to be both genetically and structurally characterized. And it's an interesting cytokine in a lot of ways because it has two different types of receptors. So rather than just interacting with two transmembrane receptors, beta gamma, there's also this alpha receptor for cells that have express high levels of IL-2 or alpha. And importantly, cells that express this alpha receptor have a 100-fold higher affinity So they normally IL-2 is biased towards signaling on cells that have IL-2 or alpha. And importantly, regulatory T cells express very high levels of IL-2 or alpha. So whereas effector T cells express very low levels. So normally IL-2 is biased toward creating an immunosuppressive environment, although it can also be used to create an immunostimulatory, right? Because it's sort of activating both sides of the coin. So even though IL-2 is normally biased toward Tregs, again, what if we want to stimulate the immune response against something like cancer, and we want to actually reverse that bias toward IL-2 or alpha low cells or effector cells? And so that's where we teamed up with David Baker's lab, which is located at University of Washington in Seattle, and is the premier lab in computational protein design that developed a software known as Rosetta that some of you may be familiar with. And this particular protein that we designed was meant to mimic a cytokine, specifically to mimic IL-2, but to improve upon the properties. So as you can see, the cytokine that we were basing this off of, IL-2, is a 4-helix bundle, meaning that it has 4 alpha helices connected by interhelical loops. And the interactions with the beta gamma subunit are, again, what would activate effector cells, whereas interactions with alpha would recruit in regulatory T cells. So to focus on effector cells, we focused on the interactions with the beta gamma receptors, and we fixed those in 3-dimensional space, and then built a cytokine, right, a globular protein around that, that basically integrated all of those different interactions with beta gamma, but no alpha. And another cool thing that we did was we said, in nature, there are 37 known discovered cytokines, and there could be more, but they all have the same format, that their helices are facing up, up, down, down, meaning that the first 2 end to C terminus are going up and the second 2 are going down. And that's actually very inefficient, because to get from the top of the first all the way to the bottom of the second, or the bottom of the third all the way to the top of the fourth, you have to have these long interhelical string spaghetti things shown in pink. And that can destabilize the protein and not make it sort of a lean, mean version of IL-2, which is this Neo2 molecule that we're calling it, that has these nice short linkers and eliminates, right, all of that spaghetti. So we popped out a variety of different designs computationally, and then we used the yeast display platform that I mentioned earlier to display all of those different designs on different yeast. And then we came in with the beta gamma receptors and selected for things that were able to bind to that target. And through various iterations of this molecular design, right, sort of Darwin in a test tube, like we talked about before, we were able to come out with a molecule that had beautiful binding to the IL-2 or beta gamma receptors, but no interaction with IL-2 or alpha, in contrast with the wild type IL-2 cytokine. In addition, we saw that the IL-2 or alpha positive cells normally have the bias, right, for IL-2, but in this case, Neo2 was active on the effector cells, giving the overall advantage in terms of signaling to immune effector, right, and immunostimulatory responses. Finally, we demonstrated that this sort of super hyperstable cytokine that we had created was basically a rock, right, indestructible. We could actually heat this to 80 degrees Celsius for 2 hours and it lost no activity. And we could even literally almost boil it to 95 degrees Celsius for hours at a time without any loss of function, whereas IL-2, right, the regular cytokine, was dead in the water. And more importantly, right, we had created something that was biased toward activating the immune response. And in contrast with IL-2, which was not able to control this very aggressive model of colorectal cancer, our Neo2 molecule increased survival and significantly inhibited tumor growth. The same thing happened when we used it in a melanoma tumor model. And actually half of the mice, right, in the melanoma model were sacrificed due to the toxicity of the drug. And the other 5 died due to the tumor burden when we treated with only the natural cytokine. But then when we came in with NEO2, right, our engineered computational cytokine, we had a 50% long-term survival rate. And I don't know about you, but I'd rather have my odds be 50% than 0%. So that's huge progress for a very aggressive model of melanoma. Finally, we didn't see any immune response, right? One of the problems that I mentioned about natural cytokines, about natural proteins, is they can lead to immunogenicity, meaning an immune response against the exogenously delivered cytokine. And fortunately, we didn't see any evidence of that that was significant in this case. So I just want to wrap up there so that we can leave a few minutes for you guys to ask all of your burning questions about protein engineering. But I just want to say that, you know, I've had such a positive experience in the protein engineering sphere, but also in the scientific sphere, just with people like you who are here today, who are just curious to understand nature better and how we can actually manipulate, right, what's in nature to create the next generation of therapeutics that will transform human health. So, and of course, acknowledging all of the awesome folks in my lab at the Translational Tissue Engineering Center at Johns Hopkins School of Medicine, and acknowledging you guys for your attention and for coming here today. And please let me know if you have any questions.
Thank you so much, Dr. Spangler. That was an amazing talk. I have one question. It's like more broad, but with like biomedical engineering, I know like when I first learned about the field, they said it was basically like a combination of CS, physics, and biology, and chemistry. Which of those 4 subjects do you use the most with biomedical engineering?
It's a great question. And I would expand that. It's definitely biology, physics, chemistry, all of those things are in there. Mechanical engineering, material science and engineering, right? It's a lot of different things because, and I think when people ask, you know, to sort of define, you know, what is bioengineering, what is biomedical engineering, what it really, I think at its core, right, is using quantitative tools and technologies to affect human health, right, in some way, shape, or form. In my lab specifically, on a daily, you know, sort of basis, we use a lot of chemistry, a lot of biology, specifically immunology, and a lot of physical engineering principles, I would say, are the primary things that we use. But you could look at another biomedical engineering lab, and it could be a completely different subset. They could use a lot more computational tools. They could use, you know, basically just be straight coding all day, like, you know, no wet or experimental, you know, sort of component. There are other labs that are very biomaterials focused, right? And they do a lot of material science and chemistry, and also, you know, biological, you know, sort of experimentation as well. So I guess I sort of artfully dodged, in some senses, committing to an answer in your question. I can definitely speak for my lab and I can speak for, you know, specific labs, but the exciting part about the bioengineering field, which is what really drew me in the first place, is that you're constantly exposed to many different subjects and many different branches of science, and you don't have to necessarily define yourself or commit yourself to just one field.
Thank you. That does answer my question in many ways. But have you personally like used computer science?
Yeah, so great question. So my lab collaborates with David Baker's lab and then also with Jeff Gray, who's in the chemical and biomolecular engineering department here at Johns Hopkins, for most of the computational components. And so we don't actually do the coding, you know, sort of interface with Rosetta, but we get the outputs of that. And we visualize. I showed you, you know, some different protein structural diagrams, you know, how we would visualize, and we interpret that by using these computational algorithms to determine what interactions are happening, what non-covalent, right, what van der Waals, hydrogen bonds, right, what's happening between the different amino acids in the interface. And we synthesize that information into how we're going to design the libraries. So although we're not the ones necessarily developing the next generations of software, we're using those softwares to integrate into the engineering process and the design process for our work.
Thank you.
So it looks like there's some questions from the chat here. Which specific components of the protein did you engineer to make those proteins that can survive high temperatures? Great question. So what we did was we actually packed the core of that fourth helix. Let me see if I can go back to the design here. So you can see that this helix that's shown in green is kind of bent, right? It has sort of like an L shape to it. And we flattened that out. You can see here shown in yellow. So we changed the order of the helices a little bit, which is fine. But more importantly, right, we flattened out that helix in the back so that essentially, instead of being, sort of the helix that would kind of recruit in that interface with IL-2 or alpha, now it's just packing flat and tightly against the other three helices to allow for the protein intramolecular interactions, right? The interactions holding the protein together to be more stable. And that stability is what led to ultimately having the thermal stability, because even if you heat this to very high temperatures, those alpha helices, right, are very close to each other and they're optimally packed so that those interactions will be very, very hard to destroy, even though they're non-covalent. The other thing that we did, which I mentioned before, sort of with the spaghetti analogy, is that instead of having these long interhelical loops, right? So the most flexible parts of proteins are what will destabilize them the most, right? Because that stuff is dynamic and it's floating around in space rather than having a very regular and regimented structure held in place by hydrogen bonds, which occurs in alpha helices. So we basically eliminated everything but the alpha helices, right, by creating these very short linkers between the helices. And now there's no unstable parts of the protein that can lead to it falling apart. And as a result, it takes very, very, very high temperatures that we weren't able to reach in these studies to be able to destroy our engineered cytokine. Great questions. Other questions from the audience? Or, how do you flatten the helices? Great question. So interestingly, the sequence between IL-2 and NEO2, if you aligned the sequences, it would be 100% clashing. There's no resemblance between the sequences at all. And the reason for that is we just rebuilt the entire helix piece by piece. So we took these sort of four, like a sliding scale of 4 amino acids, and we said, how will these 4 amino acids look, right, in theory? Because it would be very hard to just take 100 amino acids and say, how is this thing going to fold and how is it going to look? Instead, we looked at different pieces and we mapped 4 amino acids at a time. And for each of those 4, we optimized them to be in this alpha helical conformation. And so again, when we had sort of this bend in the helix, it had a region that was not going to stably hydrogen bond with the adjacent residues, and that's what led to sort of it bending. And in ours, we designed it so that there would be no gaps and no spaces in between the hydrogen bonding network that holds together that alpha helix. Again, great question. Thank you, Julia. Other people. Oh, Julia has another question, which is great. The function of the protein, was it different when you engineered it? Indeed, the NEO2 function is different from IL-2, and the biggest difference is what you see here between cells that express IL-2 or alpha versus the ones that don't. Because remember, we designed this NEO2 so that it no longer cares about alpha, right? There's no interactions, it's just a total flat line. And as a result, we got a bias toward immune effector cells that ultimately led to its efficacy in treating various types of cancer. And we're also experimenting with the same molecule in infectious disease models. Because again, the same idea and concept of activating the immune system can be used for cancer or for various infections that would threaten the immune response. Why is thermal stability important? Sean asks. Yes, it's actually a very insightful question that you ask, and one that we put a lot of thought into in terms of how we were going to frame this project and ultimately the paper, that came out of this work. And in some sense, we've explored, what are the advantages of having a thermostable protein. And in some senses, there's much that remains to be explored. So one advantage, of course, is that potentially at under high temperature or pressure conditions or situations, this protein could be extremely stable. So you think about drug manufacturing and drug processing, having a molecule that you can produce at very high levels and not have to worry about the storage conditions could be extremely useful for disseminating it all over the world, right? To different regions and different places, and having that be able to withstand the elements and other sorts of challenges that might arise. It can definitely help cut down costs in terms of manufacturability and potentially facilitate FDA approval and advancement and ultimately clinical application. Other things from a research standpoint are if you actually have a protein, right, that can take really, really high temperatures, there's all sorts of processing and development that you can do in the research lab context. Another example would be to actually use this in what's called hyperthermia conditions, where there are some approaches now, particularly for cancer therapy, where they try to use heat treatment or heat shock to destroy cancer cells. But when you're using this heat treatment, if you're giving, another therapy in tandem, you could destroy that protein, right, by elevating the temperature. But this protein, right, would be very robust against any temperature increase that you would use for any sort of hyperthermia treatment. So there's a variety of different applications, both tapped and untapped, that we're still thinking about. But at the moment, we're just really excited that we've created this molecule that seems to be behaving exactly as designed, right? In sort of this bespoke, kind of condition, but also that it could have, larger implications than we can even envision right now.
Thank you, Dr. Spangler. I think we have, sorry to cut you off, but we need to move on to the next speaker.
Of course. Yeah, thank you again for the opportunity. And if anybody has any questions, I had my email address up here at the end. Please feel free to reach out anytime. And also to follow up in the chat if you have more questions.
Yep. Yeah, thank you again for the amazing lecture. So our next speaker is an ACM fellow and the winner of the IEEE Tsutomu Kanai Award. He has written 3 textbooks and published more than 150 papers in prestigious journals and conferences. Software he developed operated in the New York Stock Exchange for more than a decade without trading disruptions and played central roles in the French air traffic control system and the US Navy AEGIS warship. Today he will be talking about cloud computing. Without further ado, please welcome Dr. Ken Berman.
Well, thank you very much. It's tough to follow your previous speaker. She was awesome. I was really enjoying her talk, and kind of disappointed that she had to cut off so I could talk. So I work on cloud computing systems, and what I mostly want to talk about today is how computer science is starting to reach out and engage with devices in the real world, what we call sensing devices, IoT devices, for Internet of Things, and try to make the world intelligent. And I want to talk a little bit about why a lot of us think this is a really exciting development, what cloud computing is and how this enlarges the idea of cloud computing, and how privacy enters the picture. Privacy has become a growing concern for computing that reaches out into the real world. And so I'd like you to have a chance to think a little bit about the privacy implications and trade-offs that this type of intelligence at the edge might raise. And we should have some time for dialogue about that at the end. Okay, so that's the plan. By the way, I'm experimenting with captioning. I hope it's not too distracting for you. I'm going to be teaching this way all through the fall, and Cornell's been pushing for captioning on the theory that it makes things more accessible. If it's more distracting, and I can see that it doesn't always render my voice properly, just ignore the captioning. So anyhow, we'll talk then about Internet of Things and cloud computing and machine intelligence. Now, I don't work on all of these at once. My real work is on distributed computing, which is when we take a computer on one system somewhere and connect it to a computer elsewhere, and we split a computer program into pieces, and part runs on one machine and part runs on the other, or on some set of them, and they cooperate to become a larger scale coordinated system. I was one of the inventors of this area, and companies like Google and Amazon, Facebook, Microsoft are very, very invested in distributed computing. In fact, there are data centers now with millions of computers in them, and many of the techniques that are used in those data centers were invented by people like me and by my students over a long period of time, to the point actually that several of my students run those places right now. And we can even talk about that if there's time. So distributed computing is what I really do. And these days, distributed computing is the sort of the platform is the term we use that supports machine intelligence and applications that dynamically learn and reason and cooperate to do smart things. So the game here is that even though I do a part of this, I need to have the bigger picture because that's the use case for what I do. So here's an example of that use case. This is something Microsoft is doing that we're involved with. It's called FarmBeats. And in this Microsoft FarmBeats project, the idea is when you look at a farm, instead of just seeing alfalfa growing or soybeans, these are soybeans and you know, they're happy or they're not, to start to think a little bit about the conditions in the field. You can think of this field as a kind of a 3D biome, right, that extends into the ground. It has nutrients, it has various levels of soil humidity. There may be pests of various kinds. I'm hoping it's an organic field, but there still might be healthier or less healthy sections of the field. And then we want to ask questions about this. Is there a spot that might have a problem with pests where we could do a spot application of pesticide? So you're probably thinking, what is that thing back there? It's probably spraying some noxious stuff. Probably it is, but if we're doing that, let's spray it as narrowly and locally as possible to kill the pest, but then leave the rest of the field alone, right? If we apply fertilizer, let's apply it because it's required. If we irrigate, let's irrigate where the field is dry. I was in a taxi with a driver from Morocco just before COVID started locking us all down. And I was talking to the taxi driver, and it turned out he was going to retire and go back to Morocco and raise olives with his brother. And I asked about climate change. He said, well, it's becoming very dry, and that they had a source of water, but that there wasn't enough water to water all the time. They had to water their olive trees twice per year at the right moment. And he said that was the decisive question for success for what he's trying to do with his brother. Well, you could imagine smart monitoring telling him and his brother if this is the moment to water the olive trees. And it would be possible to do that today with smart sensors. And then when we talk about a smart world, we're really talking about an app on his iPhone. And you know, even in Morocco, even in an olive orchard, farmers have things like iPhones and Androids. And be able to look at your iPhone and have it say, 3/4 of the field really needs to be watered now, and these are the trees you should focus on. And there are literally sensors you can plug into a tree that'll tell you that kind of thing. So that's the sort of thing we have in mind, and it's really becoming possible now. And it extends to all sorts of farming, not just you know, soybeans. Fitbits for cows are a thing, a real thing. And it turns out you use them to try to understand if the cow is healthy, if she's close to having her baby now, if she's eating well or off. If she's developed some kind of a rash, you might be able to sense that with photos and automate the analysis of those photos. So if you had a farm that had 1,500 cows on it, where the farmer isn't going to be able to look at every single cow every day, the computing system really could. You can also recycle the waste off of that farm, and you can do that in intelligent ways, which will dramatically reduce the amount of waste. You can turn it into water that's recovered, fertilizer that you can put back on your fields. You can turn it into energy. The methane that's released can actually be captured and used. So there's quite a lot that you can do. And then at the level of the things the farm produces, you can track the soybeans as they move to the, eventually to the grocery store, and you can track milk from each individual cow, separate out the milk from cows that might be under a treatment for an infection. And you can actually track the productivity of different cows and try to understand what affects that. Now, this is an idea that extends to all sorts of settings. So I'm very interested in other uses that make the world smart. And one example would be elder care. So my mom, who's older than this fellow, she was a mathematician at Columbia University. She still actually works in mathematics. She's 92. Well, she lives in New York City, and I worry about her a little bit at age 92 with the pandemic. She has help. It would be very reassuring for me if I knew that she was living in a smart home that would provide various services and would reach out to her or me if she fell, right? Now, it's one thing to say, well, she should wear a button. She does have one of those buttons, but it'd be even better if the system could tell and had been pre-programmed basically to call me if she falls down and she's not pressing the button because she got bonked on the head, which can happen, And more broadly, if you're elderly and you're trying to live independently, there's a whole question of things you might start to slip on that could put you at danger, leaving the stove running. Out in California, leaving the shower running all day and ending up with some huge fine for wasting water, right? I mean, there are tons and tons of these things. A smart home could really make the difference, where somebody who wouldn't be able to live independently right now can continue to do that. And I'm working with a company on this called Caspar.ai, not the mattress company. They spell it differently here. And they're trying to actually create, in fact, they have created solutions of that type, where you can live in your home and sort of talk to your home, but the home will also have enough awareness to say, Joan, you have the rice cooking and it's running out of water. Should I shut it off? And she might say, shut it off, or she might jump up and add water or whatever. And then you can think more about the world. You can say, well, there's a lot of congestion in our cities. Could we build cities that would be smarter about the way the traffic is routed and about the way that the lights are patterned? So instead of having a smart intersection that looks just at whether there's a car waiting on a given side, has the big picture, and you can start to schedule accordingly. Here's a kind of cute picture. This is actually La Défense. This is out in Paris. And I've lived in Paris on sabbatical. And one of the things that they have got wrong in Paris is that there's a rule for their traffic circles called priority to the right, which means that any car to your right has priority over you. And if you think about entering a traffic circle that's going, so traffic circles go counterclockwise, right? And that means that you're driving along and a car could be coming in from your right into the traffic circle. So it deadlocks, which is a deadlock. A deadlock is a distributed systems term having to do with nobody can move because everyone's waiting for somebody else. That happens in computer software too. We can make the world a lot smarter than traffic circles that deadlock. This actually only happens in a few places though. Most traffic circles are smarter than this one. And we can make the world safer too. If you think about Paradise Fire in California and horrors like that, the first responders really need to know. And if you could just tell them, there are 22 people in this building and otherwise you're sure it's clear, and these are the units that they're in, that would make such a difference in terms of rescuing people, not searching places that don't need to be searched. So a smarter world would actually be a safer world. And you can extend that to many other notions of safety as well. So you get kind of an endless list. And I've worked on quite a few of these things. I'm very excited about the idea that if we could make roadways and highways smart and have them talk to somewhat smart cars, we could really have smart cars. Because I think everybody's beginning to notice that the self-driving cars They're not coming along as fast as people had hoped. It's too hard a problem to just be a completely autonomous self-driving car. Computer vision will get you pretty far, but there's so many different road conditions to worry about. But if the road itself was also intelligent, then that dialogue might work well, because the road could warn you that someone's crossing up here. And even if it was raining, and even if the conditions were pretty bad, that section of the road could know. And then the car would know without having to figure it out on its own. Smart power grid, I'm actually working actively on that right now, where we try to integrate things. This is a Cornell solar farm, and you'd be surprised. It's extremely hard to integrate solar farms into the power grid. And what's super hard and very promising is that if there's solar panels on the roof of a house, that power is used in the house and you're paid for generating it. But in fact, right now, very few places in the world can use the power that's generated in your house. They pay you for it and then they throw it away because they don't have a good way to integrate microgeneration into the global power grid at large scale. And we're trying to develop solutions for that. And in California, smart water would be another thing of a similar nature. So we got all of these kinds of settings that are arising where computing intelligence could make a big difference. And now here's the puzzle. In order to really do this and have it work well for us, we're going to need to understand how to simultaneously monitor my mom for falls and not spy on her, because nobody wants to be spied on. And in fact, I think probably a lot of the people listening in on this have disabled things like Alexa in their house because it freaks them out. We had friends over here in the lake house that I'm in right now. And one of them had a Belgian accent and he was chatting and a deep voice. And suddenly it was Cortana, that was the Microsoft one. Cortana starts to talk like a pirate. So we're like, what is going on here? And it turns out that Cortana has a feature for children where if it thinks the kids are playing at being pirates, it jumps into the conversation with yo ho ho and a bottle of rum and stuff like that. Well, Adrien, who was a 24-year-old Belgian guy living in Vancouver, did not exactly really want to have a pirate conversation with Cortana, nor had he said Cortana at any point. So these systems are a little too intrusive. And on top of that, it turns out that right now, the way that IoT works is that the data captured in your house is exported to these monstrous data centers operated by companies like Apple, Microsoft, and others. And Google is a big one with Google Nest. And they aggregate that data into what are called giant data warehouses, big data, in order to do big data analysis and machine learning on immense data sets. This is the reason they can do things like real-time translations now. These captions you're seeing, I could have told the system to put them out in Belgian with the accent and style used in Brussels, in such and such a part of the city even. I mean, it's kind of crazy how detailed they're able to be. They don't actually offer some of the options they even have. So they can do real-time translation and they can do all of this kind of stuff. But the way that they're getting there is they're uploading it all to data warehouses. And then if you're Facebook with that data warehouse, it's irresistible right now to use that data in ways that place advertising, but in effect, reveal all sorts of things about you and your private life and your friends and their private lives that maybe weren't public. Their parents didn't know, you didn't want it public, and here Facebook knows. And they're using it to place advertising where a person seeing that ad might instantly find something out about you. And this kind of thing is very offensive to me. And you know, I grew up in a world where you could take privacy pretty much for granted. And you don't, want a world that spies on you constantly. I mean, we know now it's not like in 1984 with Big Brother, but yeah, it's creepy. And you could be cyberstalked also, which would be really bad. So the puzzle that starts to arise is if we want this smart world, and I think we do want it, how do we get there without losing all of our privacy? And so we're going to have to evolve because these data centers, they're like a bank vault. And if we're putting all our stuff in them, somebody's going to tunnel in and steal our stuff. And there are other reasons too. It turns out that this data-centric model that's being used is not very ecologically sustainable. So this is a study here on the left from MIT, which is warning that modern ways of doing machine intelligence and machine learning on monstrously big data sets are approaching the limits of what we can afford to do. Computational limits that aren't what people would call algorithmic complexity limits, that has to do with what can be computed, but practical limits that have to do with how much power it takes. And you can sort of see that on the side here. This is looking at what's happened to the use of electric power between 2010 and 2018. It's not even 2020. And you can see that this grayish and orange stuff has boomed in size. And it turns out that these are both forms of what people call cloud computing for machine learning. So machine learning and cloud computing is starting to take up just crazy amounts of the world's electric power. And so what's happening is, instead of cutting back on generating power right now, when we know how much ecological damage all of this power generation is causing from fossil fuels, because mostly it's fossil fuels, what we're doing is we're expanding. Actually, you've got data centers that use as much power as small cities. And one reason for that is machine learning. When you train these machine learning systems on very big data sets, you can look at how much computing is associated with that. And it's become a very successful thing to do, but it's also become crazily hungry for energy, as you can see here. The amount of energy being consumed associated with the amount of computing occurring, but that's kind of linear these days. The more petaflops, the more energy. It's getting completely out of hand. And part of the answer to this turns out to be to decentralize all of that computing and invent a new way of computing that does much more near the edge. And so in the last minute or two, well, maybe 5 minutes of this talk before I take questions, what I want to do is tell you a little bit about what we're doing at Cornell University right now. And we involve a lot of undergrads in this work, by the way. If you were here, you could do this too, to try to understand the benefits of edge computing, the machine learning and AI techniques that can be used at the edge, and also to develop a new style of computing platform that can hold private data and let something compute on it in a scope, in a spot, and share the knowledge it gains, but not share the raw data it gains. So that might be a machine learned model it learned that can be used elsewhere, like to recognize commands I give to the house, but not share everything that the microphone heard. You see things like that, and which we would really have strong guarantees. So we're doing a project, we're calling it Cascade, and I'll show you really briefly the way it's going to work. And as I said, we've got undergrads working on this with us now. It's really more of a PhD research activity with me and my PhD students, but every one of us has at least 2 or 3 undergrads who work with us, and over time they become the next generation of PhD students. I've got people who were in my group at Cornell and now they're at Stanford, MIT, all over the place. So what Cascade is it, first of all, it runs on a laptop or a couple of machines, some kind of small cluster of computers. And here, in this case, it's a robot who's doing something for the farm, and it found this awesome thing, and it thinks it's a flower or a vegetable, and maybe it's what it's supposed to be looking for. It needs a little help, and it would talk to Cascade. And inside Cascade would be a bunch of programs running that are represented by these circles, the blue ones and the white ones here. And the idea is that we would use a style of computing that is common and very successful in today's cloud computing, the same thing that apps make use of when you use your iPhone or your Android and you're talking to something that has some of the data uploaded to the cloud. It's working this way too. So we would sort of overload that architecture, reuse it. And that means things that work there keep working there, which is nice and would work here. And so this robot can ask the cloud, what am I looking at? And it turns out in the cloud, the way that works is you have general purpose first tier programs that receive the request. They really build web pages and take web pages apart, and that's what this one's doing. And then it would talk to a service. This particular service has 9 computers spread over different nodes, and these 9 computers are sharing the work of applying a machine learned model to figure out what this robot's photo is of. And in this case, of course, it's a flower, but it looks a little bit like it could be a zucchini flower. And so it turns out you get kind of 2 answers maybe. It's a sunflower and very likely. And it could be a zucchini blossom, but if it is, there's something wrong with it. So it's pretty unlikely. And then the idea would be that this thing here knows a lot of stuff you could find on farms. And with the robot having the access to that, it won't have to use its own onboard power to compute. And the other side of it is we won't have to upload it to the real cloud because we're doing this at the farm or near the robot in a small laptop, and we're firewalling the data so it cannot get out. Maybe the robot has stuff it's allowed to send, like I found sunflowers that are ready to harvest, but the raw data won't escape and people can't hack in to get to it either. So this is what Cascade is going to do, and it's going to be tied to modern forms of machine learning on the one side, which come in software packages and languages that people are fond of. You've probably heard of TensorFlow. That's a Google one that they've been building. There are a whole bunch of these though. And it leads to an idea that the machine learning people are excited about, which they call distributed artificial intelligence, where instead of thinking in terms of one big AI at Facebook, you start to think in terms of lots of little specialists that do different types of machine learning tasks and AI tasks, and they can talk to each other, and we can analyze the resulting graph. That's supposed to be what we're seeing up here with these little lambdas representing the AIs. And this turns out to be a very effective model. Robotics researchers have been using this. Because think about my hand, if I was a robot, articulating my hand would mean models for the joints, models for the actuator. And so they've been building distributed AIs anyway. And then if I say, oh, by the way, I'm going to firewall these so that they can't export data they're not supposed to export, the robotics guy, there's no problem. And we can then move that over to smart home like Casper.ai, which is being built by a robotics guy. And they say, yeah, of course not. Why would we want to? And the real answer is, well, Facebook would want to because they want all their data in one warehouse, but that's where that privacy problem came from. And in this model of distributed AI, once we have an environment to run it in, a kind of an operating system, and that's what Cascade will be, it'll work just as well. And because it's very decentralized, we can take advantage of smaller amounts of locally generated power. And so we kind of benefit from all that micro generation of power that's occurring too. So we end up with new computing models, new computing ideas, and new ways to solve the problems. And then we can look back at elder care and we can say, are there opportunities that this opens up now that we can assure the client that this is a genuinely private system? And we also know that they're not going to read about huge data breaches from this kind of a system the way you do every day from the data warehouses. So that's what I'm excited about. And we start narrowly, and we do something like just for the elderly or just for a dairy farm. And then once we have something that starts to work, we build it out, and we can eventually bring other people in and say, we do open source software, and say, you can use our software too. We used it for smart farms, but if you would like to use it for a smart city, easily adapt it and we'll help you do it. And my group often does that right now. So we often do that. There's even a term for it in computing. It's called refactoring, where you take a general purpose concept that you used in a specialized way when you first built it, and then you generalize it and make it available to other people. And that's exactly the kind of thing we're going to do. So we're going to be building this. We're actually there now and starting to do things like cow face recognition and smart power grid stuff. And then we're going to refactor that into general purpose tools that people be able to look at our cow stuff and we'll say, oh, that's a demo. You can build one just like it for your setting. And by the way, it's privacy preserving. It won't export data up to some centralized system without very explicit rules that anybody can look at. And they can say, well, why are you exporting all the photos from my house up to your warehouse, Facebook? Well, you don't need to do that. And that'll be a legitimate thing to do. We can make it illegal to do those things. So I've worked on a ton of these kinds of systems. I mentioned these along the way, so I'll skip the list. And we think Cascade can help in all of these settings. We're really seeing a general opportunity here. And our friends who work in machine learning and AI, professors at Cornell and elsewhere, are coming to us and saying, this is a good fit for what we want to do. Let's try to prototype something and see if we can make it work. And we might even start a company someday. A lot of people who start out in computer science with ideas like this, over time, the students go off and they do start a company and the professors help them out. So let me stop on this last slide and say something about why it's a good idea to be a computer scientist. And it's a good idea even if some of the other STEMmy talks are way more appealing than computer science. And the reason is, and it came up a little teeny bit in the talk before mine, there's a sense in which the world is becoming very, very influenced, I'll say, by computational ways of thinking. We have to learn to use computing to do that. but things like protein modeling as a way to design new drugs that we were hearing about a minute ago. Well, even being able to think it is possible to do that is a form of computational thinking. But you have to understand what the tools are and how well they work and what they can do to be able to do that type of thing. And so I'm excited about computational thinking and its power. And I believe that you can find uses of computing systems in almost every setting. And they can be beneficial uses. We can do the part about preserving privacy and do the smart grid and reduce the waste of power. And we can provide elder care and not spy on people, and all of those kinds of things. We can get these things right. And so looking at the world and seeing opportunity for computation to improve the world, I think is just a super exciting thing right now, and a necessity considering where we are in terms of global climate change and in terms of the pandemic and future ones, right? And just in terms of the quality of life. I mean, imagine some farmer in India who's very much at risk if the river floods. Being able to warn that farmer that this year the river really might flood and your soils are very saturated, but here is a seed that you can plant that won't die if your field floods. And now that farmer doesn't lose everything in the flood that comes. Can you imagine how much impact we can have on the world if we can get to the point where we can do those things? So I hope some of you are gonna come to places like Cornell. It doesn't have to be Cornell. There are tons of really good schools right now in this area, and become part of this and help change the world, whether you do it as a computer scientist like me, or if you turn right around and become a biologist who really is an expert in using computing tools in biology, which basically is what we were hearing a minute ago. And I'll stop with that and take any questions you have. Now, let me see if I can figure out if people have questions, or you can unmute. What are the questions on chat? Is that how that's being done?
Yeah, most people are putting them on the chat.
So let me just find chat. I see one chat room.
I don't think there are many questions.
It says, sounds like Silicon Valley, the TV show. Yeah, it kind of does, doesn't it? But you know, it's real too. So anybody have any questions at all? How does the smart farm work? Okay, so I'll go back to that one. This was FarmBeats. It was being done by Ranveer Chandra, who's the chief scientist now for Microsoft's cloud computing unit. It's called Azure. And he also is the head of FarmBeats, and he was my PhD student. And what they're doing is they put humidity sensors. They also use drones, and with the drones, they stitch together images. Like the image we're seeing here was actually made by a set of drones that flew over this field in various directions. And literally, they learned to sail on the wind like a sailboat in order to preserve battery power. It's the coolest thing. And they stitch those images together, and they're able to use machine learning to recognize patterns of plant growth and of photo basically imaging. They're doing it in what's called multispectral imaging that let them tell if the soil is dry, if it's very wet, if various kinds of signs of stress are occurring. Then the drone can go close and look, and they can say, oh, this may be an outbreak of such and such a plant pest. And then they can dispatch a different system that will do a spot of application of pesticide at that spot. Or they can look it up and see if they've already treated that spot and this is just old damage. So a smart farm would have things like that. For the dairy, we're doing things like as the cows walk in, we photograph them from several angles, we correlate those photos together, and we figure out which cow it is. You would think that the tags in their ear would work, but it turns out that the tags the cows are wearing get really muddy, and RFID doesn't work well when it's caked with mud. And the cows are too close together sometimes, and so they get multiple RFIDs that scramble. So photos work better. So they just walk through this little corridor, and then it might say, oh, that's Becky, she's under treatment for a rash. Send her off on the right, the vet wants to have a look at her. Or we can just keep track of where she is in the barn so that when the vet shows up, we know how to go find Becky, which could be a challenge, you know, if there are hundreds of cows. So the smart idea of the smart farm is that you're putting cameras and sensors and computing all over the place. Now, then you can say, well, isn't this going to be super expensive? And in fact, what they're trying to do is arrive at the point where the smart farm has mobile devices. They show up, do things, and then go to the next farm just like you rent a tractor for a day these days. So that's the idea. Can I elaborate on the technical skills that are needed? Yeah, so when people come into CS, the first thing we discover is that a lot of high school students are already programming pretty well in many languages like Java, but they often have not thought about computation as a process and abstractly sort of how do you think about using computing tools and assembling them? Because, you know, if you're trying to build a system that might have thousands of computing devices, even on one farm, how do I organize that for useful purposes, right? And how do I take advantage of what already exists? Because a lot of stuff that does already exist. So the skill set has a lot to do with learning to think about what's feasible and not feasible with computing and how things can interoperate, and much less to do about programming than most people think. You do need math skills though. So computer scientists, without exception, turn out to be people who are quite happy with math and strong in math. Even if they're going to apply the work in other domains, they still come in with strong math skills. We do teach programming at Cornell, but much less of it than you would expect. But we have a lot of courses on how artificial intelligence works and so on. And that's mathematical at its roots. So the main technical skills are math skills. And the secondary skills, the engineering skills, are programming skills, but most people quickly acquire the programming skills. On the other hand, learning to build systems that are secure and private and correct is something that we can teach. A lot of people have struggled with bugs. Might be surprised to realize that at a more advanced level, generally, we don't make those mistakes. You can learn not to, and there are tools that will help prevent them.
Mm-hmm.
Any other questions?
Yeah.
Thank you, Dr. Bergman.
I heard someone else say thank you.
A little, yeah. Thank you so much for the talk. It was amazing.
Okay, I think you're not allowed to ask more questions. We must be out of time. Okay, it was great to join you, everybody. Drop me an email if anybody does have a question. It's ken@cs.cornell.edu, and I'd be more than happy to answer. Okay.
Thank you so much.
Drop out of this?
Okay. So now on to our next amazing speaker, who is a John Koch Distinguished Professor, Department Chair of Electrical and Computer Engineering, and Professor of Computer Science at Duke University. He is a fellow of ACM IEEE AAAS and a Golden Core member of the IEEE Computer Society. Today, he will be talking about the journey of a researcher and dive into the digital microfluidics biochips. Please welcome Dr. Chakrabarty.
Okay, hello everybody. My name is Chris Chakrabarty. I hope you can see my screen. Thanks for the invitation. I will talk about computational intelligence or computational thinking as used to bridge engineering with microbiology and biochemistry. We have been working on this research for over 20 years, and we have gone through the process of coming up with new ideas, writing papers, patenting stuff, starting companies, and commercializing products. I want all of you to close your eyes and imagine the possibilities. We're looking at the future and we have to dream. Whenever you start working on a cool research problem, you have to imagine first. You can open your eyes at the end of the seminar. Okay, all right. It's fun, but it's also difficult because we do not know what lies ahead. So this is a quick outline. I will walk you through some motivation, give you some background on what is microfluidics, how does biochemistry and biology interact with engineering and computer science, and then get into the technology and talk about some commercialization success stories. I'll play some videos. I hope the videos will play well. And then talk about some of the algorithms, some of the techniques that we utilize to do optimization, because in the end, we need to ensure that our biochemistry runs quickly. We can get our outcomes of diagnostics fast, and also the chips that we build are small and cheap. And then I would end the presentation. So what is our goal? Our goal is to enable benchtop biomolecular assays, which are protocols that chemists or biologists run in a lab. We want to miniaturize all of that and make it run on a small chip, a microfluidic biochip or lab on chip. This chip is programmable, so we can write software that can be used to control the various operations that run on these chips. So essentially, you see this picture here. where we have a lot of equipment in a lab, and we want to miniaturize everything and put that onto a chip. Of course, we cannot miniaturize the people. We can shrink them and put them on the chip, but we want to capture their knowledge and enable the same intelligence that is available in the lab to be available on these chips. We want to keep these chips fairly simple because the users are not going to be computer scientists or engineers, but rather they will be doctors and nurses and technicians. But we want to enable realistic biochemistry, some real operations that can be run on these very simple chips. So we're seeing a paradigm shift in biochemistry. Basically, we used to have complex operations, microwell plates, a lot of test tubes, milliliter volumes of fluid, and we needed skilled technicians who had to be trained. They were prone to making errors, and bulky equipment that needed space and needed a lot of money to be acquired. Now we can do what is called lab on chip. So we can integrate a lot of components, reservoirs, wells, channels onto a small chip the size of a PCB. This is called lab on chip. And why do we do this? Well, these are very small. So miniaturization helps in decreasing the amount of fluid volumes we need. And volumes are important because the smaller we can go, the faster we can run our chemistry. And the cost comes down if we can decrease the volume. Automation, less chance of errors. We can write software that can control these devices. And very high throughput, we can run lots of reactions in parallel. So very high throughput means that we can detect various conditions in a large number of people in a very short amount of time. So what is a biochip? I'm sure most of you haven't heard of this term before, so let me walk you through that. This is a miniature, so small, disposable. That is important. This is not meant to be used for a year or 2 years like your cell phone or your laptop. This is meant to be thrown away. So it has to be very cheap. And it does very high throughput sequencing or high throughput screening. So it's basically an instrument that does lots of things in parallel. What does it do? Well, all the chemistry that you are learning now in your classes in high school or in college when you will take chemistry, you would learn about dispensing, which is, you're going to be using micropipettes and your thumb will hurt because you'd be filling up test tubes with your micropipettes. Mixing, you would shake your test tubes to look at change in color. Does a gas come out? Is there a smell? Do you see some light? That is called detection. And then in the end, you throw away the content of the test tube safely. So we can do all these different things on a chip, but a lot cheaper and a lot faster. So this is the thing what a biochip basically does. So the main types of biochips, well, the first generation was passive. These were called microarrays. Essentially, you had a substrate of silicon or plastic or glass. And on the substrate, you would attach what is called a probe. And a probe used to be basically some DNA or protein. And then you would have to do a lot of the sample preparation and all the steps necessary in advance manually on a bench top, and you would then introduce a prepared sample onto the substrate, the microarray, for the final step of binding. So there was something called hybridization. You would have binding between complementary base pairs on the probes, and based on that information, which you could extract by shining light onto the substrate and doing some signal processing, you would know what was in your sample. Now, what we are looking at is lab on chip or active systems, micro total analysis systems or microTAS, where a lot of these functions are done on the chip itself. We do not need as much human in the loop. We can control the liquid flow. We can provide mechanisms for inputting samples and reagents. We can do pumping. We can do separations, even sensing. We could integrate all kinds of sensors to detect the endpoint of the reaction. Now, I mentioned cost, and this is a very important question because when you are running these reactions, you may not think about it too much, but cost matters. And you can see right now with the COVID pandemic, there's a lot of talk about can we run so many tests for so many different people because cost is a problem. This is a chart from EPFL. This is a Swiss university. And in the x-axis, you're looking at the cost in Swiss francs per unit weight, per gram. And you're looking at different materials. So copper, which is our interconnect in most of our integrated circuits today, in chips that we have, your Intel chips, for example, use copper interconnects. Copper is very cheap, so it's on the bottom left corner of the screen. And then you have silver, a little more expensive. Gold is more expensive. You make jewelry out of gold, and platinum, more expensive. Sapphire, diamond are even more expensive, right? But if you think about the antibodies that we utilize for doing all kinds of reactions, they are way up there. So they are more expensive per gram than even diamond. Okay, that is why we need to find techniques so we can reduce the amount of volume that we need. So when you're thinking about getting engaged and you want to buy a diamond ring for your fiance, tell your fiance that, why diamond? Take antibodies. They're more expensive than diamond, right? Okay. So anyway, I wanted to make the point that volume does matter. We want to therefore run reactions not with milliliters, but with microliters and nanoliters of volume of fluids. So let's now look at microfluidics. This is a bridge. This is the technology that enables us to miniaturize and run reactions on a chip. So in the test tube world, in the old days, everything was large. We had milliliter volumes. There was no automation, no integration, and no miniaturization. You can use robots. There are methods based on robotics where you can program a robot to basically pick up samples and reagents and place them elsewhere. So this gives you automation. It's overall integrated system, but it's very bulky, very big. So you can't really make it portable. You can't run these tests in the field. With microfluidics, you get all the benefits. You get automation. You can run software to run these devices. It's all integrated. Everything is in a very small package, and things are small. So let's quickly look at the different technologies of microfluidics out there. So the older technology is based on continuous flow, where we basically have a substrate on which we can etch microchannels. So here you see the serpentine channels. You can have sensing as well. You can have all kinds of different shapes of the channels. The problem with this platform is that you cannot make these things very small. So if you make these things very small, the pumps or the electroosmotic fluid mechanisms, flow mechanisms, they tend to have reliability problems. And also the fluid flow can only be along these channels. So it's not reconfigurable. Instead, we have been looking at a platform where we used a patterned array of electrodes. So think about it as a XY coordinate system, and you have these electrodes arranged in an XY fashion. Each one can be accessed from an input pin. You can assign to it a voltage level, a high or a low voltage level. So that allows you to turn it on or turn it off. And the liquid is now transported in terms of droplets. Think of that as a packet. So this is the packetization concept. We're going from an analog world where we had continuous flow and analog signal to having individual bits. Think of a droplet as a bit of information. And this droplet can contain DNA and protein, can contain reagents, can contain samples. So this is my payload. And by turning on and off these electrodes, I can either hold a droplet at a specific location, or I can make it move. I can do all kinds of interesting things. So this is called digital microfluidics. And the rest of the talk, I will be focused on this platform. So let's look at the science behind microfluidics or droplet-based microfluidics. The basic physics is called electrowetting. The concept goes back to the 19th century, not a new concept. And the idea is that when you have a droplet that is very tiny in volume, you go down to the nanoliter or even smaller picoliter volumes, the bulk forces are weaker than the surface forces. The surface forces start to dominate. And now if you have an electrode, and on that you have a thin insulator, and on the top, I have not shown in this picture, there is a very thin hydrophobic layer. So you coat it on top of the insulator. Now if you bring a droplet of liquid, which is very small in volume, because of the surface forces being dominant, the droplet makes a nice spherical shape with a large contact angle. If I now apply an electric field between the electrode and the droplet, it basically changes the surface from being hydrophobic to hydrophilic, and the droplet now wets the surface. Okay, so essentially there is some energy being introduced into the system, and the energy would be modulating the surface tension, the surface forces, and the droplet would wet the surface like this. If I now take the electric field away, the droplet would bounce back to the original position. So this is the nice thing about the system. So you can think about the voltage as a high or a low voltage, a 1 or a 0, and that can be used to change the state of the system. So I'll show you here a video of a droplet on a surface. When I start the video, you will see that there is no electric field. The droplet stays there. Then after a while, you will see one oscillation. And then if I increase the frequency of actuation, the droplet would move faster. So let us see how this movie looks. So this is the first time. And now I'm doing it with much higher frequency. And you can see the droplet going up and down. I can now go from having a droplet which is going up and down to making it move in a lateral fashion. So from this picture here, continuous electrode with a droplet on the top, I can have now multiple electrodes with gaps in between and a top plate, which is permanently kept at voltage level 0. Now, if I want to hold a droplet at this location, I would apply a high voltage in the middle, and I would apply low voltages on the two ends. So think of this as a 0, 1, 0. There's no net force on the droplet. It will stay there. If I want to make it move to the right, I would apply a high voltage on this electrode here on the right and a low voltage on the two other electrodes. So that means I have a 0, 0, 1, and that exerts a net force to the right, and the droplet will move. And the same way I can make it move to the left. So this is a video of looking at it from the side, and you will see a droplet marching left and right. There you go. So we're just adjusting the voltages on the electrodes. We don't need any pumps. It's all electrical. Just control the voltage levels and you can make the droplet do all these things. Now, there is one interesting caveat here. Because the volume is so small, there could be evaporation. So we have seen experiments where after a few minutes, the droplet just disappeared. Poof, where did it go? Well, it evaporated because it is nanoliter, picoliter volume. So we have to use a film of oil. It's an inert silicone oil that prevents evaporation. And also it prevents cross-contamination, because if you're transporting large molecules, DNA, protein molecules, they may stick to the surface and cause contamination. So when you use oil, you eliminate the chances of contamination. You can now think about this from a computer science perspective as a finite state machine. So the system has a state, which is basically an n-bit vector. N is the number of electrodes, and each vector is 1 or 0, whether the electrode is turned on or turned off. And anytime you make a droplet move, you are doing a state transition. The system moves from one state to some other state. Okay? And you can move multiple droplets at the same time. Each droplet consumes only 1 microwatt of power. So we can have 1 million droplets being simultaneously actuated, and the power consumption on this chip would be just 1 watt. Okay, so next, I will show you a view from the top. Looking down on this array, a droplet is going to be routed to the east, north, west, and south, and very quickly. This is actual speed. This is not simulation. I have not done any adjustments. This is the real speed at which I can move a droplet. You can see that the transportation is very rapid. Then I will show you 2 other videos. The first one is actually inputting a droplet into the system. So this you can think about as the interface to the outside world. The outside world is not droplet. The outside world is bulk liquid. You have large volumes. So you can have a reservoir which can be filled with liquid. And then what you can do is you can inject a droplet into the system by controlling the voltages on the line of electrodes here. I can control the voltages here. So I can start with a 1 here and a 0 there. Then I make this 0 and make this 1. And as I do that, I would create a neck, and I can break the neck, and the droplet would enter the system. So this is my basic input operation. Think about this as an A to D converter, analog to digital converter. So you can see that I can with very high accuracy, I can inject these droplets. And we have done this billions of times, and we are seeing less than 0.1% volume variation. The next video is a dance. Basically, there are now multiple droplets. Each one is being controlled very precisely by software so that they can move around simultaneously and they don't have any accidents. They don't collide. We can track them very precisely. So there you go. This is a choreographed dance of droplets. Okay. Now, what this tells us is that I can run multiple reactions on the chip at the same time. I can do multitasking. I can do parallel processing. This is like pipelining. We can run different threads of control on this chip at the same time. So of course, this was very attractive. We got a lot of interest from companies, and we basically started our own company from Duke. It was called Advanced Liquid Logic. And around 2011, this was one of the early products. So this was the PCB platform we had fabricated. So the reservoirs are on the edges. These are for the various samples and reagents. And then we had electrodes in the middle for transporting the droplets and doing incubation mixing. And then there was a sensing area. And then the package would be placed here. This was the instrument. And the instrument had power supplies, control software, memory, all built in. And the user would see things on the screen. So this was not a very small chip because it was a PCB device, but it was actually of great interest to 2 counties in Illinois. There were 2 counties that mandated that every newborn in their hospitals was going to be tested with these chips. So during that period, the company was selling 5,000 of these chips a day. Now you may think it's a very large number, but these are very cheap chips, right? You throw away, so there's not much of a margin. But still, it was great to see so much interest in these chips. And then there was an acquisition in 2013. Illumina, which is the world's largest DNA sequencing company out of San Diego, they bought ALL. And at that time, their senior VP said that they were going to be using this technology for the next generation sequencing workflow, which means they will use it for sample preparation. So for sequencing application, you have to prepare your samples in a whole range of concentrations, even the reagents. So 1 molar, 0.5 molar, 2 molar, and then you need to have the library created so that you can use it during the sequencing. And this is a very tedious process. So if they could automate that using our chips, that would be great. Now, very quickly, within a year, they transitioned this to a product, and there was an announcement in 2015. Illumina announced the new prep library system that essentially uses these chips. And I'm going to show you a video from Illumina. I hope the sound would work out okay. Let me maximize the sound here. And let's hope this plays well. So you're seeing here a scientist, and she's very tired from working very hard on all these things, and she's going to wipe her brow, and then she'll look up and see light, and then you'll see that the lab on chip come into play. She's tired, exhausted. So you can see that we went from research to commercialization, and there was a product in about 2 years. And then there is a company called GenMark that has also licensed this invention, and they are using this for nucleic acid extraction, amplification, and detection, all done in 2 minutes of time. They have a platform called ePlex, and I will play a video from them.
GenMark is pleased to present the future of molecular diagnostics. ePlex, a sample-to-answer multiplex molecular diagnostic system, delivers laboratory efficiency and rapid comprehensive clinical results for clinicians and patients. ePlex features enhanced workflow, enabling optimal use of staff time. Simply load the patient sample into the cartridge. Scan the cartridge barcodes for positive sample identification and load the cartridge into any bay. The visually appealing user interface is intuitively designed to meet the unique needs of laboratory professionals. The fully integrated cartridge contains all required reagents, simplifying sample preparation. ePlex fully automates molecular testing, including sample preparation, extraction, amplification, and detection to deliver rapid sample-to-answer results.
So as you saw in that movie, they are able to move these droplets really fast, much faster than you can do at the university. And this is pretty common because once you commercialize, you have to make a product, and a product is of course a lot more effective than the university prototype. Okay, so with that, let me move to the next part of the presentation, which is about how do I optimize these systems? Because in the end, my goal is to complete my reactions in the shortest possible time using the minimum possible volume of reagents and sample and ensure very high reliability. So you can think about this now in terms of algorithms. So we are talking about a specification of the biomedical assay. What do I want to do on these chips? So I take some samples and from a patient like plasma, urine, saliva, and then I would do all kinds of assays or tests on those samples. I could do them one by one, but that is very slow. Instead, can I do them in parallel? So I can think about doing an architecture level synthesis where I find out more or less the top level chip plan, and then look at the macroscopic structure, look at the scheduling problem, in what order I run the different fluidic operations, the binding problem, which basically says to what unit on the chip do I map each operation. And then I look at the microscopic structure, the actual layout. Where do I place the different modules, what kind of routing I do, and I get the full layout of the chip. Okay. So essentially, I'm talking about two kinds of engineering problems. One is called fluidic level synthesis, and the other is doing the actual chip design. So I'm talking about the sequencing graph model. I have to formulate the problem in terms of some mathematical construct. And the construct we're using here is actually a graph model. Every node is an operation, and the edges indicate that they should be done first. So which one gets done first? And then I'm talking about scheduling. So this basically tells me in what point in time different operations get scheduled or run, time assignment. And then I look at the placement. Where do I put the different modules on the chip? What kind of transportation pathways do I use to transport the droplets? And then the chip level design, basically what I have is I have the electronics going underneath the microfluidic layer. I have the fluidics on the top, and below that I have the wiring that is used to control the electrodes. So I need to know which electrodes get utilized at which point in time. And then I have to think about my control pins. I have to now add IO pins to the chip so that I can use these IO pins to provide the voltages to turn the electrodes on. And then I have to do the actual wiring, connect the IO pins to the various electrodes on my device. Okay, these are all very interesting problems in engineering. There are algorithms we can come up with to do optimization. A problem that I want to showcase here is about droplet routing. So routing is the problem of transporting droplets from point A to point B in the shortest possible time. Now, if you think about VLSI or very large scale integration or in ICs and chip design, we also do a lot of routing. We have wires. We lay out wires that can connect point A to point B on the chip. So in that sense, the problem is similar to interconnect routing in complex chips, but it's not the same problem because if you look at a VLSI chip, you have an actual wire. But when you look at microfluidics, it's a virtual pathway because there's really no wire. I can program the electrodes to act as a transportation medium. Once the droplet is transported, I can reuse these electrodes for doing other things. So we think of this as the problem of routing of trains. When you have a train being routed, the tracks can cross each other. That's fine. That's not a problem. But the trains must not come at the same time at the intersection. So we must have control mechanisms to guarantee that no two trains would collide at this intersection. So we do the same thing here in droplet routing. A second problem is about pin constrained optimization. So I may have 10,000 electrodes or even more on a chip. And ideally, I would like to control every electrode by an independent pin, but that is impossible because the IO pad frames are much larger than the electrodes. I really cannot have 10,000 pins on the chip. So I can probably do only about 1,000 pins or 500 pins on the chip, but I should be able to use them to control all the electrodes with no impact on throughput. Okay, now one option is I can move one droplet at a time, and then I can have a small number of pins, but that is too slow. So I would like to therefore have very high throughput and find a way to do parallelism. So one way is to use what is called cross-referencing. I basically use X and Y coordinates to control every electrode. So instead of having an n by m, I have n plus m, n rows and m columns. Okay, so use row and column addresses for every electrode. So think about this as an array. I have 10 rows and 10 columns. I have 3 droplets on the array, and I want to move 1 and 2 as shown. So to do that, I have to turn on the columns and the rows. The destination rows and columns get turned on, and that would allow the droplets to be moved. But I have destination cells. I have unintentional destination cells. When I move 1 and 2, I also move 3. This is a problem. So the question is, if I have many droplets like this on the array, 9 droplets, do I need 9 steps to move them one by one? That is very slow. Or can I move them in parallel? Can I find a way to move as many of them at the same time as possible? Now, this problem can be modeled in terms of some mathematical framework. The question is to find an optimal grouping plan. So put these 9 droplets in groups so that all the droplets in the same group can be moved at once. And the number of steps you need is equal to how many groups you have formed. So the insight we can draw here is that we look at the destinations. If 2 droplets have a common destination row or column, then we can move them at the same time. Okay, this is the insight we get. Once we get that insight, now we can go from biology and chemistry to computer science and mathematics. We can draw a model. This is a model of the array, and the model has nodes and edges in a graph. Every node corresponds to a droplet, and 2 nodes are connected by an edge if they have a common destination row or column. Okay, so for example, if you look at this graph here, 1 and 2 have a common destination column. Therefore, you have an edge between 1 and 2, but there is no edge between 1 and 5 because they don't have a common destination row or column. So I first draw this graph, and then I do a clique partitioning on the graph. A clique is a maximum subgraph, basically a graph where every node is connected to every other node. And this is a very well-known problem in graph theory. So I will do a clique partitioning. The number of cliques I have in the graph tells me how many steps I need to move the droplets. And all the droplets in the same clique can be moved at the same time. So in this particular case, we need 3 steps, and not 1, not 9, but we need 3 steps to move the droplets. You can also think of this problem in terms of what the voltages you need for the electrode. So we have talked about 1 and 0. There's also a third level, which is called an X. I don't care. For example, if I have a droplet which is to be kept here, I need to make sure that this is 1. The neighboring electrodes must be 0. But the one here, I don't really care. Can be 1, can be 0. So it's an X. So now if you think about the actuation sequence over time, essentially you have these 9 electrodes as shown here. Sorry, there are 8. This one is not marked. You can think about this over time, a sequence of actuations, and each vector is consisting of 0, 1, and x. Now the question is, can I map the x's intelligently to 1s and 0s so that I have as many columns being identical as possible? If 2 columns become identical, then I can control those 2 electrodes with the same input pin. Okay, so I need to therefore find a way to map the x's such that the number of distinct columns is minimized. Okay, and this can also be mapped to a problem of clique partitioning, or in graph theory, every electrode can be modeled as a node in a graph, and I have an edge between 2 nodes if the 2 nodes are compatible. And what that means is that in any time frame, in any row of this table, they don't have opposite specified values. So for example, here in the first cycle, this has to be 0, this has to be 1. So this is incompatible, and therefore I cannot have an edge between those 2 nodes in the graph. Okay. So I look at compatibility, I create the edges, and then I do a click partitioning on the graph. The number of clicks on the graph tells me how many input pins I need, and all the nodes in the same click can be controlled by the same pin. Okay. So you can use a very nice algorithmic method to do optimization on these chips. So with that, I come to the final few slides. So what I've given you is a flavor today. Digital microfluidics offers a very attractive platform for doing lab on chip for clinical diagnostics and biomolecular recognition. We are using a lot of automation methods from computer science, from algorithms, so that we can control using software, the droplets, and doing the reconfiguration. I talked about some commercialization success stories. There are products now which are using these kind of chips. Some numbers in case you're interested. So we have been able to work with 11.4 volts to dispense droplets and 7.2 volts to transport them. These are the smallest voltages we have used. We are using different materials as our hydrophobic layer and insulator. The smallest chips, we can work with 12 picoliter droplets on 33 micron electrodes. And we've also done 5 picoliter droplets on 21 micron electrodes. So the final slide is, we now have a biochip ecosystem. So on one side, we have the folks who are building the chips, who are actually doing the chip fabrication. And then we have the users, the different medical diagnostic labs, nurses and doctors. And then we have software. So this is the bridge that is connecting these two entities and allowing us to make the best possible use of these chips. Okay, that is the end of my presentation. Thanks a lot. Let me see if you have any questions. Let me stop sharing and check in chat. I see one question in chat. Is that for me? No, that's not for me.
I have a question.
Yep, sure, go ahead.
Do they do any of this digital microfluidics research somewhere in the Bay Area or California?
Yes, so this is a research field which is fairly large now. So there is ongoing research at at Stanford, at Berkeley, at UCSF, and there are companies as well, mostly spun out of university labs, which are looking at further commercialization. So yes, the answer is that these are not in large companies. You don't see this advertised in the front, but if you look inside their corporate labs, they have ongoing activity as well.
Okay, if that's all your questions, thank you so. Oh, there's another one. We are running a little bit low on time, and I know Dr. Chakrabarty, you also have another commitment. So we're going to move on to the next speaker.
Thank you very much.
Vasila Petrascu. Thank you so much again, Dr. Chakrabarty. So let me spotlight. Give me a second to find him. Oh, found. Awesome, everyone, please welcome Vasila Petrascu. He's a principal engineer at Jitterbit, responsible for driving the design and implementation of the next generation of cloud integration products. A lot of words. Vasila Petrascu graduated with a bachelor's in computer science from the University of Bucharest and went on to work as a senior technical lead at IBM and Cast Iron Systems. Without further ado, please take it away, Vasila Petrascu. We can't hear you. You're muted.
I'm sorry. I've been using the Zoom product and I'm still making the same mistake. So thank you, Diana, for the wonderful introduction. It's 2 o'clock Sunday Pacific time. Thank you everyone for sticking around, and also a big shout out to the organizer for putting together this this wonderful conference, and big shout out especially to Diana. I put together a few slides so that we can have a context to talk about what does it mean to, how does the life of a full stack developer look like, right? And hopefully we'll have some question at the end. Let me go ahead and share some of the presentation. All right. Hopefully, yeah. Okay, so you guys can see it. Just a quick introduction for myself. Obviously, principal engineer at Jitterbit with more than 20 years experience. Jitterbit, it's a data integration company that basically moves data between various systems. So I have a little agenda that I want to talk about. So the first one is how do I get into computer science? I'll just spend a few minutes, and then I would like to talk about life as a full stack developer. And usually I like to talk about a typical day. What is a typical day as a full stack developer? And as part of this topic, I will also cover what is a full stack. And this is just my view. What does it mean to work on a full stack? What actually a full stack is, which I'm sure everyone knows what a full stack is, but what really is, what are the components? And then hopefully we're gonna we're gonna have enough time for Q&A. How are we doing on the time?
So right now we're like 45 minutes behind, but you can take.
All right.
Yeah, you can just take as much time.
So how they got into CS, into computer science, right? Everyone experienced and how they got into a career. It's obviously unique. And I would like to say that, hey, computer science chose me, but that is not true. And to be honest, I don't even remember when I was asked this question. When was the last time, actually, or even if I asked this question. But regardless, I had to dig into the memory to figure out how they got here, actually. And I think everything starts for me with middle school. When I started middle school, actually, I wasn't very good at math. But I had an amazing teacher, and she was very good at she's very good at inspire a lot of passion into you and get the best out of you and get the best out of me when it comes to math. And by the time I finished the middle school, I was really good at math. I enjoyed solving problems, and the same passion carried over to the high school. However, as I got into the junior and senior year, what did I wanted to do was becoming fuzzier and fuzzier. But one thing that I knew that I want to follow on the math path, but also I knew that I didn't want to follow other career like being a biologist, follow medicine, or being a lawyer. By the time I got into college and got accepted to the math faculty, it just happened that I think a few years before they added a new major, was called informatics, which is the equivalent of computer science. And I had to decide until the end of the first year to decide if I want to continue on the math path and follow a career in teaching or maybe researching, or actually switch to the computer science. I knew that I didn't want to follow a career path into teaching. So now you have to imagine that this is the end of the year. I've seen computers only in movies and probably had no idea how to turn off a computer. And I still made a decision to actually go the computer science and switch the major. And obviously I realized that being relatively new, this is gonna open up a lot of opportunities, but also it's something that was challenging to me, something that I haven't done before. And that's how I got into. I mean, the big takeaways is sometimes knowing what you do not want to do, what career you do not want to follow is as important as knowing what you want to do, what career you want to follow. And obviously, what I would say is be open to opportunities, be open to challenges. You may not know now, but you will figure out later. All right, so let's go to the next slide. So I want to talk about the full stack developer in a typical day. But before that, let's talk about the full stack. What is a full stack? In general, a full stack represents all the components, all the layers that make up an application. When we're talking about application, it's really referring to a web-based application. And usually people, when they refer to a full stack, they refer to the front end, and we're actually, you're doing the UI of the application, and then they're referring to the back end. Now, what I want to explore a little bit those two layers and dive a little bit more into and see what kind of technology actually are being used at every layer. So you have at the top of the stack, you obviously have an application. Usually it's a web-based application that uses HTML, CSS, JavaScript technology. This application actually can be packaged as a mobile app, or can be packaged as a desktop application, or even you can access it through the browser. And one sample of such application, which I'm sure everyone is using, is Slack, right? Everyone is using Slack. You can go on your phone, you can download it, you can go on your on the desktop, download it as a desktop app. What behind the scene, the application itself, even though it seems, when you download it on your phone, it's a mobile application. In reality, it's built using the HTML, CSS, JavaScript technology. Now, in the recent year, the developers actually, they start using frameworks like Angular that allows you to develop what they call single-page apps. And those single-page apps actually mimics the desktop application behaviors, right? So that's one of the things that it's happening, and that's really what the industry is going to. Now, as you go down the stack, there is the app server. This is really where the business logic of the application gets encapsulated. Usually you would use the same language, right? The one that you use for the web-based application for the above layer. For example, in our case, we're using Java. We're using TypeScript and Angular for the application layer, for the web-based application layer or the UI layer, but also we're using JavaScript and TypeScript for the app server layer or the backend. Definitely, it's not a requirement. Others are using Java. Depends on the requirements, or they're using languages like Python, PHP, or even Go. Now, as you go down, there's another layer that not a lot of people talk about it. This is what I call the data store layer. Usually, where you're storing data either for a short period of time, or you store it for a longer period of time. As part of the data store layer, you might have messaging layer, which it's in general it's used for storing messages for a short period of time, and it's storing for queuing tasks maybe, or you want to check out later. It's also used for communicating with other services in your stack. So your app servers actually, it's a series of services, and those services needs to talk to each other. You might have a login service to allow the user to log in. You might have another service that does the credentials. Those applications may use the messaging layer to communicate among each other. As part of this data store layer, you might have a cache layer for performance boost. And in general, the cache layer will store the most used data that application uses. And this data will be stored in memory. And of course, if you want to store data for a longer time, you would use a database. Usually you'd use either a traditional database like a SQL database. If your data is modeled as a relational model, or if, for example, if you want to support high volume transaction, you'd use something like a NoSQL database like MongoDB or so. If your application has a need for search, you probably most likely end up using something like Elasticsearch database, which is a NoSQL database, and it's very suitable for searches. So this is the data store layer. And as you go down, obviously you need to run all these things somewhere, and usually you deploy to an infrastructure, right? To one of the cloud providers like AWS or GCP or Azure. Most of the developers actually like to run the entire things on their local computer if possible. Sometimes it's not possible, but most of the time it's possible, and they'll make it happen. So you can think about, now you can think about the full. So the general notion is that the full stack developer will work only on the the top two layers, the web-based application and the app servers, but also they need to have knowledge about data store. They need to have knowledge about infrastructure and how to deploy their application and so on. All right, let's see. I'm going to stop for a second, see if there are any questions. In case there are questions, I'm more than happy to answer as you go. If not, it's extremely hot in California today, and the air conditioning is not working the way it's supposed to. All right, so let's get going. A typical day. Well, before starting actually talking about a typical day, just want to mention a couple of things. Our development team, the one that I'm part of, we follow the agile software development, specifically Scrum. And Agile, also known as Agile, you're probably going to hear that. This really has been adopted by the industry a few years back. Before that used to be the waterfall model, which now is not used anymore. But Agile is really focusing on individuals' interaction over processes and tools, customer collaboration, and responding to changes. We are using Scrum, which is the framework in which our dev teams, our development team operates. And probably this is the standard anywhere you go in the industry. And usually the Scrum team will be made of the product owners, or we call them stakeholders, and of course the dev team, and sometimes you have a Scrum master. And usually the Scrum starts with planning. When you're planning, you as an individual contributor, you're committing to certain tasks to be done during the sprint, and sprint lasts for about, on average, 2 weeks. In our case, it's 3 weeks. And at the end of the sprint, you'll have a release so that you can get the features to the customer sooner than later. You have a retrospective where you talk about things that, hey, what worked, what didn't work, how can we improve? And of course, things that you haven't been able to finish will go in a backlog. So those are kind of the I would say, the framework in which our development team operates. And in most situations, all the development teams operate in those two frameworks, subscribing to Agile methodology and also using Scrum as the framework to really operate. And it's all about being as nimble as possible. How can we deliver features quickly to our customer? How can we be predictable in the things that we're doing? So we know when we check in the sprint, yes, this is where we are, and we can commit the features to the customer in the time given. Now, let's talk about a typical day. This is really what a typical day looks like for most of the developers, I would say. It may sound boring, but there's a lot of things, obviously a lot of nuances that probably are not captured here, but I'll try to capture them as much as I can. So we start with daily Scrum, also called daily stand-up. Usually this is, when the team gathers, give status, what you've done yesterday, which task have you worked, and what you'll do today, right? What task you're going to work on, any issues that needs to be addressed. And usually, if there are any issues, those we're gonna talk about them at the end of the daily Scrum, and usually I moderate those discussions so that we can get to the right solution. Most of the time, after the stand-up, there is a sprint progress where we're keeping track of the progress using Jira. As a team, you have to know where you are in the sprint. You have to know if you can deliver what you committed to. So, or if in certain situation you have to adjust and actually change the plan, you have to be agile. And then everybody goes about the day. They start developing and working on their task. So they may write code. People, in our case, we're writing code on the front end. We're using Angular and TypeScript. For those of you who doesn't know what TypeScript is, it's really a superset of JavaScript, very similar, but it's typed. Obviously, Angular, it's a web framework that is being very popular. It's one of the popular frameworks out there. Angular, React, Vue, I've seen, but definitely Angular. It's It's one of the popular one made by, I believe, Google. And then on the back end, you would use the same thing. You develop write code for the back end using the same technology, TypeScript. Sometimes you have to do Java or maybe other languages like C++. Just as a side note, anyone who wants to go into computer science, most likely they're going to learn and use more than one programming languages. The important thing is once you learn one language and once you learn the fundamentals and the concepts, everything is coming natural to learn. And the interesting thing is that even though they are different, sometimes you have to, when you're writing code in a specific language, you have to write code the way the language has been designed to. The same way you speak in a language, right? All right, so, and then obviously after writing code, there is the part where every code that you write has to be unit testable. Making sure that all the scenarios are covered, by the time it gets to the customer, your code is bug-free. The reality is that's not necessarily true. You may have situations when things are slipping away. And then, of course, testing whatever feature you work on, whatever bug have you fixed has to be as well unit tested and tested. Let's see. This is an interesting thing. If you're running into issues, if you're running into a problem, usually what we do, we ask help on Slack, right? Like anyone else. Most likely, the interesting thing is that if you're running into a problem that nobody can help you from your team, probably somebody else have already run into, and there is a good chance that you may find an answer if you either, using the search engine or if you go to Stack Overflow. So the search engine, without naming one, is probably one of your best, is going to become one of your best friends. But the trick is you have to know what is it that you look for. The search engine can help you so much, but if you don't know what you're looking for, then it's going to be a problem. Obviously, the collaboration between the team happens on Zoom and Slack. There's a lot of things that we need to talk about, especially today when remote work has becoming, when the work has become remote, it's becoming more imperative, the collaboration, and we're trying to stay in contact using those two technology. And the other thing is going to happen is that once you're done with your work, what's happening? Well, usually you want your work to go in the main branch so that it's going to go to, eventually it's going to get released and the customer is going to see the changes. There is a process where you're doing the pull request. Those of you familiar with GitHub probably are already familiar with the pull request, where you're asking essentially your changes to get into the main branch. Those needs to be reviewed by your peers, and once they get reviewed, they will get merged, and there is a process that the team has built where things are getting automatically deployed and pushed to one of our environments for either testing or releasing. And then, of course, there is meetings. We try to keep those meetings at minimal so that the work is not disrupted. Writing code, it is a creative work and requires a lot of skills, and we try not to interrupt somebody because you have to switch context. Just think about it. One thing can be written by multiple guys different ways. So it is really a creative work. We try to keep meetings as minimal as possible. It's not always possible, but that's kind of a typical day. And let's see. All right, I have one more slide that I want to talk about it. So it looks like I'm on time. Actually, I wanted to allocate about 10 minutes for Q&A and see if there are any questions. Let me talk about the next slide, and then we're gonna go to the Q&A. Usually for me, there is a non-typical day as well, where there is things that I have to take care of, but that's because besides the normal responsibilities as a full stack, also I have other responsibilities. Obviously, customer interaction is important. Without customer feedback, you wouldn't know, and you wouldn't know how to prioritize the improvements on your product, right? You want your customers to be happy and enjoy using your product. Another responsibility is architecture. I'm responsible for the architecture of the stack. Stack is something that evolves constantly. There's always room for improvements, and there is things that you have to answer. Can the stack auto scale when there is a spike, when there is a load of the number of requests of the volume, when the volume of transaction increases? Is the stack reliable? What happened when, for example, one of the layer doesn't work? The database, you can't communicate with the database. Are you able to still properly return a response to the application? All these are important things that we have to take care of. If there is an outage, right? How do we know? How do you notify the customers? Are you getting notification? So those are all things that we have to take care of, and of course, and be on top of it. Things like the stack. Can the stack self-heal itself when there is an issue? Those are important things that we have to answer, and we have to make sure that we are ahead of the curve. The other thing is, which I think is very important, how do you keep up to date? The tech industry, especially in the Valley, it's a very competitive industry, and changes extremely fast. And it is important. It is important to see where the industry is going. What's the trend? You may not notice, but definitely, just I want to say Slack, probably Zoom wasn't around 20 years ago, and in less than, probably was around 7 years ago, maybe 10 years ago, and just in a few years everything changed. So the way we do it is, you gotta read a lot. You gotta go to conferences, make connection with other people. When you go to conferences, see what problem they run into, how they solve, exchange experience, figure out what's new on the market, and learn as much as you can from other experiences. Blogs also, it's another things where you can learn a lot of things. If you run into an issue and you Google it, to figure out what other people have solved it, most likely you're going to end up reading a blog, and suddenly it's like, yeah, there are some other people that most likely are smarter than you, and there's no shame in actually learning from those folks as well. And of course, there is Meetup, there is friends in the industry that is sharing this information with, and so on. And the last thing is mentorship and leadership. My team, or our team, I would say, it's a very young team, a brilliant team. They graduated, maybe a couple of guys, they graduated a year ago, others they graduated 3 or 4 years ago. You have to really work with them and mentor them and help them with their career and achieve their goals as well, right? There's one thing that I've learned, and I don't know who said that, there is no compression algorithm for experience. That's something you cannot compress, and you just have to go to those stages to get to where you want it. And at least share your experience. The guys that have more experience than others, share the experience with them, and so that they can learn. That's kind of what I have as far as, okay, so I'm on time, 20 minutes. Now I'm just gonna do a Q&A, since if there are any question and answer that I could,
I actually have a question, but before I ask it, Dr. Graham, are you here? I think.
Yes, hello.
Oh, hi. Okay. Just give us a few minutes for questions, and then we'll transition to Dr. Graham.
Thank you.
Okay. Okay. My question was, how many hours do you code a day, like on average?
I wish it would be an average. I get that asked a lot. It's sometimes could be 10 hours, sometimes could be 1 hour. It's, sometimes could be inspired, and you're not gonna leave the computer until you finish what you started. Again, coding is a creative work. I almost consider it's like an art, right? And you have to apply the same discipline. the same, the same skills. You have to be disciplined. You have to practice good habits, because the tendency is of the human behavior. Yeah, just, I'm going to come back. But most importantly, it's a creative work. And when you inspire, I tend to actually finish the entire thing that I propose to finish. And usually I don't like to, but that's personal, to leave things halfway done, because I may lose my thought. That's really at least my concern.
I have a question also. So if I want to find people, or if one wants to find people, like a team per se, to help students or high schoolers or parents with like development and these types of things, how available are people to do it? These types of things, depending on the project.
It depends on the project, and
more specifically, like LLVM compilers.
LLVM. What's LLVM?
It's a form for compiling.
It's
an infrastructure.
LLVM, you said?
Yes.
LLVM. Okay, yeah. I know what LLVM. Yes. Okay. So the best thing that you can do is, at least what I find out, is follow the open source project model. You'd go on GitHub. That's probably the best place where you open a project, your repository, and you'll find people that they want to help. If they find your idea interested, they will join your project, and that's the best way to collaborate. As a matter of fact, just my saying is that open source project is the best model. It's probably without open source, the industry would have not been where it is today. That's the reality. When I started, open source, the biggest open source project was actually, what was it? Linux? That was the one, yeah. But yeah, that's the model. That's the way you probably want to do it, and you'll find people to join you, and from industry and others, other students, either from college or from high school. But you will find there's no limit there.
Yeah, thank you.
Vasi, can you see the chat?
Oh.
I can just read them off. I know you're screen sharing.
All right, I can see. All right, so let's see. How did you do to better your coding skills? Well, that's actually an excellent question. You gotta practice a lot. You gotta learn. You gotta read a lot, and you gotta steal from others. That's the best thing to do. Steal from others. Steal, if you find a mentor, steal from there. It's the same that I do now. It's, the younger team in my team, they stealing from me. They learning how to do things. They learning about best practices. They learning about design patterns that they need to apply in each situation. And that's probably the best way to do it. What do you think is the most rewarding part of your profession? Oh, that's an excellent question. The most rewarding part, the most rewarding parts. Okay, so when customer using your product and they enjoy it, and they come to you and say, hey, I enjoy using your product, they help me a lot, that's probably the best reward that I can ever get. That's really the best reward, bar none, because ultimately what you're building for somebody else, not necessarily for you. You're building to help somebody. Let me see. And I'm not sure if that's the complete answer for the rewarding part, but this is one of the things that are really, really, it is rewarding for me, the customer feedback. What is different between programmer and software engineer? I don't think there is any difference between programmer and software engineer. In my opinion, it's the same thing. You still have to do the same chores. There's no difference. I think enterprises, they may have different titles in their company, but ultimately it's the same thing. Between Angular, React, and Vue, which is a better framework to learn? If I say jQuery would be a better one, is that a better answer? No, I'm kidding, of course. All of them are good, are very good frameworks. Angular, it's one of the popular out there. It's a little bit more complicated. I think the learning curve for Angular is steeper than the learning curve for React and Vue. And I think if you don't have the patience and if you want to see something quickly, the best way is to start with probably, I would say, even though I haven't used myself React, but you could start with React, which is a little simpler. And their programming model, it's definitely simplified. Angular, it's a little, again, it's the learning curve, but both of them are extremely powerful. And Vue as well, actually. I've heard a lot of good things about Vue. What do you think is the best useful coding language to learn? Coding language to learn, what is the best useful? There isn't one. Once you're learning one language, it's going to be easy to learn the second one. The best thing that you can do is focus on learning the fundamentals, the concepts of computer science. Learn about algorithms, excuse me, learns about data structures, learns about those basic things. Well, actually, they are not basic. They are really, you need them. Those are part of your tools when you're going to go in software engineering, if you're going to go as a software engineer. Those are just part of your tools. The language is just the tools that you're using for doing something. For example, JavaScript, it's very good if you're doing web application. It's not extremely good if you're doing, let's say, CPU intensive application. You probably use a different language for that, either Java or C or C++. But I would say if I were to start again, and I think, well, actually no, when I was in college, when I started actually with C. And the reason I started with C was that once you learn C and learned about the concepts, you learn about memory allocation, you learn about how to destroy, deallocate memory, you learn about pointers. Those are basic concepts that is going to help with any programming language. All right. Any other questions? Okay.
Yes. I would like to ask, if you are starting a business or you want to start a business, do you think there are some ways to integrate coding into your business, or are there ways to make coding itself into a business?
So let me see if I understand correctly. If you're starting a business, is there any way to use coding into the business? Is that what you're asking?
Yes.
Well, it depends on the business. Again, is it a high-tech business? Is it a business that, let's say, the domain is different than high-tech? Maybe, I don't know. Just give me an example of a business. Let's say if it's, I'm just trying to think, a shoe shop, right? A specific shoe shop that does a specific sneakers for sports. I'm a big fan of sports, so I'm using that analogy. Probably you only use the coding just as a tool to help you grow the business, but the main business is actually the shoes, the sneakers, not necessarily the coding, right? Does it make sense?
Yeah.
Maybe I don't understand the question. What was the second?
That was a good answer. Yeah, thank you.
All right. Okay. Let's see. All right. So, all right. So it looks like there are no more questions. Thank you so much for sticking around. And great question, guys. Really great question. And by the way, I love all the talks.
All right. Thank you so much.
Thank you.
Now we are going to transition to Dr. Jason Graham. So let me just spotlight him. Awesome.
Hi.
All right. Dr. Jason Graham will be demonstrating computer science's role in bee research. He is a bee researcher and has worked with honeybees and beekeepers for more than 12 years. And he earned his PhD in honeybee research and extension laboratory at the University of Florida. So without further ado, I'll let Dr. Graham take it away.
Hi, everyone. It's great to be here. I feel honored to get a chance to speak to you all about my research and how I've used computer science and bees together and how it's used in other research projects. So first of all, is there any beekeepers in the audience? And wave your hand, be proud, you are a beekeeper. No? I'm not seeing many hands going up. So I'm not a web developer, not a computer scientist. But I am a bee researcher, I'm a beekeeper, and I see the tremendous value that you all bring to the table, and that's kind of one of the reasons why I wanted to be here to talk. And so first, I'm gonna, since you guys aren't beekeepers, and I'm trying to bridge this gap here of my knowledge and your knowledge, I'm gonna jump over to my PowerPoint. We're gonna talk about bees. Okay, so I'm gonna share a screen. And you guys can laugh at how untech savvy I am. Well, I provide that entertainment value for. So if you see me goofing around with this stuff, then please teach me how to do this better. All right, so can you all see my screen, my PowerPoint? Awesome, cool. So first of all, this is me kind of getting started learning about bees at University of Florida. So I took a class for the fun of it, actually at University of Delaware, and got into entomology, which is the study of insects. So learn more about insects. I took a beekeeping class, did well in it, and then ended up getting an invitation to do my master's at University of Florida. So here I am at my master's at University of Florida, and I'm beekeeping. These probably don't look like normal beehives to you guys. They're actually bumblebee hives. So these are hives that bumblebees dwell in, and these are put in different agricultural spots to help with pollination. So now I'm going to jump down. So these are another bee home. This is for solitary bees. So some bees actually just live in tubes. They could be boba straws, they could be bamboo, they could be different materials. And I was curious, so there's a huge diversity of bees and they all prefer different kinds of materials. So I was using this kind of setup to try to figure out, do bees like small holes, big holes, bamboo, plastic, paper, trying to just look at, do some prefer to nest in wood that's been burned and versus wood that's not been burned. They like to nest in the soil. So I found this one bee. This is a chimney bee, pretty cute, right? So this bee nests in clay, and somebody had this in their backyard, this clay that they were using for landscaping. They called our university and said, should we get rid of this? Should we call an exterminator and get rid of these bees? And I came over and took a look, and they're actually solitary bees, so they don't sting to defend themselves. They're nesting in several different types of materials. And the homeowner, when they found out that they don't sting to defend their nest and they're good for pollination, they helped out with a citizen science research project to kind of study this bee and take care of it. So jumping down a little bit, I got interested in bees that are endangered. I thought, these bees that may have a relationship with a particular flower, that may be keeping that flower going just through pollination. So I got really interested in why aren't there any endangered bees? Because at the time I was looking at this, there wasn't. There was one bee that might have gone in danger or been considered endangered if it was able to get the status through the Federal Register. And so I worked with the department. So after I graduated from University of Florida, I went to Hawaii and started working on this project I went to University of Hawaii and worked on this project for endangered and threatened. We wanted to find out these endangered and threatened bees. Where they lived, what they needed. So I did some research for a few years, and then we got this listed as an endangered species, and then this is what comes out on Facebook. So these are not the yellow-faced bees, but you see how media sometimes you get the wrong story, but the right I guess maybe came from the right place. Anyway.
Dr. Graham.
Yes.
Oh, sorry. So sorry to interrupt, but we can't see it's still on the title slide. I think.
I'm sorry. Okay.
Yeah, it's sharing the wrong. Sorry, I didn't want to interrupt.
Thank you. No, I appreciate it. So let's see. Like I said, I'm not a computer scientist. I wish I was able to do that as well. Let's see. So you are on the title slide. I'm trying to increase my screen so I can see. So you see computer science's role in bee research right now?
Yeah. Okay, now I think it's, yeah. Now we see all the slides.
All right, I'm so sorry.
No, no worries.
It's okay. So here we go. This is me, University of Florida. I was looking at, these are bumblebee colonies. So if you guys were curious what I was talking about, that's what a bumblebee colony looks like. These are solitary bee nests. So the bees nest in these tunnels and tubes. These kind of solitary bees do not sting to defend their nest. So there's some pretty cool things you can do with education, sharing this with kids. It's cool for backyard gardens because you don't have to worry about a hive full of stinging honeybees. And we'll get into it more later. So this is the register on Facebook and things like that. We saw these popping up honeybees are endangered to the added to the endangered species list, but they aren't. The honeybees are not completely endangered. They do have problems of their own. But when we have to look at bees, there's a lot of misconceptions out there, and trying to clear a few of them up real quick. Bees are insects. So bees are animals, they're insects. They have a head, a thorax, an abdomen. Inside, it's not just bug juice. They have brains, they have circulatory systems, they have respiratory systems, muscle, all kinds of structures in there that are known, and we can dissect the bee and see all of this, the nerves, some really interesting pieces. So bees are related, very closely related to ants and wasps. One of the big differences, if you're not sure, am I looking at a bee, an ant, or a wasp? You have to look at it under a microscope, look at their hairs. So some of the bees' hairs are branched like this. Anybody have an idea of why that might be? Why the branched hairs are helpful? Bees?
To collect pollen.
Yep, absolutely. So they collect pollen. It's because their diet, they're pollinators. They eat pollen, they drink nectar, and that's their protein and their carbohydrates to keep them going. Unlike ants, which can eat just about anything, and wasps, which are predators of other arthropods. So bees can also be solitary or social. So ants are pretty much always social. Here's an ant and thousands of ants in the colony, and you can see how huge some of these colonies get. Here's a wasp. Wasps can be solitary or social. So yellow jackets, things like that, those are social wasps that can sting. They sting to defend their nest, but they chew up bits of the insects that they catch and feed that to their larvae. In the solitary case, down the bottom, we have this tube. It's like a bamboo tube. And the solitary wasp drags these katydids in, laid eggs on them, and then partitioned off some area for the katydids to develop, or serve as food for the developing wasps. Sorry. So with bees, it's the same thing. We have some that are social. We have these honeybees that are social in these big colonies of thousands and thousands of workers and one queen. So the queen can lay eggs. All the workers do everything else in the colony. To a different situation with these solitary bees, where one bee comes in and she lays an egg at a time into a long tubular nest or something similar, and then she flies away. And those eggs develop on their own without adults to care for it. So there's no adult bee caring for them. So here's again our honeybees. We have the queen, which you can see biologically is a bit different from the drone, which is the male, or the worker, which is the females that are sterile and cannot lay eggs. She's got a longer abdomen. And I'm going to show you something cool. This is just a quick video. You can find it on TED Talk about bees, but this is like shows their life cycle, if it works. Good. It's an egg developing into a larva. They're fed royal jelly. The larvae eat the royal jelly, and they get bigger. And this is kind of the pre-pupal stage. So they go from larva into a pupa. So if you saw something like this on the street, you probably wouldn't think, oh, that's a bee, right? It's a lot different from what we think of as a bee. But this is the pupal stage. There you can see their brain developing through the exoskeleton there. See the exoskeleton hardening. I think you probably saw the varroa mites running around on the bee. So the bee hardens a bit more, and then the first job is the bee cleans its room, just like us, right? Go to your room, go clean your room. So it cleans its room itself and makes room for the queen bee to move in and start laying eggs for the next generation of worker bees. And this is just an ongoing process. So now you guys are pretty much experts on bees, bee biology. You got to see the whole entire thing go through. So we have egg, larva, pupal, and then adult stages. They have interesting communication, so they sense things through their antenna, which is covered with these little holes, and hairs, which is kind of like noses, brings in chemical smells, and that's what the bees use to sense their environment. They also see through compound eyes, which are made up of thousands of lenses. They sting, so that's one of the things we got to talk about with bees, right? They can sting. These bees will leave a stinger under the skin, and the serrated blade will kind of drive the stinger down. Best thing to do if you get stung, scrape that stinger out immediately and then clean the area. And you're probably going to be fine as long as you don't start having trouble breathing or swallowing. If you do, then you may be allergic to bees and need to get to an emergency. So real quick, I'm kind of going to cut through this a lot faster because I don't want to take too much time. I have to get this slide 86. So these are just pictures of how bees may be kept. Different types of hives, right? This is the standard honeybee hive. So you can see the honey, the pollen, queen bee. This is all brood. And people keep bees for a variety of reasons. They could sell pollen, they could sell the honey, they could sell beeswax, they could make more bees. They may do it for educational purposes. And bees are super important for pollination. So a bee goes to a flower, this white flower, and afterwards, the pollen that she leaves behind will change that flower's morphology. It changes the flower into a fruit. Starts out that plump white blueberry and ripens. Same thing here, we have this is a passion flower. After it's pollinated, we get lilikoi. Other flowers, same thing. We need that flower to get pollinated so it can become the kind of fruit that we like to eat. We typically don't eat a lot of flowers, right? But it's important for the flowers too, because with that fruit come seeds. So, sorry, okay, I'll just jump into it. These are different kinds of diversity. So we understand pollination is important, right? This is diversity of bees. So there's lots of different kinds of bees. Not just the honeybee. The honeybee makes honey, but there's a lot of other bees that are important. This is an endangered yellow-faced bee, much smaller than a honeybee. Has the same general biology, right? Goes from egg to larva to pupa to adult. They live in Hawaii, right along the side of the beach. So this used to be my lab. I would go out here and I would look for these bees nesting in wood, nesting in trees. And this is my research block in the back here. Found out these bees nest in coral that washes up on the beach. And they also nest in stems of trees. And this is what their nest looks like. So at top we have the egg, larva, pupa going into an adult. I put out these blocks to try to see if I could see what's going on inside those nests and put these tubes in the blocks. The bee would go into the tube and make its nest in the tube. So I could collect that data as far as how much pollen was there. A little video about the bee making the nest. She uses her tongue to brush on this very thin layer of material that is kind of like silk, but also wet. And then it dries almost immediately and provides like a cellophane for them. These bees are only regularly seen in kind of two main locations. But I had worked with some students at Iolani Middle School, and they put together, can you still see my screen as well? I'm not sure if you're only seeing my PowerPoint, but if you could also see me. So this is a 3D printed tube that some students at Iolani put together to try to see if they can figure out whether bees prefer transparent tubes or opaque tubes. And they did this with several different projects. They made some blocks for us to hang up outside in their habitat. They programmed the router to put the exact size tube tunnel that we're finding in the wild, kind of to see if this would serve as a habitat for these bees, and several different projects. So they really helped out with that. And that's kind of one of the reasons I think it's great to share this stuff with students, because it's a win-win. You guys can help out with a project and then get some experience, and then also really be helping research at the same time. So that brings us to the reason why I'm here. So these are some other, so beekeepers are finding different ways to get revenue. One of the things is collecting venom. So there's harvesting bee venom is really important for, there's a therapy. It helps a lot of people with different kinds of problems. One of them is Lyme's disease. So if someone has Lyme's disease, they could be on a very strict regimen of medication that could be harmful to them. They could be having trouble with it. And some have actually gotten off of some of those medications using bee venom if their body responds to it properly. So beekeepers can harvest bee venom using this glass plate. They have a battery-powered collector that has has a small pulsation. As the bees sting that glass plate, doesn't hurt the bee because they're not losing their stinger, but the venom is actually being able to be collected. This is being tested in a variety of different ways. Here's another. So this is some beekeeping apps that have been made available for beekeepers that have been really helpful. Hive tracks. This is so you're able to manage your apiary, so you know what how many bees you have in each of your hives, and you can have someone else go out and check your hives for you and input the data, so you can stay updated on how your bees are doing. Some of these are built in with scales, so you put a scale underneath of your hive, and as the hive gets more honey bound, has more and more honey, sends alerts to the beekeeper like, you're getting a lot of honey in this hive. You can either probably split it, or you can maybe harvest that honey to sell. So these are some really good resources to help out beekeepers. Beekeepers are really in need of help right now because the bees are having lots of different pathogens and pests and things like that that are affecting their colonies. So we're also trying to appeal to the new beekeepers, because the beekeeping kind of, if you think of that, this feels like kind of an old career. Like not a lot of people nowadays, are getting into beekeeping, but actually the reverse is true. I guess since more and more people are hearing about problems that beekeepers face, they think, what can I do at home? So people are designing bee hives that can be printed through 3D printers, scanners, things like that. Things like the flow hive, a way to try to make beekeeping less scary for someone, right? You just turn a switch and harvest the honey out of your hive instead of having to go into it. I think education is really important to kind of train beekeepers and share things with them so that they don't feel scared to go into their hives. But these are all improvements. This is all technology that, that STEM has led to bees. You have a bee box that senses your hive and can send security alerts if it gets too hot, too cold, if it seems like they don't have enough food, bees don't have enough food, or if there's threats inside the hive. There's sensors that can smell your hive, whether the bees are sending off alarm pheromone. So you can tell if your bees are being invaded by some other pest, or maybe a bear. If you have a bear attack your hive, then you find out right away, because that alarm pheromone is setting off a signature. Zombie flies. So these are a fly that was found here in California, and a whole zombie watch program was started as a result of that. And people all over the country can send in samples of their flies and then find out, they're mapping where the zombies are. These are flies that go in and change the bee behavior. It makes them fly out at night and will land in, usually you'll find them the next day flying in front of a lamp of some sort. There's a cocoon. So this is a type of high-tech beehive that stops varroa. So those mites you saw in that video that were walking around on the larvae that were developing as bees, those mites are really bad for honeybees. Probably one of the #1 enemies that honeybees have. So this type of device is used to heat up the hive to a temperature that the bees can survive, but the varroa mites can't. So it's used when the varroa mites are detected. It heats up the hive, and then hopefully the varroa mites will die because varroa mites will die if it's over 100 degrees, whereas bees can survive a bit higher. 3D printing helped out make these bee gyms. So these are little gyms the bees can walk around in and maybe knock the mites off of them, because it has a series of little flaps and strings and things like that that knock the mites off its body. So another way is how you can help. This is iNaturalist. This is a program that is used for a lot of different things. Has anybody used this before? Anybody familiar with iNaturalist? So iNaturalist is a program where you can take your smartphone out, you download the app iNaturalist, and then you go out and you record an observation. If you see anything living, so it could be a caterpillar, it could be an elephant at the zoo, it could be a leaf on a tree, and you want to try to figure out what that is. Well, first off, after you take your observation and submit it, it'll first just leave kind of a blank. You can put what your observation is. You can say, you can use this to search for what species are around, or you can use it to kind of identify something. So if you take a picture of it, first you can write like bee. I think this is a bee. And AI will look at what that bee is and see if it kind of fits other pictures that look similar to that bee, and matches it up to, okay, I think this is a bumblebee. And then after that is a kind of final quality check. Volunteer taxonomists and specialists, experts go on here and they look through all of the sorted AI files and they confirm whether this really is a yellow-faced bumblebee or not. So what happens is we get all these pinpoints of bumblebees in that particular area. And then that's helpful for researchers. If I want to go find out where's the best place to find a yellow-faced bumblebee, here's my spots. I could also look at some of these pictures and see what flowers they're using, so I know what flowers to plant in my backyard if I want to attract yellow-faced bumblebees. And so first you enter your field, you say, okay, I think it's a honeybee. It'll record the timestamp and it'll record the location. Other useful tools, you could also bring a click counter and see how many times they're landing on a flower. There's a lot of different ways that you can do research with this. You just need really a smartphone camera and your iNatural app. So that's one tool that you can use. Another thing you can do at home to help out the bees, if you're not interested in working with this app, another thing you could do is this nest habitat for solitary bees. So you can actually create habitat for bees in your backyard. It's pretty simple to do. These are solitary bees. You can take a bunch of bamboo and put it into a can. You need to look at the size. So you want to go from anywhere from a 3/32 hole up to a 5/6 diameter hole. And there's a lot of research going on to see what's the best material, what's the best size, but it's all kind of up in the air right now. You see some anecdotal evidence for certain things or reasons why not to do others, but there's definitely a lot of information out there that's still to learn. So nest habitats, what happens is the bee will find your habitat, she'll look for the perfect hole for her nest, then she'll go and collect and store some pollen nectar in that tube. She'll lay eggs on it, and then she'll go collect some other kind of material to put in front of the egg to protect it and seal her cell. She'll work her way forward on it like that. And at the very end, she'll seal it off with a leaf or a resin or mud, depending on what type of bee she is. You have wool carder bees that go and collect some fibers from plants, like the wool from plants, and put that in front of their nest. So there's some habitat care that you have to worry about, like keeping ants out, replacing damaged portions of the nest. You need to monitor for mites. Sometimes these bees can get mites as well. So if you see a mite problem, clean out the nest and then maybe start out with new materials. It's really easy to make a liner. You just take wax paper and roll it around a pencil, and then make a tube like that. And then tape it, the bees will find something like that and start moving in. So here's another program. I'm not sure how much time we have, Diane. You still doing okay?
Yeah, we have a few more minutes.
Okay, so I want to show you another one. This one's called Brood Mapper. So citizen scientists score bees to better understand bee health. I'm going to escape from this one, and now are you seeing my Brood Mapper page or no? I might have to stop sharing and then come back.
Oh, we can only see the slide with Brood Mapper.
You can only see the slide right now? Okay.
Yeah.
I'm trying to go to your website. But this is basically a program where you can sit at home and help out bee research by looking at these pictures of bees. So these are frames of bees, and you can click on which bees are larvae, which are eggs, which are pupa. And when you go through and do this kind of scoring, it submits data to bee researchers who are trying to understand bee health better. So all these pictures could be taken really quickly, but looking at each individual cell to see whether we have a sick bee or a healthy bee is pretty hard. So asking citizens to go in and kind of score these for us has been really helpful for bee research. So someone can sit sit at their home and put an hour in on the weekend and score hundreds of frames. This is really helpful for bee researchers, and it's kind of like a game once you get into it. So that's the main things that I wanted to show. I was hoping to show this too. Maybe stop share. Try to stop share, and then I'll go to the Brood Mapper and share screen again. Okay. Now are you able to see Brood Mapper, or?
No, we only see, oh, now it started screen sharing. Yeah.
Okay, cool. So this is Brood Mapper, and basically you click on one of these cells, and whether you first click on, say, egg, and every time I see an egg, I can click on one of the egg cells, put an egg in there. So this is kind of the idea of this program. If I use this, will it already stop sharing? Yeah. So now I'm going to show you one more real quick. This is the iNaturalist. So if you happen to go to Hawaii and want to really help out with this project, this is Pollinators in Paradise, our project on iNaturalist. And so it already set the parameters. Can you see this okay? Say Bishop Museum up here in the corner, Pollinators in Paradise?
Yeah.
Yep, okay, great.
Yeah.
So this project, we have had over 1,000 observations. And these are anybody that takes a picture of a honeybee, wasp, might be a bee, gets pulled into this automatically. You can also go in and kind of see some of the different stats of the different people that have helped out with this project. You get, as a researcher, you get your own kind of section here. So this is my profile, and I can look at the different species that I've observed. So you can, some of these are, so this is some stilts, some birds. You can see some out in the zoo. Kind of fun to do. So you just get different observations of animals. And when you get enough observations, then it helps the research in different ways. So, and also we could go to iNaturalist to look for a particular, so if I want to go explore, you could look for, say, bees in you look for bees in, say, San Jose or Cupertino or anywhere in the world, really. Take the bees, click on that, and then pick a location. So if we just say California, then this gives us observations in California of bees. We can kind of scroll through, you can make a checklist off of this and figure out what bee species near you. You could go down to the town level, the county level. You can even put in a particular university. So like Stanford, just the hiking trail. What kind of bees have been found there? So no results yet, but I'm sure there's bees there. So if you happen to like this area, get a couple pictures of some bees and then add that, and it'll and you can see these are the observations. You can click on any of these observations. So if I click on any of these pinpoints, it'll bring up that particular find. And this one's research grade, so that's helpful. It's bed into the research level. So that's pretty much all that I have for my presentation, but there's a lot of different projects out there that you can get involved in with citizen science. I'm trying to put together some things for, okay? Try to put together some more projects with bees and beekeeping, and I could definitely use some computer science help. So if anyone's interested in volunteering some computer science expertise, help out with some of these projects, that would be great too. I can connect you with other researchers. Does anyone have any questions?
Oh, someone asked what inspired you to do work involved with bees. Oh, so one of the things, I guess I went back to school a little bit later in life, and I was looking to see what interested me most, because I felt like I would do better in classes that were very interesting. So I took some electives, and one of them was a beekeeping class. I thought it'd be really fun. So I put on a bee suit, went out, and we actually managed a hive for a full year. So I was able to open up the bees, or open up the hive and see them. It's a lot different than seeing it on video, but such a cool experience that I wanted to keep going. And as I go, I'm still learning about bees. Every time I hear someone else's talk or read a new article about a different species of bee, it's fascinating to me, so it just keeps on going. That's what feels to me about bees. And just how important that they are for the environment, both for our agriculture and then also natural ecosystems. Definitely.
Do you feel that orchard owners should raise bees, such as the orchard mason bee? Yes, I think that beekeepers should definitely have more options than just the honeybee. There's a lot of different, there's over 20,000 different species of bees, and we're really relying on just one for most of our agriculture. So using things like these solitary nests, we may be able to help agriculture where provide more pollination services for specific plants. Any other questions?
All right, if that's all, thank you so much, Dr. Graham. I hope everyone really enjoyed learning about all of these resources and iNaturalist. And now we're going to transition to, let me just spotlight her again. You guys know the drill. Okay. All right, please welcome our next speaker, Dr. Maiti Loh, who's going to be joining us to discuss her journey from a refugee camp to the heart of Silicon Valley. She is a technologist, an entrepreneur, and educator, and she received her PhD in electrical engineering and computer science from UC Berkeley. So without further ado, please give it away.
Okay, so hello, everybody. So I thought, I just want to find out quickly, how many of you are in California? Okay, so where else is everybody? Okay, so I'm not going to give a long, boring talk because it's really, really hot at my house. And in fact, I'm hiding in the back bedroom because we have my brother, his partner, my nephew, my daughter, and my husband are all in the living room. So I'm hiding in the back room. So it's very, very hot. So instead of giving a long, boring talk, I wanted to have a session where actually I want to learn more about you guys, about who you are, what you're doing right now, and why are you participate in this conference when you could be out doing something else. Like, for example, if I weren't here, I would be in the pool because it's really hot in California at the moment. Okay, so I want this more to be an interactive, and I want it more so learning what you want to know instead of giving a speech about how wonderful I am, which I am sure none of you really cares, right? So tell me, why are you here? Why are you at this conference? What are you hoping to get out of this conference?
Okay, our audience is a little shy sometimes, so I'll start. Well, personally, I know I organized a lot of it with, of course, with the STEMI team. And the reason we organized and attended is because a lot of people don't get great exposure to STEM through like normal classes. Like, for example, with physics, I feel like the physics talks we had this morning were amazing. And it goes so far beyond any physics that like you learn in AP Physics, which is, or like AP Physics 1 at least, which is normally the only physics class that high schoolers even take. And physics wasn't even mandatory till last year for our school. And so a lot of people don't realize how cool all of those STEM subjects are, because they're just taught like those skills in a very like, I don't know, monotonous and kind of technical manner. Like, okay, here's Newton's law. This is what you need to know. So we wanted to like explore all of the different disciplines and yeah. Okay, I'll give other people a chance.
Yeah, so I'm attending this first also because I did help like organize it, but mainly because I find a great interest in a lot of the subjects, spoken in these in this thing. Like a lot of the subjects can affect me and what I think about on a day-to-day basis, and what I want to do in engineering or in all these subjects in a field. So like it's always nice to know what's happening. Even though if you know stuff, it's good to have like more of an understanding, I guess. So that's a good reason too.
Okay. Anybody else?
I know I attended it because I kind of want to learn more about like physics and math and kind of like what I want to go into in university. And I feel like through my like what type of engineering or just like anything like that, and at school I can't really figure that out. So I think that's why I really attended this conference.
Okay. And who's just spoke?
Hi, that was me, Lauren Bridgewater.
Okay. So I'm going to tell you a story about the reason why I ask questions for you guys is because this is what I do with my own student at Stanford. So I spend a lot of time talking to them and listening to what they have to say. So I started out teaching a class. The joke is at Stanford, I started teaching graduate student. Then I started teaching a required class for graduate and senior. And then I went down to teach a class that's required if you want to declare a major is electrical engineering at Stanford. And then at the end, I end up teaching a freshman seminar, and that's why I stay for a long time. I keep moving down the ladder. And the class that I co-taught with Professor Andrea Goldsmith was called The Art and Science of Engineering Design. So we take a bunch of freshmen who didn't know anything about engineering, and we put them in a class, and we say, form a team, pick a topic, any topic that you think that's any way related to engineering will help you work on a project. That's the premise of the class that I came up with. And it was so simple, and yet it was so powerful. And we have students, and the student absolutely love the class. The class is incredibly popular. Every year, there are about 200 freshman and sophomore seminars at Stanford. And every year they give out an award for what they call the Excellent Award. They would pick a project or a team or a student out of those 200 seminars to give out the Excellence Award. And every time we teach the class, our student win the award. In fact, one time we actually nominated two teams, and one won the prize, and the other one was the runner-up. So the next time we taught the class, we also nominated two teams, and we got back a very snooty email from the committee saying, hey, you're only allowed to nominate it once. So we nominated one, and they won anyway. And the reason why is because the student get a chance to work on something of their interest, and that's related to engineering. But what's really interesting that I found was, like I said, I spent a lot of time working with the student, talking to the student inside the class and outside the classroom. And many of them, especially young women, would come up to me and say, I would go do engineering if it were more socially relevant. And I heard that over and over again. And after a while, it really struck a nerve in me, because I was beginning to ask myself that question. I was very lucky. I went to college, I graduated, I went to work in Silicon Valley at the very beginning of the networking boom. So I worked on all sorts of networking projects and became very successful because it was such a hot field at the time. But the more I started working on it, the more I questioned myself of, so what is all this for? So it's great that you have Facebook, right? You can chat with your friends. It's great that you have Google that you can do search. It's great that you have DoorDash and you can order food and you don't even have to go and pick up, whatever. But how is it socially relevant? How is it really directly affecting people's lives, changing people's lives? And just as my students were questioning themselves, amazingly enough, at the very beginning of their career as a college student, I was asking myself that way, way past my college career, right? Way into my own professional career. And so because of that, I started working with many NGOs and many not-for-profit companies that directly affected people's lives. Okay, so I learned so much from my students because of the questions that they have in their lives. That forces me to question my own life. Okay, I could very easily just keep on working exactly the way I have always been. I can, I'm an angel investor. I can probably go get a job working with a venture capitalist firm. I have worked with startup throughout my career. I can keep on doing all those things. It wasn't satisfying to me. It wasn't important enough to me. So let me give you an example of the kind of things that I'm helping young entrepreneurs working on right now. So do you guys remember, maybe you're too young, but in 2007, 2008, there was a huge crisis, health crisis in Africa. It was the Ebola crisis. And people were dying. People were dying by the thousands. And they were just, people were desperate to stop it. And they didn't quite know what to do, okay? There were two young college graduates from UC Santa Cruz who were working in Nigeria at the time. And they came to Nigeria working on making the healthcare system in Nigeria more up-to-date, more modern. They wanted to computerize, they want to digitalize the Nigerian healthcare system. They just happened to have the most up-to-date maps of Nigeria at the time. They have a more up-to-date map of Nigeria than the government of Nigeria, than the UN. So when Ebola was spreading through Africa, it was coming to Nigeria, and they have a map, and they were able to trace, along with a young team of Nigerians, computer nerds, able to look in the maps and figure out where the Ebola crisis was coming and where it was going. So there were three organizations that were responsible for stopping the Ebola crisis in Nigeria. It was a local organization that had to do with burial, because in fact, that was how Ebola was spreading, was when you bury people, the people who do the burial get infected, and then they went home and infected others. So that was an organization that was helping stopping the Ebola crisis in Nigeria. It was the Doctors Without Border organization, because they were the one with the all these sort of makeshift hospital that was trying to save people who get infected. And then there's eHealth Nigeria, which is now called eHealth Africa, that will be able to go in and determine where to get people away, to get people from the Ebola center and stopping the crisis. Okay, so I happen to be supporting eHealth Nigeria at the time, now eHealth Africa, and it's supporting these two young UC Santa Cruz graduates in that process. Okay, so from that little organization, they are now have an organization with about $20 million annually. They have about 600 employees, and they were working on 6 or 7 different countries within Africa. Okay, so it is relevant because, 12 years later, we are at this place where we are now facing with another pandemic, right? And that's what we're working on. So the eHealth Africa is one of the few organizations within Nigeria that have a testing center. So that's where people send testing sample to the lab. We also have a hospital where people with COVID can come and be quarantined and be treated. Okay. They work on so amazing things. So I still remember we were talking with a young engineer working at eHealth Africa last year. And he was working on a refrigerator. Basically what he was working on is a glorified cooler, the kind that you put beer and sandwiches in to take to the beach on a hot day like today, okay? Except that he was building on this super duper cooler to put in vaccines, because we were working on a program to eliminate polio in Nigeria. So he was able to work on creating this amazing, lightweight, tough, maintain the right temperature range cooler, so that the community health worker can bring the vaccines to these very remote, very challenging regions to vaccinate hundreds of thousands, millions of people, especially children. Okay, so my message to you today is there's beauty in mathematics. There is beauty in astronomy. There is beauty in the Genome Project. There's so many things that you guys can do. There's so many things that you can make a difference in the world. There's so many things that you can explore. What I would like to encourage you to do is, especially in the current environment, go look at the world and ask yourself, what can I do? How do I use the technology to create a better world? Okay, because frankly, my generation, we screwed up, right? We are leaving you a pretty messed up world. And what we counting, the reason why I am so passionate about teaching, I spend a lot of time teaching and working with young people, because I believe that you guys, my kids, you guys, the next generation is going to be able to ask, I think, a more relevant questions, more out of the box questions to solve the world's problems. Okay, so there is such value in technology, in engineering, where you can ask these amazing questions, and from those questions, you can come up with amazing answer to get ourselves in the mess that we're in. Okay. So I can go on. I can tell you many other stories about other projects, about other ideas. But what I really want to do is I want to hear from you guys. Ask me questions. Tell me what you think. I think it's more important, it's more relevant for you guys.
And did you say, are you currently teaching at Stanford or?
So I was teaching at Stanford, but the problem that I have is that I get involved in two things. So I teach two classes at Stanford. One is called the Art and Science of Engineering Design. And the other class that I teach, not surprising, is called Engineering for Good. So in the class, we have a bunch of students from all sorts of discipline, from anywhere from mechanical engineering to history and English major to HumBio, which is human biology. They come and they work with NGOs and not-for-profit company on projects that Engineering for Good. So I teach those two classes. I'm also involved with the International Summer High School program at Stanford. And I should be teaching right now because that's when the International Summer High School program at Stanford is happening. But of course, it's not happening this year. I'm supposed to be teaching in January for my Engineering for Good, for the Art and Science of Engineering Design. But I'm not teaching it because it's going to be online. And for the class to work, because the student need to be working together, building stuff, designing things. It's just not, I didn't think that it would be an effective class to be teaching online right now. I might consider do it in the future, but not at the moment. So no, I'm not teaching it at the moment. I'm very sad about it, actually.
Yeah, that makes sense. It's just really cool to hear about all the classes at Stanford, because that's actually like my top choice right now. So
Sure.
I know, yeah, it's just really interesting to learn about all the classes there.
Anybody has any other questions for me?
What has been like the biggest challenge in your career?
What's the biggest challenge in my career?
Or like career pathway leading up to your career?
Yeah, so that's the thing, is that my biggest challenge was for me to face up to the fact that I didn't want a career. For me to face up the fact that I didn't want to climb a ladder, that I didn't want to follow a traditional trajectory of what I wanted to do. That was the hardest. That was the hardest thing when I realized that these are classes that I only want to teach these classes. I'm not willing to teach anything else. Or the fact that I'm really interested in working with high school summer programs, sort of choosing what's relevant to me. Seeking out the kind of entrepreneurs who are working on ideas, on companies, an organization that speak to me and speak to my interests and my conviction. Right. So that's really hard.
Okay. Me and my family have, I don't want to do like a super grand introduction, but we actually like a year or so ago, we started this small nonprofit organization to help fund, like do monthly funds or yearly funds for our family back in Africa, that people back in Africa that are in need of it. So schools, children that are in a deficit of supplies and money and stuff. And my mother is also from Cameroon in Africa. So we have a lot of connections and stuff like that. But I was like recently, over the summer, I did like a lot of business research and I got really inspired and interested in business. And I want to ask first, like, what kind of investing do you do? Like, what do you invest into?
Yeah, so I think that's amazing. So I think that one of the things that I love to do is once a year I go to Nigeria and meet up with the teams in Nigeria. And what I'm always amazed, I love doing that because because I'm so inspired when I talk to the young people who work at eHealth Africa, how entrepreneurial they are and how driven they are and how tech savvy they are. And I think that, you know, when we sit in Silicon Valley, I had no idea how entrepreneurial and how tech savvy and how business savvy young people in Africa are. I mean, there are just so many opportunities. There are people who working on, for example, starting motorcycle ride sharing program. People working on delivering goods in remote villages. There, which is so many things that young people in Africa that are working on that just really, really inspiring. If you're interested, get in touch with me. I will put you in touch with a colleague of mine who is doing just that. Her job is to sort of help train and nurture and mentor young entrepreneur in Africa. And so there are lots of opportunity. It's really exciting. It's wonderful to see.
Oh, I'd love to get in touch. Yeah.
That usually people always ask me when I go to these conferences, they always be like, you don't get to have your card. I never carry cards anymore. I think I have a stack of business cards somewhere up in my office. But I say, you know, these days, if you really want to find me, you'll find me. And usually people do. So yeah, you want to get in touch with me, do. Right?
Where can I contact you?
Find me. I'm not hard to find online. I try very hard to keep a very low profile, but it's very easy to find me and find me. And then, you know, just let me know where we met and then we'll go from there. Okay.
Okay. All right. Thank you. I know you don't have a lot of time, so bye.
Bye. Given that there are still very few women in experience, what advice would you give them that they're not intimidated when
I think someone was trying to say something, but I can't hear them clearly. Let me see.
Given there are very few women in engineering still, what advice can you give these young women on how not to be intimidated when they're in a room full of men?
Oh, okay. So I have to tell you a little secret, okay? So usually when I first started out, I think the number of women in engineering was 2%. I think the number is now maybe 5 or 10%, right? We haven't gone that far. And my trick is this. Number one is that when I walk into a room and there's a sea of men, and usually there's 1 or 2 women, you know what usually I notice? Those are the best, smartest, toughest engineers out there, right? You have to be, that's just the way it is. It is challenging, it is tough. But one thing I really like about being an engineer and being with other engineers is that there is a language that we use, right? Whether you write code or whether you build cars or whatever it is, there's a language that we use. And I think that once you speak that language, I think it's easier. I think it's probably easier to be a female engineer, oddly enough, than be a female lawyer. In fact, I know that for a fact. I have lots of female friends who are lawyers, partners in big law firms and such. It is intimidating, it is tough, but well, that's what it is. And realizing that there are a small number of women in the organization, look out for each other, help each other out, be kind to each other, nurture each other. Don't stab each other in the back, right? Look out for each other. Make sure that you get the sisterhood going, okay? And in fact, some of my close friends are like that. We usually seek each other out, and we usually sort of get each other's challenges in a way that our male friends, our male colleagues don't. Anything else?
I've been asked, what can we do to keep women engineers to stay on Midway in their career?
Oh, that's a great question. It's not just engineers. A friend of mine graduated from Stanford Business School, and she said that when she went back on her 20th anniversary per year, half the women stopped working. They've done something else. And I think this is the problem that we have, as I said before, because many of these women who work in high tech become disillusioned because we say, well, it's great. You can go work for Facebook, right? To get how many clicks in their ads, or you can go work for DoorDash to see how many people will order food online or whatever it is. So I think that one of the things that for many women, for many people, but I think especially for many women who work in high tech, is they say, what good is these things? What good are all these technologies? That's why I encourage you to go and look and say, how can we use this technology to make a better world? It's important. It's very sexy and it's very profitable to go and solve problems for the top 1 billion people in the world, right? That's what everybody is doing in the Valley, pretty much. I'm encouraging you, especially the women who are questioning the value of technology and their place in high tech, is to go and say, okay, so how are we going to use this technology for the bottom 6 billion people? I think that women will stay around longer and they will work harder and they will push more because they will see the work that they do is meaningful and is important. And in fact, you already start seeing that. Any other question?
I'm just checking the YouTube chat. Well, I think we've run out of questions.
Okay.
Been on here for a while. Oh, actually, Ivan has another question.
Yeah.
Are we more innovative or less than before? Wait,
Okay.
less than.
I think that's a great question. That's a great question because I think yes, I'm answering yes to both. I think because in some way we are all victims of the success, right? We all look at Silicon Valley, we all look at the Facebook of the world, we all look at the Instagram of the world, and we say we want more of that. So in a way, we are less innovative. But if you go look and all the stuff, look at what the speaker before me was talking about, how to use, programming to work with bees. That's incredibly innovative. That's incredibly interesting. So there's also a bunch of people working on these really interesting, really innovative projects. Okay, so the answer is yes in both ways, in some very sort of perverse way, that we look at the success and we want more of the same thing. And we don't think outside the box, and we're not really asking the hard questions like, okay, so what's beyond this? That's a great question.
Oh,
Yeah,
someone asked, what was moving to the US from another country like?
Oh, I came to the United States when I was 15 years old. And how many of you guys are 15? Is anybody here? Everybody's a bit older than 15, yeah? Okay, so I think at 15, I was very arrogant. I was very arrogant. I was very cocky. I thought that I could conquer the world. I thought I knew everything already. So to me, coming to the United States was like a game. It's sort of, I don't want to minimize. It was very tough. I was a foster child. I moved to 3 different foster homes in 6 months. Okay, I went the worst at the time, the worst performing high school in the state of California. So I don't want to minimize the tough times and the difficulty that I faced it. But at the same time, I bought into the idea that this is the land of opportunity, that if I'm smart enough, if I work hard enough, I will get to where I needed to go. In some way, thank God that I was so naive, because it's not true, okay? I succeeded in a lot of ways because I was lucky, far more than I was smart, or far more than I was because I was hardworking, but I was very lucky. But coming to America, sort of, for me, a chance for me to live that American narrative, that why all of us immigrants, most of us immigrants coming to the United States, was I was gonna get my American dream, right? I was gonna go for the brass ring, and I'm gonna wrap it with both hands and hold on.
And in high school, were you able to like access any STEM opportunities?
I'm sorry?
Were you able to access any STEM opportunities in high school still?
Yeah, so when I was in high school, because I went to the worst performing high school in the state of California at the time. So in a way, when I walk into the classroom and I wanted to learn, I wanted so badly to be, I didn't speak English. I didn't have anybody to support me. When I walk into that classroom and they can see the fire in my eyes, they can see that I would do anything to succeed. I was willing to work hard. I was willing to do whatever it takes. All the teachers and all the counselors and all the administrators were just there for me. They just could not do enough for me and supported me, right? I went to a community college to take classes because there wasn't enough AP classes in my own high school. So I ended up taking calculus and chemistry and physics in the local community college. And that was at the urging and the support of my own teachers and my own administrator and my own high school. So, you know, I was very lucky.
Last thoughts?
Okay. So,
well, oh yeah, go ahead, sorry.
So again, I really want to encourage you guys to go look beyond the obvious. And if you're wondering what the hell I'm talking about, just go outside and look at the world without any motive, without any preconceived notion. And you will see, I have a little notebook I have on my laptop and on my iPhone that I write ideas all the time, right? Every time I see something, you know, why something is not working or how I think something could work better, I would write in the notebook. I would encourage you to do that, okay? Don't accept things as they are, okay? So we have Google today. Well, what's beyond Google? We have Facebook today. What's beyond Facebook? Okay, don't just accept what we have now and say, well, we're just gonna fix it a little bit, make it a tiny little bit better. What if you blow up a whole model and start again? What would you do? Okay, somebody asked me, you know, what's the hardest thing for me to do? Those are the hardest thing to do, to say, okay, what if we create a new paradigm? What would it look like? How would we make it work? And how would we make it accessible to everybody? Okay, ask those questions. And as long as you continue to ask those questions, you will find meaning in what you do and you will love what you do and the world will be a much better place.
I wanted to ask too, is there any type of engineering that you feel is most socially relevant?
You can do any kind of engineering and make it social relevant because you will ask the right questions, right? You know, you're going to build a better motorcycle, right? You are going to create a better roof, which is what one of my entrepreneurs is working on, right? You are going to create a better network. You're going to make better, you know, better way to deliver energy. Any kind of engineering you can think of, you can make it social relevant. It is entirely up to you and you alone to figure that out. Okay? And to have the courage to say, this is what I really want to do.
All right. If those are all the questions, thank you so much, Dr. La. I know you stayed.
Thank you.
A lot longer than you
Good
had
luck.
originally planned. But yeah, thank you so much for a very inspirational talk. I hope that everyone really enjoyed that.
Thank you. Bye-bye.
We're going to resume in 2 minutes. Wow, marathon right now. We're going to resume in 2 minutes with Allison Jia, who's an amazing undergraduate student at Stanford University. So tune in or stay tuned for that. It's not here already. All right. Oh, I'm gonna take a stretch break. I've seen some of your guys' names on for like hours, so congratulations for those of you who've stayed on since like 8 a.m. Okay, can I get like a general sense of interest? Who here would be willing to, or who would want to come to like the networking session and just like play icebreakers and get to know each other better at, yeah, I mean, me and Catherine. It's gonna be delayed though, because everything is pushed back 30 minutes.
Just out of curiosity, like, is that just like with everyone who's on the call, or is that like with like the speakers and stuff as well?
Oh no, that's just with us. That's just with that. Well, there are a few speakers actually on the call, or I see one. I'm not sure how active they are. Yeah.
I think there's actually 2 or multiple.
I saw Dr. Idala earlier, but I think she just left.
Yeah, and then Ms. Romer's also there.
Yeah, Dr. Finn. Did you say Miss again?
Yes.
Oh my God. All right, we can actually we'll just hang out after the, oh, Allison's here. We'll just hang out after the award ceremony instead of putting it before. Yeah, I saw. Okay, everyone, we are getting started with our next speaker. Just give me 1 second. Where is Allison?
Hey, Diana.
Oh, hi. Okay, I found you. All right. All right, everyone, please welcome Allison Jia. She's going to be our first college student speaker of the day. Allison is a student researcher, aspiring biomedical engineer, and a recently graduated senior from the Harker School who's now attending Stanford University in the fall. Allison received the Intel Foundation Young Scientist Award at the ISF, or International Science and Engineering Fair, for her work in creating a live imaging platform to visualize the neurodegeneration process responsible for diseases like Alzheimer's. So without further ado, we're gonna get started. This is basically gonna be a discussion between us and Allison about any tips she has for college advice, any tips she has for specifically like biomedical engineering. So I'll start off by asking a few specific questions that we've already laid out. And then if you guys have any questions, just feel free to pop them in the chat and we can always address them. So our first question for you, Allison, thank you so much again for joining, is why and how did you become interested in biomedical engineering?
Well, first of all, I want to thank you, Diana, for inviting me here today. Seems like, it's going pretty well. I'm glad everyone is learning a lot. So I guess the reason why I'm interested in biomedical engineering and just bio in general, it stems back to what I did in, lower school and middle school, actually, I'd say. Going back to lower school, I feel like I've always been pretty interested in biology. And I don't know what it is. I think maybe the hands-on activities, and I remember in 5th grade, one of the strongest memories for me was when we dissected a worm in our 5th grade biology class. And the guy sitting next to me was like, ew, it's a worm, I don't want to touch it. But I was like, oh my God, give me the knife, I want to do this. So I really enjoyed that aspect of biology where it's, you got to be super hands-on and you got to really just put yourself out there and dig in. And so that was really where I first started getting interested in biology in general, I'd say. And then as for my research, it's a lot of research surrounding neuroscience. My interest in neuroscience kind of stemmed from middle school, where I'd participate in a lot of middle school summer camps, for any middle schoolers out there right now, at middle school summer camps at like our local museums. I did mine at like the local tech museum, where I got to learn a little bit more about I think we dissected a cow brain in one of the summer courses. And then I got to do a lot of other really cool hands-on biology things, and I started learning more about neuroscience in 8th grade-ish. I did my first 8th grade research project thing. It was a behavioral science project, and that really got me interested in neuroscience. And then in high school, I was part of the same organization that Diana is part of right now, which is Society for Neuroscience in the Bay Area. And then there I got to learn a lot more about, we heard from a lot of really great speakers who are in the field of neuroscience, doing a lot of really cool research. We did our own brain dissections for students, free for students around the Bay Area, and so many more activities. And I think that, just learning about neuroscience as I go throughout high school, learning more about biomedical engineering as a whole, just really kind of cemented my interest. Again, I'm going into Stanford undecided, but I do think it'll probably be somewhere in that field. Yeah, very long answer.
This is a more specific question, but if you had to choose between majoring in neuroscience and biomedical engineering, which would you pick?
It's a good question. I think I still have to do some more research into that. For me right now, I just think something that I've been finding pretty cool recently is the medical devices. And so, or wearable technology, for example. So some things that I thought were really cool were there's something called an e-tattoo, which is a material that you can put on your skin and it helps you measure. It's a tattoo that measures your vitals, whether that's your heart rate or your, that's the only one I can think of right now, but there's more that it measures. And it's pretty cool. And I just think technology like that is super interesting. So right now it's more biomedical engineering. If I can include something with the neuroscience, if the what's it called? There's a better word than this. It's not brain prosthetics. That's not the word I'm looking for, but it's the idea that the electrical activity from your brain can stimulate muscle movement and stimulate some muscle.
Oh,
movement. It's not though. It's just not coming to me right now.
Like BCIs?
Yeah, I think so.
Yeah. Brain-computer interfaces.
Yeah, brain-computer interface. That's what it was. My brain just blanked. Yeah.
No worries. Awesome. Well, I know you mentioned SFN and some of your middle school summer camps, but what are other important activities? I know you did research, maybe other competitions, internships that you did to get more involved in STEM and that really inspired your interest.
So what other things I did?
Yeah, what other activities?
Yeah, so in high school, I was I guess my biggest involvement was my 4 years in Bay Area Society for Neuroscience. I'd say that was probably the biggest. I guess outside of I had my own separate research internship, so I guess those two were my two biggest kind of science commitments. Society for Neuroscience was more of like a community than I feel like it was, you know, when you're in a research setting and you're more working, you know, you're learning things from reading papers, you're like designing your own experiments, doing the hands-on work. Whereas I felt like Society for Neuroscience was more of meeting other people like Diana, who is equally as interested in neuroscience as I am. And so those were like my two biggest activities. And I think it was a pretty cool balance. One is like super academic focused. The other one is more of a community-based organization, but still around an interest of mine. And then some other, so beyond research and beyond SFN, I also was the vice president of our school's research club. And so if any of your schools have research clubs, I really think that it's a great opportunity to get involved. What we did, we held like monthly workshops on things like how to get an internship or introduction to science fair, or, you know, how to communicate your science to an audience, because that's super important. And then another thing I was really into in high school was we had a student-run science journal as well. So it's kind of like journalism, but obviously for science research and science articles, where I wrote 2 debates with like another one of my friends. One was on the pros and cons of gene patenting, which is like, for example, if I just want to like take this, like if I find this gene segment really interesting, I want to patent that so I can do all the focused research on it and no one else can take my like study that same DNA sequence, I guess. And then so we wrote about the pros and cons of that. Another example, we wrote about like the scientific merits of Eastern medicine. And so that was a really great way to get me more involved in learning how to like write, like not verbally, write and communicate science, which is like another very important skill too. So I think those were pretty much my biggest science related commitments in high school. Yeah.
What was like your biggest or like your most significant resource that helped you get to Intel and ISA?
My significant resource? Oh, what do you mean by like resource? Like
if it was like a mentorship, if it was the support you had in your research club, or
yeah. Then I would have to say it was definitely my mentor helped a lot. So I think because I'm the type of person, so I ask a lot of questions. So I kind of felt bad for my mentor sometimes. I just like hammer him with questions. And then I asked him for some papers to read. So I always went through those. If I didn't really understand, I'd like write it out as a specific question and then ask him at like the end of the day, like, I didn't understand XYZ in the reading. And then we, through the lab meetings too, I'd say like the support that I built in my research internship was extremely invaluable. I got to work with 2 other undergrads in the lab, and then my mentor, another senior scientist, and of course my PI. And I think that support network was definitely very useful. If I had any questions whatsoever on like a lab procedure or on a technical term that I didn't understand, you know, I feel really comfortable asking them like, hey, I didn't understand this. Could you explain this to me? And then if, you know, like when I learned how to, in the lab meetings, when I was presenting my science, if my mentors have any feedback to give me, they would always help me with that. And so I think that also helped me fine tune, first of all, my understanding of what my research was about, and second of all, how to present my science effectively. So I would say, yeah, my mentor, my not even just a mentor, but my mentors, plural, in the research setting was my greatest resource.
I have a question. How can you get access to a wet lab if it's really hard? Because like some schools don't offer research programs like Harvard.
Yeah, for sure. So that's actually something we present on in Research Club. At least for my lab, I think you have to be 16 years or older to work in a wet lab. And you have to be 16 years or older to work in a wet lab. And then so a great like resource that we tell students is to reach out to postdocs in labs. So not just like, you know that when you like open a, for example, you want to intern at, I'm just going to bring up my own school, like Stanford University, for example. You can first Google the fields that you're interested in. So neuroscience, just another example, and you can see the different labs that these professors are working in and see their specific work. And then if you want, you can make a spreadsheet of like specific labs that you think are are doing some pretty interesting work. And then contact the postdocs in the lab, who probably have a little bit more time than the PIs of the lab to like read through your email and ask them for an internship that way. Or you could do some like reading about like some of the papers that they may have published in the past, and then try to like reach out and ask for questions. And then if you develop that relationship with the PI or with the postdoc, then it's typically much easier to get an internship. Yeah. Hope that helps.
Yeah.
You have a question here. Where did you do your research? Was there like a specific, what specific lab or internship or mentor did you work with?
Yeah, so I did my work at Stanford University because it's pretty local. This is where I'm going, but it's pretty local to me. I live in Cupertino, which is like 20 minutes away. And so I worked there over the summers and over my school breaks too. And then I worked in the Department of Neuroscience, the Yanmin Yang lab. So my work was doing a lot of work with microtubules and like a specific protein called tau, which is in charge of holding these microtubules together in the cell. So that was just a very high level summary of what my research topic was, but I'd be happy to talk a little bit more about that too.
Oh yeah, you can take that.
Okay. So I see in the chat that Michelle has a question. Do you have any advice relating to presenting / talking to judges? This is a super, like presenting your science in general, I think is a super important skill. I think I've mentioned this before. Advice related to presenting or talking to judges is to, and you might have heard this already, but it's like to keep it like a conversation. So a lot of the times when students present their science, maybe it's nerves, but maybe it's something else, but they'll feel a little bit like rigid or robotic in a way where they're just kind of reading off their poster board. Make sure that when you talk to your judge, it's a conversation. Like they're not trying to poke holes in your research. Like they know that you hear, because when we're all high school, I'm not anymore, but we were all high school students. And so they're just trying to understand the work that you did and like how much you understand as well. So I always tried to keep it a conversation with my judge, and then give them a quick overview of like what your research is, and then ask them if they have any questions they're interested in. In terms of also, I guess, so that's more of like talking to judges. In terms of presenting, I've always found it pretty helpful. So I was lucky enough to have like one of my best friends. She's also pretty into science fairs. And so before the science fairs, we'd actually present our projects to each other. So her project was a chemistry project. My project was a molecular cellular biology project. And so we didn't really understand each other's fields, which I thought was very important when we were presenting, because then if I presented my project to her and she didn't understand something, I'd have to figure out a way to better phrase whatever it was that like I'm trying to present, so that it'll be clear for her, because chances are if she doesn't understand it, maybe a judge probably won't understand it either. So we would do that to each other, and I think it was a pretty great way to get started on like presenting. Yeah.
What do you feel has like really helped you get into college and into like Stanford University?
Yeah, that's another great question. I really don't know, but I honestly think it was probably my ICEF experience and the award that I received at ICEF. Obviously that's just for me. Like that's not it's you don't have to get that award to get in, and like definitely not. I was fortunate enough to receive that award, so I think that did help. I will say though, I think what else? I really do think like the other activities I did too, like Bay Area SFN, also helped a lot. Just to show that I was more of like a well-rounded student. I guess it was still STEM. Honestly, I don't know. I think I'm gonna like pinpoint onto my ISEF award, but that's
So
just.
do you feel like it was more like the activities more than like the essay and stuff like that?
In my specific case, I'd probably say yes. But again, I'm not admissions, so I really don't know.
I got a question, like back to the internships. I feel that it's like getting an internship with one of these I don't know what I don't remember what they were called, but
Yeah.
seems like pretty hard or complicated to get an internship or a mentor from like a specific person that like seems to have so much work on their hands, plates, all that research and all that stuff. So where do you recommend that we start or go to get resources on who we can get a mentorship or internship from? And what do you recommend that we do to ensure that they'll accept you?
Yeah, that's a great question. I think first of all, I know it seems super intimidating to reach out to like someone who's done like this groundbreaking work. You're like, oh my God, I'm just a high school student. How am I supposed to ask them for an internship? I understand that can seem super intimidating, but after you get to know them, at least they're all humans at the end of the day. And so one thing they do, I know they do, like you mentioned, they're very busy. So if you show that you have that initiative, that you've taken the time to do that background knowledge, they don't necessarily want someone who's going in the lab and saying like, hey, I don't know anything about your work, but can I have an internship here? Then there's like a low probability that they'll take you on. But if you've shown that you've done some research into like what they're doing, you think, hey, like I think that your work on microtubules is super cool, or I think your work on DNA sequencing is really amazing. And then maybe if you have like a couple specific questions or like stories even relating to why you want to work to their lab, it helps them realize that you're not like that they don't have to put as much work into you because you're the one who's like willing to put that work on yourself. Does that make sense? I'm not sure if that. Okay. Yeah.
So I have a question about your research. So when you were working under the guidance of your mentor, was it the lab's research that you submitted for science fairs and ISEF, or was it your own individual research?
Yeah, so my research was actually an independent project. So it was like kind of a side project to the labs. Like it was still related to microtubules, but my research is more focused on a protein relating to microtubules rather than the microtubules themselves. So that was more of like I wouldn't say it's the lab's like focus. It was more of a side project.
Oh yeah, and then my second question is like, how's your ISEF experience? It's like it's always so cool to see it from the outside, but I don't know what's like.
I really enjoyed my ISEF experience. I thought it was one of the coolest things I've ever been in because I got to meet a lot of teams from around the world. One thing that I remember was that really sticks out in memory was, there's like this public showing day where you can just walk around and you can see teams who've done work from around the world. And I've never taken a Spanish course in my life, so I can't speak Spanish. But one of my friends who did, he was like from the same Silicon Valley fair, who qualified with me. He was like, Allison, like come to this booth. And it was a group from Peru, and he was like, and then he started speaking in Spanish to them. He was like explain to her your project. And so they explained it to him, who translated it to me. And then I asked him questions and he translated it back to the group. And so we had like a kind of like even though we don't speak the same language, we still spoke the same science, I guess. So that was one memory that really stuck out to me.
Wow, that's so cool. Wait, I just have a quick question about like your mentor. So was your mentor like from the lab you were interning for?
Yes. My mentor was the senior scientist of the lab that I worked at. Because so like if I had questions on, so a lot of the stuff, like the question that I explored wasn't really explored before, but obviously as a scientist who's been working in that field for so long, he knew a lot. So definitely helped.
What was your lab called again? I didn't quite catch it the first time.
The Yen and Yang Lab, Department of Neuroscience.
Oh, Michelle asked, what other competitions did you enter? And I'm also curious, did you enter like any Olympiads?
Oh yeah. Actually, it's something I should have brought up. I forgot. So well, in terms of science fairs, I entered JSHS, which is a pretty popular one, Junior Science and Humanities Symposium. And then I also entered, in terms of Olympiads, yeah, I took the USABO, USA Biology Olympiad. I took that twice in my freshman and junior year, I think. And I got semifinalist, but I remember when I was taking that semifinalist exam to go to finalist, I literally was staring at the questions. I was like, I have no idea. So it's hard. Like those exams are pretty difficult. Yeah. And then what other competition? I mean, I've done a couple like math competitions too, like AMC. Amy wasn't too good at Amy though, but yeah.
Wait, but you qualified for Amy?
I qualified for Amy.
Oh, okay. All right. Oh, I think Catherine asked earlier what your favorite research project in high school was.
I'd probably have to say was my ISEF research. I like to call that research my baby because I put a lot of effort into that one. I guess to explain it briefly, I think Diana gave a super, like a high level explanation that I told her, which is essentially there's a protein called tau, and it's a protein that helps basically stabilize the cell structure. And so when this protein becomes mutated, it turns into these like toxic clumps that start clumping together more and more. And then all of a sudden the cell cannot stabilize anymore. And then when you have when the cell eventually dies because it's not stabilized anymore, these tau clumps actually have the ability to somehow escape the dying cell and be uptaken by nearby healthy cells, healthy neurons. These are all neurons, by the way. So healthy neurons. And then that transmission process causes this whole domino effect of dying neurons, which essentially is neurodegeneration. So my project was to visualize the uptake of the toxic tau clump into into the healthy neuron. And that's called like a transmission process. So I ended up creating I ended up capturing a real-time video of that process. And so, yeah, that was my research. It's my baby.
Yeah, I have one question. How do people come with like ideas for ISEF or like in science fair? Like, how can you formulate an idea for that can, you can enter into a science fair that you'd feel like would do okay or well, that you like?
That depends on choosing like a field that you're interested in, right? I mean, I don't know what fields you're interested in.
Let's do biology because honestly.
Well, biology is a very, very broad field, whether you like you like genetics or you like behavioral psychology or something like that. So it's a pretty big, broad field, but in like whatever specific direction that you're generally interested in, I would say do some general like research. When you look at like what professors you want to work with, you can look at some of the research that they've done, and then you can start asking yourself questions and then have conversations with other people. Like the fact that you're already at this conference here, I'm sure you've already heard from a lot of really great speakers, and if you think they're doing really, really awesome work, there's no harm in trying to reach out and just be like, hey, I'm interested in what you're doing. And then they're all busy people, so if they don't respond, don't take it personally. But it's a good way just to ask questions, because and I'm sure like science is like never ending, right? There's always some question to be answered. So when you show that you have the background knowledge, and when you show that like this is when you start asking questions about like the papers that you're reading, then that automatically leads to new conversations and then new questions that you can explore.
There's another question from Matthew, different from the current topic, but why did you decide to attend Stanford for your undergrad?
That's a great question too. So I got to know because I worked at Stanford in high school. I got to know 2 of the Stanford undergrads there, and I really enjoyed working with them. They always had super interesting stories. They were really friendly people, and I just enjoyed working with them in general. And then I think for me, at least, if I wanted to study, bioengineering, I thought that Stanford was a pretty great place to do that, to explore a little bit more. All the mentor I had at Stanford too was incredibly formative for my science research journey. Like, he was always open asking to answering my questions, and then like reaching out or things like that. And so I think just the support I got from the Stanford community, and then the continuing, like, the cool programs that they have at the school too, made me choose it.
Yeah, I want to ask about like all the competitions and stuff that you've done, and I want to try not to come off as like offensive saying this, but what is the benefit for you in the future, like after you finish college and everything? What is the benefit for you getting all these rewards and doing all these competitions and stuff like that and getting?
Yeah, that's not an offensive question at all. Don't worry, I'm not offended. I guess when I graduate college, that is a great question to ask. Like, what benefit do I do from having had experience with all these competitions and the awards? I think that it's like the skills that I gain from doing these competitions. And so when I'm in science fair, I'm presenting to a judge. When I'm doing USABO, like, that means I probably studied some like biology concepts, right? The presenting my science to a science fair judge, I'm 100% sure will be useful for me in the future, like, no matter what I do. Presenting anything to anyone is just such an important skill. There's that saying, it's like, if you have a great idea but you can't communicate it, then like, what's the point? This is not, I'm just paraphrasing the quote, but it's like something about that. Like, if you have a great idea but you can't communicate it, then there's really no point to your idea. So like, that kind of skill, I think, that I got from doing science fair, I'm pretty sure will last me for a lifetime. And then the award itself, you're right, it past college probably wouldn't even matter. But the fact that, the skills that I gained from there, and the friends, like, our ISEF chat still has, I think someone made like a Facebook message and there's like a couple hundred people in there, and they still chat like day to day. Like, those friendships too are really invaluable. And then like the story from me communicating with the Peru team, even though we don't speak the same language, I think that memory and that motivation for me to keep doing science is that's what's valuable from doing all of these. Does that kind of answer the question?
That was helpful. Thanks.
Awesome. Well, it is 4:30. Thank you so much, Allison, for joining us. I hope everyone enjoyed her talk and our discussion as much as I did. Allison has some amazing advice. If you just tuned in, you should go and watch what she was talking about. Now we're going to transition to CS and engineering. So a little less bio involved. But again, thanks so much, Allison. And I'll hand it over to Faith.
Hi, guys. Oh, sorry. So now we're going to be I'll be introducing our college CS and engineering panel. So all of our panelists are from Brown University, and I'll just do like a little quick intro of each person. So first we have Ashley, and she is involved in many STEM women's clubs at Brown. Nick works at a fashion tech startup. Lauren is human-computer interaction at the Brown HCI lab. Samantha, in addition to studying CS, is considering pursuing a degree in computational biology and attending med school. And Anna is an intern for a nonprofit startup where she's developing a website portal. And David conducts research at the Brown Visual Computing Lab. And lastly, Ellen is currently researching in a paleoclimate and studying potential ocean biomarkers. So if all speakers would turn on your videos and start your panel. Thank you.
Hi, so my name's Ellen. I'm a rising sophomore. I'm the one who's studying mechanical or environmental engineering. And I'm currently in this lab studying paleoclimate and like biolipid markers for researching climate change. So I guess something that I could give insight into is how to get involved in research once you're in college. So I was actually kind of lucky getting research because something that I think you should take note of is that you definitely want to contact a bunch of professors that you're interested in your first semester, because by second semester, they might already have spots full. The only reason that I actually got a spot in the research lab that I looked into was because he was going to have Chinese students come from China, but obviously they couldn't come because of COVID.
I can go ahead and introduce myself next. I'm David Hahn. I'm currently thinking of concentrating in applied math, computer science at Brown. And for me, I'm involved in the Brown Visual Computing Lab at school, and it's kind of a focus on computer graphics and stuff. For me, I kind of want to talk about the question a lot of people have of how I got interested in this field. I'm someone that actually went into college with zero CS experience, had never taken a class, didn't know anything about it. And my first kind of intro to it was taking a class in college. And I think it just proves to show that you don't really need to have a lot of prior experience. If it's something that you want to kind of explore, something you're interested in, just go ahead and take a class. Maybe you'll like it, maybe you'll hate it. So yeah, I'd just say like getting into CS field might seem a little intimidating, might seem a little scary. But at the end of the day, you have a bunch of friends to help you out, and you can really learn a lot in just a year. So yeah, I'd say going into college, especially just kind of taking one course, seeing if you like it. And then from there, looking into research positions or internships, it's definitely a doable task for sure. So yeah.
I guess continuing on the CS bandwagon, my name's Nick. I'm studying pure math CS at Brown University. Me and David work together. That's why I felt it was apt that I go right after him. But yeah, if you have any questions about going into industry, I'm currently in the process of recruiting. If you have any questions about how to get into CS, I too came to Brown with like not so much CS experience. Like I started the spring before, but I had exposure before that. And if you have any questions about like the industry as a whole, any classes or mathy things you might like as well, I'm open to answering those.
So I can go next. My name is Ashley. I'm a rising sophomore at Brown too, and currently I'm thinking of concentrating in electrical engineering and computer science. And I'm mostly involved in like the Society of Women Engineers at Brown, so getting really involved in clubs that are promoting diversity in engineering, especially for minorities. And if you have any questions about being a female in STEM, that's definitely something that I'm really passionate about. And also for me, I came in with a very like bad view of CS. I didn't really have any interest in it. And I was one of the people that didn't really have any experience in CS before going to college, but I took one class and decided I really liked it. So if you have any questions about having like a double concentration in engineering and CS, trying to combine those and having those kind of cater to your interests in those specific fields, I'd be happy to answer those too.
Yeah, I can go. My name is Lauren. I'm also a rising sophomore studying computer science and possibly psychology. And so one of the things that I wanted to sort of talk about was how to find a community within CS. Just because when you're studying computer science, it's really important that you have this group of people that you can go to like, whether it's like seeking them for help with your classes or, you know, asking for mentorship about a specific, you know, internship that you're interested in or a research position that you want to do. So at Brown, I'm really involved with Hack at Brown, which is the organization that organizes Brown's annual hackathon, and also the Women in Computer Science organization. And both of those are really good resources for you to reach out to upperclassmen and professors and people who are already working in industry. So if you have any questions about like how to find a good community, whether that's in college or in high school, then feel free to ask.
I can go next. So my name is Anna, and I'm also a rising sophomore at Brown studying CS. I'm not really sure what specifically I want to do with that yet, but college is a great place to dive into every field and take like one class in every field so that you can figure out what specifically you want to do. CS is a really broad field, and so it can seem very daunting, but college is a great way to figure out what specifically you want to do without having to commit to something super immediately. I also wanted to touch on the fact that I know a lot of you guys are high schoolers and you might be scared to apply to like a super STEMmy school without a lot of STEM background. So I decided that I wanted to do CS halfway through senior year, and I applied to some very CS specific schools without any like CS background, and I was able to get into some of them. So if you're worried about not having like internships to back up, like some kids in high school get started really early, I wouldn't worry about that if you want to apply to those kinds of schools anyways, because not everyone starts off like running. Like it's okay to not have an experience and still apply for those schools if that's what you're interested in.
I guess it's my turn. I'm Sam. I am a sophomore at Brown, and I didn't know what I wanted to do going into school. So I kind of went in like pre-med-ish, kind of just like testing the waters. And I feel like Brown's a really good place for you to do that. You can really experience every option at Brown. And my first CS class was actually my first semester at Brown. And I kind of just took it because a lot of people I talked to said it was like the best class on campus. So I kind of just like went in, and it definitely was hard without any background, but you can definitely go through, especially with like all the TAs and the support and all the friends that you make in the class. And from there, I think I definitely realized the opportunities that the CS field has. So from there, I think I'm probably going to major in computational biology just to stay on that pre-med track, but also incorporate some CS into it.
All right, thank you for all of your introductions. So we're just gonna have kind of like 3 separate sessions. So first, if you guys have or want to talk about tips regarding college admission, so when you guys were applying for your specific field of study, and then ways or advice on how to get involved with STEM in high school or college. And then lastly, we'll do Q&As. So either people within this current Zoom will type questions into the chat, or we'll take the questions we have from our YouTube live stream. So first off, if you guys have any tips on like college admission and like that whole process.
I guess I can start since I started last time. So I know it might seem daunting sometimes when you like, it's hard to figure out what you want to do in high school. I mean, a lot of us probably don't even have it nailed down yet, but it does help if you're applying to like engineering or CS to, especially if it's a separate school within the college, to have some, like some background interests that can back you up. So definitely look into some camps that you can attend. I attended the SAME, which stands for Society of American Military Engineers camp. That one's really good. They have a ton of locations all over the country. And another thing, don't focus on stuff that kind of like looks good on an application. It really, I think it shows more when you pursue something that you're passionate about, like, maybe just organizing something in your community. Yeah, that's all I have to say.
Kind of piggybacking off of that, nowadays, like a lot of students have the test scores to get into the colleges that you want. So schools are more looking for your personality and your passions to shine through. So even if you don't have the experience or anything to back up what you want to do, if you can show colleges that you're super passionate about what you want to do, and if you realized it late that you're still taking steps to pursue this passion, colleges will see through that, because the scores are kind of like a baseline now, but that's not the determining factor. Like if you're super passionate in something, they will take a chance on you. It doesn't just have to be based on experience.
And one thing I want to add on to that is I think in college admissions, or when you're just applying to anything, it's really important that you have a story. And so really thinking about like what makes me different from every other applicant or even anyone else who's interested in CS, like what's my story and how can I market myself? That's really important just because it helps you stand out in admissions officers' minds, I guess, because when they talk about you, they can reference you as this like one person who's like really interested in like computational bio or like game design, and they have that like sticking point. And yeah, so just finding like your brand is really important.
I think a lot of panelists are going to bring like a lot of advice on like things you should do about your application, things you should do to frame yourself. I'm going to give a little bit of advice about how to survive the process as a whole. So I don't know about everyone else attending this panel, but I'm an international student, so not a lot of people from my school apply, or a lot from my country apply to like other countries. And moreover, like sometimes it can be really daunting when you are in like certain spheres and everybody's applying for those same schools. They're all gunning for the same positions. And those schools historically only take like 1, 2, or no students from your schools. And it's like, even if you aren't in my situation, the whole process is incredibly stressful. And you're going to be writing applications, like studying for tests, like whatever it might be, for like a good 2 years. And that's all that's going to be on your mind. And I just want to give some advice on how to survive that. The biggest thing that helped me get through my entire college admissions process was focusing on myself. I found that a lot of times when like I would look at other people and be like, wow, that guy has like ISEF, that guy has like so much good CS stuff, that guy's really good at like debate or whatever. And I'd stress myself out worrying about it when I forgot to realize that like, hey, I also have really great accomplishments that I can leverage to get into college as well. And like every second that I wasted comparing myself to other people was like just that waste. Moreover, I think that it's really important to like when you're writing your essays, also focus just on yourself there, because the more time you spend like reading other people's essays or getting people to look at your essays, the more voice you lose from your own writing. And that can be really dangerous, especially when you end up having like 20 people collaborating on the same piece of work and it's nothing like you would have written by yourself. I want to keep this a bit short, but remember to just focus on yourself, focus on your mental health, and focus on making sure that like you are running this marathon like a marathon and not like a series of short sprints.
Thank you guys so much for your insight. We actually have a lot of questions coming in both from the live stream and the chat, so we'll just address some of those. So someone asked, can you guys talk more about like the drawbacks to open curriculum at Brown, like if you think that there are any, and your experiences with, you know, Brown, you being very distinct in that way?
I think I can take a stab at this question. I'm someone that's a huge fan of the open curriculum, especially because I was someone that applied as a business major, and I'm CS now, which is kind of totally different in terms of prerequisites and everything. And I just think like it gives you an opportunity to have some buffer room, have some time to just take the classes you want, explore. Like I know out of everyone in this chat and also in general, most people are taking 3 classes in their concentration and then 1 class in astronomy or history or I don't know, Middle Eastern studies. And that's something that the open curriculum really allows you to do, given that you have time, you don't have those like PE general requirements or that English class that you would never really take if you were a STEM major. And obviously having some sort of foundation is good, but I think Brown is a really good combination of that, as it requires us to take writing courses for the STEM people. And you also are required to take some foundational math courses. So in my opinion, I have not yet have any complaints with the open curriculum. I think it's something that's definitely special to Brown, different from all other schools. And it's one of the reasons why I kind of love being able to pick different courses here at the school. So yeah.
I think
Okay. Oh, I'm sorry, go ahead.
It's all good. I think the only drawback I've really seen, I don't even know if this would be considered a drawback, but Nick mentioned in the chat, like other than the curse of choice, I guess like the only time I've seen people struggle with the whole concept of the open curriculum is when there's like too many classes that you want to take. And if you don't really have any idea of what you are interested, that might be a little hard to kind of find classes that you might want to take for your concentration. So I think what would help combat that would be to kind of just have a general idea of things that you're interested in. And Brown has like hundreds and hundreds of courses, so in all different types of concentrations. So that might be a little difficult, but that's really the only drawback I've seen. And that is definitely something that I feel like could become useful because you'll be able to explore so many things. And yeah.
Okay, so moving on to the next question. Has anyone here been in Science Olympiad? And if there are pros and cons for college apps? I don't know why David is laughing.
I definitely did not do Science Olympiad. I hope someone else did.
Totally okay. The girl before who spoke did a ton of stuff in College Olympiad. So we can just move on to the next thing. So how do you demonstrate interest in your application? So this kind of goes back to that question of like the admissions process. If you have any further insight on how to show like interest in that field, whether it's CS or any of your like minors that you guys are doing.
Do projects, write about those projects. Again, if you don't have a lot of time of CS experience, like recognize that you are a full person and you are a full person that has done many, many things, and writing about the specific thing that you're going to study is not like the only way to go. Like I wrote all about Hong Kong. I wrote about a coffee shop or a bubble tea shop. I don't remember which. And I wrote about like the open curriculum. Like I didn't really write about CS at all because I applied for poli-sci. So like, again, like you're a whole human being that has many facets. You are more than just like the academic field you study. So just remember that, I guess.
I would also say it's good to pull in your interests outside of STEM and see how you can possibly integrate that into the STEM field. Like colleges don't just want students who are going to study well at their school, but they want students who are going to do well with that education. So they want to see what applications you could possibly think of with your degree. So if you can find ways to show like your personal interest, like if you have a sport you're passionate about, something like that, how you can tie that into STEM. You don't have to know specifically how to do it, but if you're interested in pursuing that or like even researching about that, colleges love that, just to see like you're interested in something and passionate about learning more.
All right, sounds good. So this kind of goes into what happens after you guys go to college, but like what jobs do CS and engineering result in? Just maybe like specifics of what you guys are considering and like the different avenues you can take if you were to study this kind of major in college.
I think one thing I've noticed having such a wide range of STEM friends is there's just so many fields of CS, and you can just see like the different things that people are interested. Like I know Lauren is actually a lot more focused on UI UX. She's someone that is really good with the front end stuff. And there's other people that are pure software engineers. They like the back end stuff, more of the nitty gritty. And then there's others that like computer science with econ, which is actually a concentration major at Brown. So that's more focused on using CS for in an economic context. And so there's just so many different fields you can go into. There's data science, security, systems, and so I'd say like depending on what you're particularly interested in the field is kind of where you end up. A lot of people decide that they want to work for a big company like Amazon or Facebook or Google, but there's also those that love working for startups, smaller companies where they feel like they're making a bigger impact. So it's just kind of preference. It's something that you learn as you take classes. You find out what you're particularly interested in, and then you try out different internships. Maybe you like research and you end up doing CS research, which is a huge thing as well. So I think that's just based on personal preference, and it's kind of what you're interested in particularly.
And adding on to what David said, I think the great thing about studying computer science is that a lot of the skills that you learn in computer science are transferable across different industries. So like, let's say you're a software engineer in like fashion, but then you want to like pivot to like, I don't know, agriculture. Like that's totally fine because the skills that ultimately you're going to use as a software engineer are like going to be the same in either industry. So for CS, the great thing is that there's a lot of different paths you can take within different fields of CS. But when you're looking for a job after graduation, there's also a lot of different paths you can take in terms of industry.
Okay, so I'm gonna like kind of combine two questions of like why you chose Brown, because I'm sure you guys applied to many different, and I think a lot of our seniors who are watching this right now want to kind of know why you chose the school that you did or like the process of how you got to learn about Brown.
We'll say it at the same time, open curriculum. It's the only real reason.
Actually,
Also clout.
oh, sorry.
Go.
Oh, I was gonna say I was actually choosing between two tech-focused schools and Brown, and I know Brown is like very liberal arts and not somewhere you would really expect to study CS or STEM or any of that. If you want specifics, I was choosing between Georgia Tech and Carnegie Mellon CS and Brown, and I ended up choosing Brown because of the community. I think the other two communities felt a little bit too competitive for my taste, and I wanted a more collaborative environment, one where people were pushing each other to do the best rather than competing for the best. And I knew that I was going to get a great education no matter where I went. And I thought it was more important how my experience was going to affect me as a person versus my education, because I knew that any one of them would set me up for a great career.
Yeah, I totally agree with Anna. It really helps to visit a college, which I'm not sure that you guys will be able to do, which I'm sorry about, but a lot of schools have online tours where you can, it's kind of like Google Maps where you like walk around the campus virtually, or Brown actually built like a Minecraft world that's like a replica of the campus. So if you guys want to check that out, you can. But like, I think sometimes when you visit a college, it feels like you're kind of just observing them, and you don't really feel like integrated with the campus. But visiting Brown, everybody kind of like sucks you in. They ask you if you need help, if you look kind of lost, and that's totally transferred into the college experience. Everybody's super nice and super helpful, and they just want to like lift each other up.
Sorry to interject, but I have a general question. I hope it's not too off topic, but just a general question about college. Like, I want to ask you guys on your advice of how you stay focused with all of these distractions and things that might come around you. I know some people may not get the chance to go to college in physically for a probably good amount of time, but if we do get to go back, like there might be a bunch of distractions, say people, a lot of like entertainment that's just showing up in your face, your personal interests that might drag you away from staying focused on your studies. How do you stay focused on that? And also, how do you find people, like a good friend group and community that's going to help you like develop ideas and help you like grow, you know?
I can comment on the finding community part. I think one thing that was really important for me freshman year was like most schools will have like an activities fair or club fair where all the student organizations will come out and kind of like a high school club fair sort of thing. And I think in the beginning of your freshman year, it's really it's a good idea to explore a lot of different interests that you might have, even though you might not think that like this could go anywhere. You never know. So I think exploring a bunch of different options in any different club that you're interested in and kind of just sticking with a couple of ones that you want to stay involved in, I think is a really great way to first meet people and kind of develop a community outside of your normal group of friends. And I think a lot of people, especially freshman year, will meet some of their closest friends through organizations and through clubs and events that they're involved in. So for community, I think joining different clubs is a really important part for that. And at Brown specifically, I think most of the people I've met outside of my friend group that I've had like mentorships from upperclassmen or just meeting people in my major or people that have similar interests as me, joining these organizations were like a pretty pivotal part of my freshman year.
Okay, I'm sorry if someone else wants to answer, but we got a lot of questions. So I think something that people want to know is like research. So if you guys did high school research, how did you get that opportunity? And also like what your experience was like researching. Like what you found, what you thought was interesting, if it made you deter from a certain field, et cetera, et cetera. So any of those things in regards to like research and opportunities.
I'm not sure if anybody researched in high school, but I definitely didn't. But don't let that deter you or like scare you away from asking professors if you can research with them, because I don't think that they really expect, 17 or 18-year-olds to have experience with that.
Yeah, I also did not have research experience in high school. But I did do an internship in high school, and one thing that I will say about like getting an opportunity for an internship or research in high school is that like the key is really about who you know, and it's much easier to get a position if you're connected with someone who's already in industry. So like yes, it is worthwhile to send out as many like applications as you can, but if you can leverage like the people who you already know and the connections that you already have, it'll be much easier to get an opportunity.
And I think in the other parts of the STEM world, kind of like the medical side, research is super focused in high school. They're like, oh, like you really want that research position. But speaking on behalf of computer science in general, a lot of people don't really have an opportunity to work with like a college professor on CS research. And it's not like a lot of high school professors are doing CS research at all. So I'd say in terms of whether I know something that someone asked is if research is a big thing that college look at. All of us in this chat did not do research in CS, and we ended up continuing on with CS at Brown, which is kind of a testament to how it's a different story for everyone, but in no way is research expected or is it required to get into a certain school. And a lot of things I'd say is in terms of, I'm sure a ton of people have mentioned this, but in terms of getting into research in college, it's all about kind of just reaching out to random professors, being not afraid to being like, to just giving it a shot. And like they mentioned, they don't expect you to know everything, and they're willing to work with you, and they're willing to kind of guide you through that process. And you just have to be willing to reach out and set up a meeting or shoot them an email. And a lot of professors are very nice about it as well. And there's a ton of different labs at different schools. And so finding one that you're interested in is really important.
This is a question that's going to be like nearing the end of our panel, so they're just going to be a little bit more specific to Nick and Samantha. But Samantha, if you could like kind of discuss what it's like been doing like CS and medicine, and like what that's kind of been like in your college experience, and Nick, your like internship at your fashion tech startup, like what that's like and what you do there. And that would be all. So thank you guys. Yep.
Yeah, so as a pre-med, there's a lot of requirements that you need to get into med school necessarily. So it's not necessarily like your major or concentration or whatever. There's just like a checklist. Oh, you need to take chemistry, you need to take bio, you need to take all these different classes. So on top of what you're concentrating in, you want to try and complete those prerequisites for med school. And I think with CS, none of those really align with each other. So if you're like a bio concentrator, a lot of them overlap. But it's definitely doable, especially with open curriculum, to like, if you want to major in comp bio or if you want to do CS pre-med, like it's definitely, I've definitely know of people who have completed all of the requirements and like turned out fine. And you have a lot of time to complete all of these requirements as well. So you can definitely take like all these other classes on top of that if you need, like, and if you want to.
Right before Nick talks about his fashion thing, I just want to knock down some of these questions like real quick that have been asked. Yes, we have a lot of friends. I'm sure all of us have friends in the PLEMI organization, and it is possible to do CS in PLEMI. PLEMI allows you to kind of do whatever major you want in your undergraduate. In terms of IB and AP courses preparing you for college level STEM work, I'd say it is something that does give you a little bit of foundation, but there's tons of people that didn't take like Calculus BC and they took it for the first time in college and they ended up doing okay. Is chemistry in high school vital to taking engineering in college, and will many universities turn you down? I don't think so necessarily. It also depends on what type of engineering you're in. It depends on what they're looking at. I'd say in terms of taking difficult courses in high school, I think that's definitely important. And if you enjoy chemistry, that's something you can do. But I personally didn't even take AP Chem in high school, and that didn't seem to affect me at all, especially in the CS field. So yeah, sorry, Nick, if you want to go ahead.
Yeah, no, totally. To add on to some of that, at Brown, typically, like if you can think of something, you can probably do it. Like I have no friends that are double majoring in applied maths and archaeology. Really, like the sky's the limit when it comes to open curriculum. There's like no limits whatsoever that I can really think of, other than like you have to use 8 semesters. You can't graduate early under most circumstances. To answer the question about like what I'm doing this summer, so I am working on a fashion tech startup called Style Index. It's a great time. I do full stack web development, so I'm writing front end in mostly React and back end mostly in Rust and Python. And then I also do some DevOps stuff with Docker, GCR, whatever that kind of stuff entails. But I'm also working at a hardware accelerating machine learning company called Stochastic, and they're doing some cool stuff with latent Dirichlet allocation. If anyone's interested in like machine learning, they can totally reach out to me. I don't really want to talk too much about what I've been doing because that's like not super useful for you guys, but rather like how I got these opportunities and what you can do to sort of like gear yourself up for an internship like this. So since I didn't really start CS until like, I don't know, about 18 months ago, like I don't have like the strongest of foundations that like some people have, like having done CS for 5 years or whatever, but I do have like some foundation. And so leveraging like what I did have, trying to do projects in my spare time, trying to have a personal website and a resume of some sort was literally what got my foot in the door for both of these roles. Like I basically had to cold call people to like try and find something to do this summer because COVID kind of messed up everyone's plans. And then having like a good website, having a good, or I say good, but having a website and a resume is really what is very essential for, CS and CS internships especially. If you're not going for like a large tech company, like both of my companies this summer are startups, typically cold calling is okay, cold emailing is okay. And you don't need to go through like rigorous interviewing through like, I don't know, HackerRank or whatever, which pretty much has taken up the majority of my day today and will take up the majority of my time until October. But yeah, if anyone has any questions specifically about like industry and like moving into industry, applying for internships, resume or whatever, I put my email in the chat at some point. It's hello@n-young.me. You can surely shoot me an email there.
Thank you so much for coming, and hopefully you guys all now know a little bit more about CS. I just wanted to say thank you again to all of our panelists. And also, as they've stated before, Nick and Ellen both put their emails in the chat if you want to ask them questions about that specific thing that they were saying that they could help you with. And yes, just thank you once again. And if you guys want to continue to hear from our other college panelists, next we have our nursing panel. Please stay. But thank you guys once again. And yes, now we will be transitioning. So I'm just going to introduce our college panelists. We have Kylie, who is currently attending Case Western Reserve, and we have Adela, Chizu, and Helen, who all attend UCLA and are a part of their undergraduate nursing program. And just a little bit about each of them. Adela specializes in pediatrics and has worked in hospitals and studied cells and proteins in research labs. Chizu was an intern for Kaiser and currently writes public health articles for Peacefully and Breathe. And Helen specializes in neonates and has volunteered at the Ronald Reagan UCLA Medical Center and was also public relations chair of nursing students at UCLA. And last but not least, Kylie is not only a nursing major, but minors in business and is currently an active member in NSNA and Morale Committee in Spartanthon. So we are excited to have all of them as speakers. And now panelists, please take it away. I can just give a little like question or something that you guys can talk about until questions start coming into the chat of what you guys can discuss. So I think first, maybe some like why you got interested in the field that you're currently in, like what led you to pursue nursing instead of, med or any other kind of STEM field?
Hi, I can go first. Hi, my name is Adela. I go to UCLA, like she mentioned before. I was actually a neuroscience major before I switched into the nursing program. And actually, it's kind of interesting because I actually took up nursing after I got into research and learning a little bit more about the humanities side of nursing, I guess. So I can talk a little bit about that if anyone is interested. But I did research on certain cells called the IL-15. So yeah, and I worked with the NICU at St. Joseph's Hospital of Orange, and as well as the mother and baby unit the most. But yeah, if anyone else is like interested in talking about their story, please take it away.
I can go. So yeah, I go to UCLA. I'm a nursing major. I'm actually going to be a second year this year. So the reason why I chose nursing versus like other careers is I did an internship at Kaiser before my senior year of high school. And there I interacted with a lot of nurses, and I always thought I wanted to be a doctor actually. But seeing the patient care that nurses do, it's very, you only have a couple of patients. You're assigned to like 4 or 5 versus a doctor who sees more. So the relationship that you form with like your patient or the person is much deeper than a doctor, which is why I chose nursing. Also, nursing, you can like go into so many different fields. Currently, I'm interested in public health nursing. So there's just a lot of different options for you, which is why I decided to go nursing.
I think I'm Kylie. I go to Case Weston for nursing. I think mine's also similar to Chisu, where I really like the direct patient care side of nursing. I volunteered at Santa Clara Valley Medical Center, and I just really liked, or I just kind of got to see like all the different healthcare professionals when I was volunteering. And I think out of just like when I was like shadowing a nurse when I was volunteering, I feel like I liked how just like all the little things they did, because like they do tend to do a lot of or they just have like the most interactions with the patients for sure. And I think just like I like the relationship that was formed between the patient and the nurses.
Hi, I'm Helen. I'm also a third year nursing student at UCLA. For me, I chose nursing because of an experience I had back in high school where I was interning at a local hospital, and I was given the opportunity to like, we got to go to like different like departments, but I got to go into the NICU, and it was a truly like memorable experience for me. And to me, like just being there, like I had like a sense of desire to want to help the types of patients in there and be a source of support for the families there. So that really like that experience really piqued my interest in nursing. And rather than being a doctor, I feel like nurses, they have a more patient interaction. It's like more like patient-centered care. And I feel like the pathway is also like quicker than a doctor, and there's a lot of like good job benefits that come with it that I really liked.
All right. So next, I think you guys all kind of talked about why you guys did nursing, in the sense that like you had a previous experience. So how exactly did you get that experience, or how were you exposed to that? Like application, how did you get that opportunity? Like in terms of nursing and healthcare, because it is definitely difficult because of like rules and stuff like that. So what you guys did and how you guys reached out.
I can go first. I can talk about my Kaiser internship. So I did it through the program KP Launch, and I know that juniors going into senior year of high school can apply. But there's a lot of different internships. They don't have to be technically like nursing focused, but just getting like involved in like healthcare, whether that's like volunteering at a hospital, shadowing doctors or professionals. I think that really helps. Because at least for me, nursing, UCLA nursing, it's very like once you get in, you're like kind of stuck for 4 years, and then you get your BSN. So they want you to know that you want to do nursing, kind of. So they ask for like a separate supplement for nursing. So I think it's good to get experience and know that you want to do nursing before at least you apply to LA nursing. At least for me.
Okay, hi. So there were 2 things that I was involved in, and the first one was called COPE Health Scholars. I think for anyone who is interested in going into any kind of medical field should try the COPE Health Scholars. There's like a lot of locations throughout California, but it's basically you go through an interview process, and then if you get selected to be a health scholar, you go through intensive training on the US healthcare system and the clinical nursing practice and practical hands-on patient care. And you get to actually do assist patients with care tasks such as bathing, feeding, changing, ambulating, and checking vitals under a supervision of a licensed staff member. So you know, it's kind of like volunteer hours, but I got to work in so many different departments, and that's kind of how I settled on, you know, liking pediatrics and things like that, was because I was able to go through different pods and different departments under a certain, like for 3 months. Every 3 months you get a department. Yeah, it's COPE Health Scholars.
Yes, so anybody who like mentions like a program or something that you guys have done, if you guys could like type into the chat, because I think people are like interested in what you guys did and to see like if they could do something similar. So yes.
So the first one, yeah, is called COPE Health Scholars. And after you're done with the program, you actually do get a pre-licensure like a degree, or not a degree, like a certificate from UCLA, because it is connected to UCLA. So I would highly recommend it to high school students or, you know, college. Yeah, and then the program is not suspended due to COVID right now. I think I just saw a question about that. It's still going on, but you will have a little bit of a restriction, and there are still times where you still need to go through the interview process, and we only take applications at a certain time. So yeah, and there's also leadership like opportunities that are with that. I got to be an administrative coordinator, so I got to kind of handle the files for cohorts who were in certain departments, like their CPR certificate and their just vaccinations, keeping that up to date. So if you wanted some leadership opportunities, there's that there. And then the second one that I was involved in was called SURF, or Summer Undergraduate Research Program. And this is offered by Chapman University. And I'm actually unsure if they offer this to high school students in particular, but it's also like a very rigorous, very selective program. Only around 50 people, 50 students get to, you know, directly work with the Chapman professors, and you get to research, you know, things that other people usually don't get to research. So they get a lot of funding through that. And it's a summer program that you basically work and research for 30 hours a week. Yeah.
As for me, like in high school, I volunteered at 2 different medical facilities, and then I also had an internship at a local hospital. So I volunteer at a pediatrics office and a senior home that focuses on Alzheimer's. And for those 2 opportunities, they're both like local and small like places. So like I looked up like a bunch of different places, like 20 to 30 places around my area that focus on like medical facilities and clinics that I'm interested in. And then I would just like contact them and ask them like, oh, like, are you looking for volunteers and stuff? And it was like, I feel like that's like a really way to get involved in your local community. And since they were both like very small, like clinics and offices, I built like a really intimate connection with those people. And they helped me write like recommendation letters when like applying for colleges. So that was like, those 2, like I had like a really good like experience there. And it's like, I also like learned a lot because it was like very local, so not many people applied for like those places. So I would like, I highly encourage you to like reach out to like medical facilities in your local community and see if they are accepting new volunteers. And then I also had an internship at the local hospital, and that was through a program called ROP. And I can type that in later, but the ROP has like a lot of different fields. Where you can learn about like any like career field you're interested in, and they had one for nursing at the time. So you just apply, and usually you get in. Like it just based on like first come first serve. But that experience was really good since I got a lot of like hands-on experience there, and like it was more than like like more hands-on experience than like normal volunteers at hospital, since like we got to take vitals, we shadow like a nurse, and if you ask the nurse, they let you do like a lot of different things as long as you ask the nurse, and it's just like truly like a really great experience. So if like ROP isn't like canceled because of COVID, I would like highly encourage like applying for that, since I feel like that was where I got the most hands-on experience in the hospital.
I think for me, like others, I also volunteer at Santa Clara Valley Medical Center. And I think on top of that, I think I took a course at Dianza, which is like a community college near our area. It was called Career Opportunities in Nursing. And then it just basically like, it doesn't really have any like requirements to take that course, although it's like a college course. And it kind of like goes over like just basic information in nursing, and like it focuses on like education and just practice portion of nursing, I guess. So I think that was also one of my ways to show that I was really interested in nursing for college application.
As you guys are talking about like high school, like what you guys did like experience-wise in high school, do you guys have any tips specifically regarding like college admission? So like essays in terms of like nursing and like doing nursing programs, because I'm sure that's very different than your typical like Common App. So how you wrote that and like what influenced you in writing it?
I can go first since we're like going like a cycle. So there's like a nursing supplement, at least for LA, and a lot of different schools when you're applying to nursing, there's going to be a supplement. So usually ask why you chose nursing. Or like why did you want to go into nursing? Like what drew you to the program? Something I actually forgot to mention before was I did a CNA program, so Certified Nurse Assistant program. So that's 150 hours of clinical and then 100 hours of theory. There's a lot of different programs. You can look it up online, super local. And once you get that certificate, you can actually work at a hospice. So that's another option if you're looking for getting patient contact. In terms of approaching my Common App to make it more focused on nursing, I think I wrote a lot about my nursing like experience or like patient experience, or like geared towards science versus maybe like I don't know, like art stuff. I definitely geared myself towards science because I knew those were courses I was gonna like take in the future in college.
Okay, so I think for me, I'm so sorry. What was like the question again? I was like answering this.
No, it's okay. It was basically about like how you wrote your essays, or like what influenced you when you were writing your essays. Yeah.
I think for UC specifically, because UC is such like a research, heavily dependent on research, I would say if you can get your hands on research, that would be a really good way to kind of stand out specifically for UCs. That's kind of like the route that I took. And I think Jisoo made really good points about, being specific to, gearing towards like science classes, but I also wanted to stand out in other ways. So not only did I focus on, those STEM courses, but I also did a lot of other things on the side that showed more, like I said, the humanity side of me. Like I just wanted to show more that, I'm not just here for like just to be like a STEM major or just to be a nursing major, but more that I actually do care about the people. So I chose a lot of volunteering that didn't really have to do with I guess science related things. So for example, in high school, I was the president of Make-A-Wish, which is more, it doesn't have anything to do with medical, conditions or anything like that. But I chose to do that. I also like volunteered like my musical talents, I guess, to local hospitals. And so I was a little bit more creative, I guess, in showing like that other side of me. I think in order to stand out, you need to do other extracurricular activities that aren't just geared towards nursing. I think that's like my best advice. Yeah.
As for me, like like adding on to both like UCLA and Adela, like UCLA has a nursing supplement, and it shows that like UCLA nursing doesn't just focus on academics. Like academics are important, but I feel like there's a greater focus on what you do outside of school, and to show like your interest in the field of nursing, and to like volunteer at like different places, since like your experiences volunteering helps you write your supplement essay. And it's like really important to like show that like you've when you volunteer you've had like some sort of experience that's memorable to you, and something that I guess inspire you to go to choose like nursing and that future like career.
For Case Western, we didn't have a separate nursing application. I don't know if they do now. I heard that they added it, but when I applied, at least I didn't have it. But my Common App was actually about kind of like geared towards nursing and healthcare area. So I think even if you apply to schools with no nursing application, like a separate nursing application, I feel like you can also just incorporate kind of like your experience at the hospital, or just like you can just kind of like show your passion for nursing even in your Common App.
Okay, thank you. We actually have a question from the chat related to if you guys have ever done interviews related to nursing, and in that setting, like what kind of questions were asked, and like how did you answer them, if you guys have a general idea.
Do they mean like interviews related to the nursing work or nursing schools in general? Because I have gotten interviews related to nursing. Specifically, they're called MMIs, or multiple mini interviews, where it's kind of set up into separate and this is for getting into nursing school, by the way. And this was for Cal State Long Beach. You do MMIs, as in you have like separate pods that you have to go into, and there's several interviewers, and they ask a single question, and you go around doing either certain tasks that they ask you to do, or write an essay, or like in 10 minutes, or just kind of like an interview talking kind of style. It's all incorporated in that one interview. So yeah, I would say the type of questions, they range from very clinical to very specific questions, such as like, what would you do in this situation if you were ambulating a patient and you patient falls, like what are you supposed to do? So they ask a lot of highly specific questions, but also they ask generally, you know, what is your passion? Like, why do you want to do this? What departments do you want to go into? And you know, what are your intentions for, you know, wanting to be in this program, that sort of thing. And
do you have like tips on those MMIs? Like now that you've kind of specified that that's the kind of interview process that you went through.
Honestly, practice makes perfect, as in when I first started MMIs, actually we do MMIs for the Cope Health Scholars program too, and we actually grade you on like how you do your leadership skills and things like that. So yeah, I would say just kind of even just trying out for these volunteer positions who do offer the interviews. I would say that's really good hands-on practice, but also you can kind of like practice at home. If you like just kind of like look up MMI questions online, they do come up, but they are more like situational questions. So I would say that you want to just kind of prioritize patient care and patient autonomy as much as possible as you're giving your answers. So, yeah.
Okay, so we can move on to a different question. Thank you for answering that in terms of interviews. I think this kind of goes into like a double question of like, how has this pandemic kind of affected you studying your major? And in terms of that, how do you recommend ways to get involved in doing extracurriculars? Do you know of any that are virtual that existed even before this pandemic? And so like, yeah, it's kind of like two-sided, like how has this pandemic affected your ability to study your major? And if you know of any opportunities that the people in this Zoom webinar or that's watching the live on YouTube can like get involved with medicine virtually, like a good, yeah.
I can go first. So in terms of opportunities, I think you don't have to look for like healthcare. There's always like other opportunities, like what I think Adela mentioned, like just because you're applying for nursing doesn't mean they only want to see nursing on there. So there's a lot of like opportunities I know online for like um nonprofit organizations. I would look into that. That's what I've been doing. I'm doing an internship, like an online one where I'm writing articles for a geriatric website, so end of life care. And then I recently started another internship about public health measures. So even though it's not like super like directly related to nursing, if it's like volunteering, helping patients, helping people, and just cultivating who you are as a person, I think those are opportunities that are great for you. And then I forgot the other question.
It was just about how has this pandemic affected your ability to study your major?
So at least for LA nursing, we start clinicals third year, I think. So I'm gonna be a second year. So in terms of classes, nothing has changed. I think the only thing that's changed is like volunteering. It's transitioned from being like in person to online. Yeah.
Maybe Kylie, you want to touch on how it's affected you, because I know Case Western starts clinicals earlier than other nursing schools. And just to clarify, clinical is like you actually like kind of like in-person hospital stuff. And so
Yeah.
yeah.
So for Case Western, we do start clinicals the third week of freshman year. So it is a lot earlier than other schools, I believe. For Case specifically, we are still continuing clinicals as of right now. So I'm back at my college. So we are back, like all the nursing students were required to come back for the semester to do labs and clinicals in person. So I'm guessing like in that aspect, nothing has really changed. But I heard that from my clinical instructor that we may need to stay 6 feet away from the patients and possibly the nurses. So I guess like that might be a different experience, but and also in terms of like, I guess like volunteer activities, I feel like I know that like at least for like the local hospitals near my area in Cleveland, they are offering online volunteering activities where you can just write cards to little kids if you like to get yourself self-involved in like pediatrics unit, or just I feel like there are a lot of activities you can do online. Just like kind gestures will be really nice to the patients.
Okay, well, it's kind of nearing the end. I think one question that we just want to ask all of our college panels is why you chose the college you did. So as our previous Brown panel was talking about like open curriculum. So for you guys, UCLA or Case, why you chose the college you did, especially considering that nursing, I don't think people keep in mind, is very different than studying other majors. So nursing specifically at your school and why you chose it.
I can go first. So for UCLA, I really like, so I chose UCLA in general just because it's a really like big school. It's located in LA, so there's like a lot of opportunities in LA. There's a lot to do in LA. So I feel like it's just like a really good place for me. I felt like for me to grow as a person. And then in general, like not a lot of colleges offer nursing majors, so there's already a limited options. But I chose UCLA nursing because they have a lot of good research opportunities and like very like astounding like professors. So I feel like going there in terms of my professional route, I would be able to have a lot of opportunities that can enrich my learning and enrich like the volunteer opportunities and hands-on opportunities I would get as a nursing student.
I can
I
go
can
next.
go. Wait,
You wanna
Kylie
go?
go first. Kylie
Okay.
go first.
So I chose case nursing because I think like like this one aspect that attracted me to nursing was just direct patient care. So when I heard about cases, how like they start clinicals earlier than other schools, I feel like I wanted to get the most clinical hours as possible when I'm in school. So that was one reason. And I think I also just consider financial a lot because case tends to well, Case is like a private school, so it is supposed to be pricier on the side, like on the pricier side. But Case is known to give out a lot of scholarships, so it's just more affordable for me. And also Cleveland just had like a lot of access to a lot of great hospitals like Cleveland Clinic and just University Hospital. So I wanted to get opportunities from them.
Yeah, so for me, I think Helen mentioned like UCLA, the research opportunities really drew me. Just the fact that you're going to a school in LA, I thought that was really fun. The location is really great, but also from the schools in California, the UCs at least, only UCLA and Irvine have like a nursing program. So I applied for both. I don't know about Irvine's program, but LA's program is really small. So the number of people who are admitted each year is, I think, 40. So in my like grade, there's only 40 other nursing students. And I really like that because UCLA is such a big school, but like nursing is special because you have a small cohort that you're like studying with, taking the same classes with. So you get like you form individual relationships with like all the people there, which is something that's kind of not typical for like a UC school, which is why I chose LA.
I chose UCLA because I did a lot of research on just like universities and nursing schools in general. And just adding or clarifying what Chizu said, it's 40 freshmen and 10 transfers. So I was a transfer and I knew that like, yeah, it was like incredibly hard. So I wanted to like research why. And it is because we have a lot of professors who are very well known and they're really, really helpful. I would say, yeah, some of these professors are really amazing. A lot of good research opportunities. A lot of the professors are currently doing research as well. And yeah, like I just thought, yeah, how small it is. It was kind of like, you know, it's a big campus, but you have like a small cohort that you get to like know really well. And I really just like kind of like that aspect. So yeah.
Well, thank you so much for speaking. We really appreciate it. And hopefully everyone that was here got to learn a little bit more about nursing and just what it's like to study it in college. We're actually going to be transitioning to our next panel, but just want to thank you all once again for being here and speaking. I'm going to actually transition to introducing our last panel before closing remarks. And it is going to be Jessica, Lee, and Cynthia. And so I'll just do a little quick intro of Jessica and Cynthia. Jessica is a co-chair for the Collegiate Team HBV chapters, which works with Join Jade and Stanford's Asian Liver Center to raise awareness on the dangers and effects of hepatitis B. And Cynthia is also involved in Team HBV as the public relations advisor. And so they'll be discussing not only their involvement in Team HBV, but also their personal endeavors and careers. Yep, please take it away.
Hi, can you guys hear me? Hi, so I guess I'll just do like a really quick introduction about myself. So hi, my name is Jessica. I'm one of the co-chairs this year for Team HBV. I went to UC Irvine for undergrad, and currently I'm a master's student at Keck Grad Institute, which is one of the Pomona colleges. Yeah, I don't know what else there is. Yeah.
It's okay. You can do a quick intro, and then I'll kind of ask like sections of questions, and you can answer those. But yeah, Cynthia can do a quick intro.
Yeah, so hi, I'm Cynthia. I'm on the A board for Team HB as the PR. And I go to UCLA and I'm under the MCDB, which is Molecular Cell Development Bio major, and I'm happy to be here.
Well, thank you so much for both being here. So first, in the field of STEM that you're in, why and how did you become interested in that? Because I know you guys don't study the same things. Science is very broad, so why you particularly got interested in the thing that you currently study right now?
So for me, not so like I guess I'll go like way back, because for me, like my journey through STEM kind of goes like from, it starts from like an early age for me. So for me, I used science as a way to kind of bridge communication barriers. So growing up with you know, bilingual, I'm Korean American. I grew up with my grandma who couldn't speak English very well, and then I couldn't speak Korean very well. And so, and she also had dementia and Alzheimer's. And I kind of found science as a way to kind of explain, I guess, more complex things that I, as you know, like a child, couldn't really comprehend at the time. So from there, I really kind of saw science as a way to, a deeper way to explain things and really kind of bridge gaps between different, you know, like I guess like discrepancies, if that makes sense. So yeah, that's kind of how I fell in love with science. And then from there, I really saw medicine as, you know, an opportunity to even further bridge the gap, because that's really kind of what it's all about, like, is relationships. So I really fell in love with that. And yeah, so right now I'm actually studying for the MCAT. So if you guys have any questions about the MCAT, feel free to ask away. So yeah, right now I'm in grad school preparing to go to medical school. And yeah, it's kind of a background on how I got into science and STEM.
For me personally, it would also stem back to my childhood. And I was in a position where I felt at a loss because a lot of my family members were experiencing medical conditions, and I felt the doctors didn't give much empathy towards me and my family, and it was a lot of struggle. And I saw there was this gap in the medical field where people didn't acknowledge the family members as people, but rather as cases. So I wanted to bridge that gap by going into the medical field. And I also saw that when I was researching how to become a physician and all those things, I became really interested in pathology and things like that. So I, through that research, I also became impassioned by the subject, and also I want to bridge that gap. So that's how I became interested in the medical field.
Thank you. I think another thing is that might interest the viewers is important activities you did. So you guys can talk about how you guys got involved in Team HBV, and not only that, but also other activities, communities you've joined, clubs, like etc., of what you did in order to study at the college that you do, or you know, kind of fuel your interest in your field.
So growing up for me, I was very athletic. So I was actually a competitive figure skater for, I think, a little over like 12 years. I did synchronized figure skating, and I did ice dancing. And actually my senior year of high school, I competed internationally and represented America. That was really special. So that's kind of my background in high school. And then I really wanted to stay engaged with the community, like the figure skating community. So I made it a priority when I was in college, and even now in grad school, to volunteer with an organization. It used to be Best Buddies. I taught figure skating to you know, individuals with disabilities, and that was a really special way to, you know, connect with the people in my community and just the figure skating community in general. And then at UC Irvine, I majored in bio, just general biology. One of the biggest, I guess, things that I was involved in at UC Irvine was I did research at the stem cell lab. So that kind of bridged the gap between my desire to understand more and actually, you know, seeing it in a research setting. That was really special. I unfortunately did not get published, but right now at Keck Grad Institute, I'm actually one of the founding members of our free clinic, and that's really exciting. I don't really know where it's going to go with, you know, COVID and everything. We'll see, but we're actually working with the dean of the new Keck Medical School, not the one at USC, but Keck Grad Institute School of Medicine. We're working with them to get it integrated into the curriculum, and so that's really exciting and special. And yeah, I think those are my main involvements.
So my main involvements in high school was I was in a bunch of variety of sports. I was in diving, track, and I kept with those. But eventually I dropped it because I had too many things on my plate, and I didn't want to not be able to commit myself fully to the other activities I was in. I was also in a I can't say it, sorry, rehabilitation hospital near my where I live, and I worked as a nursing volunteer there. Even though I didn't plan to pursue nursing, I just knew that through that program I'd be able to also explore if I wanted to become in nursing, but eventually I didn't choose that. But it was a really great experience to interact with patients through that. And I also formed a cooking club because I really love cooking. And I think it's really important to be involved in activities you actually like rather than doing what you hear everyone else doing. And I think it's really important to enjoy yourself and make strides in your progress rather than just being stagnant and joining things you don't like. And then when I joined UCLA, I joined a program called Care Extenders Internship. And there we have the opportunity to volunteer at Ronald Reagan Hospital. And I got to volunteer in a variety of different wards, such as the ER ward and the pediatrics. And I work there as a department coordinator. So I manage about 20 to 30 volunteers to work inside the pediatric department, and I train them to handle our pediatric patients. And I'm also involved in, what else? Oh, in Team HPV under the UCLA chapter and also as a board. And it's been really fun, and I really enjoy the work we've been doing there.
So I think another thing is, as you guys talk about your high school experience, do you guys have any tips on like college admission regarding trying to go into this like field of STEM? And also, Ivan has typed into the chat, are you still doing Disney on Ice? So if you could answer that question along with your question about college admission.
I was actually not on Disney on Ice. I was actually, I was part of a team, a synchronized skating team in Anaheim. So I'm from San Diego, and this senior of my high school year, I drove up to Anaheim like 5 times a week to practice with this team, and then I got to compete with them. So I'm not on Disney on Ice, but I know a lot of people that are right now. So that's really cool. And yeah, I guess like tips for high schoolers, was that the question? Like tips when you're in high school?
Yeah, like college admission, and also like if you know anything about applying to direct medical programs.
Okay, I don't know too much about like the 7-year MD ones where you apply as an undergrad and you get into medical school. Was that the question? Sorry.
I think she'll continue to write in the chat about the specifics of the question, but while she's doing that, yeah, just talking about college admission.
Yeah, so in high school, I think, you know, like Cynthia said, it's really easy to just kind of do things. I'm so sorry, this is going to be really cliche information, but after going through, you know, just not even college, just like school applications for undergrad and grad school and going to be in medical school, I just want to tell you guys right now that it's so important to show your character and show your story. And I'm like truly speaking this from the heart because I'm like helping all my friends with their medical school applications right now. And the biggest piece of advice I can give in terms of applications is have your personally really come out. Like that like personal statement, and I guess like whatever application you're going to submit is like truly your story. So like whatever you do, show that you are passionate about it and like make it connect to something else. And like from there, like watch your story kind of blossom, I guess, if that makes sense. Like, I don't know how to explain this. It's like have everything connect with each other and have a reason for doing it. Because if you have a reason for doing it, colleges and schools will see your passion, and you know, that'll speak a lot for why you want to go to that program. And so I think that's like my biggest piece of advice. I'm so sorry, it's really cliche, but if I could go back and do it all over again, I would be really clear as to showing my passion for something instead of, you know, I'm really accomplished in this and these are my accomplishments, these are my awards, these are my, you know, accolades. That's not really what they want. They want to know how you think as an applicant. What would you do differently? Like pour your emotion into it, I guess. So that's like my biggest piece of advice.
Oh, and that, oh, sorry, that was her question. If you guys, either of you guys know anything about the, like what PLEMI is or like the Northwestern stuff. So like the 7, 8, like dual like med programs, if you guys know about anything in that sense.
So I'm sorry, but I don't personally know anything about the medical. Sorry, my computer muted me. But I don't know personally about those, but I know there's a lot of resources online that you can search but I'm sorry, I don't know anything about that. And then for psychology, I know a lot of people who are pre-med and a psych major, so it's definitely an option. And there's also majors called psych bio, and that's also a great option. So it has that combination of both psychology and biology. And I know a lot of people who really enjoy that. But was the question what I do in high school? Sorry. I got off track.
No, totally okay. Just when you were doing like college admissions, like essays or any of that thing of that sort, like college admissions, like do you have any tips on like that entire process, or you could specifically talk about essays and like what you wrote?
Yeah, I definitely agree with Jessica, putting your personality in there, because the results I saw for a lot of my friends, even though they had superb grades and their SATs was like the highest they possibly could be, they didn't get accepted to the schools they wanted because when I read their essays, it lacked a lot of that emotional depth. And it was more just, I accomplished this, and it wasn't really beneficial for them in the long run, but they still went to colleges they enjoyed. But I think for sure, put your personality in there. And I think putting quality over quantity is very important in terms of your social or your extracurricular, because a lot of people bounced around different extracurriculars, but they never settled on one. So they never got to have a story and a connection to their organization. But I was able to volunteer in this program for about 2-3 years. So I had a lot of stories from it, and I was able to speak about my experience. And you could see that there was a lot of emotional connection. And not only that, but also I grew from that experience rather than I grabbed what the surface level that I could from that experience. So I think that's really important. Quality over
And
quantity. Yeah.
sorry, and this is just something that I kind of take like gospel with me. Like I truly live by this. Like no matter what I'm applying for, like scholarships, grants, like whatever, like if you're writing a personal statement and it's supposed to be personal to you, if you can take a paragraph from your personal statement and substitute that in someone else's personal statement, that paragraph should not be in your personal statement. So that's like been a really helpful kind of step, like kind of like a study, like a tool for me to kind of always mentally engage myself whenever I'm writing anything that's like supposed to be personal. Just always having like a story, make sure it's very personal to you. So my biggest piece of advice in terms of, sorry, I don't know if this is a little off track, but when you're writing something, like a story that you experience, like yes, everyone did research, yes, everyone might have done this volunteering opportunity, but what will separate you from someone else who did this exact same thing is how you felt during it, how like what your experiences were in the moment. So like if you came across a unique, person that you're working with during your volunteering hours, like what were you thinking, how did you go about that, how, like what did you do after that? So like that is what is personal to you, not the volunteering in and of itself. So that's like something really to keep in mind. Like if you can replace that with anyone else's name, that should not be there.
Wow, thank you. I think, I guess personally for me, that's very good, insightful advice. Yeah, I think because a lot of our people in the Zoom call and in our live YouTube, all are kind of in that concern space of like what I should write on my college app. And I think something else is why you chose the college you did, because I know some colleges like want certain things, or they're definitely like different kind of priorities. So for you guys specifically, you can talk about, Jessica, both your undergrad and graduate experience of how you kind of catered your application to your school and ultimately led you to choose that school.
Yeah, so for UC Irvine, I don't know about any other UC that does this personally, but the general bio major is tailored to fulfill every single AAMC medical school requirement. So if you're a bio major, the requirements for graduating UC Irvine as a bio major align perfectly with what AAMC requires of an applicant. So I know that at other schools, like if for some reason you're a bio major, they like physics may not be required, sociology may not be required. It's very different for each school. So especially if you go to like a private school, you will have to look into that more deeply. But at UC Irvine, if you're a bio major, you don't really have to worry about whether or not your other classes will fulfill medical school requirements, because it already is. That's a big reason why I chose UC Irvine. And also just that in and of itself just kind of speaks to how much UC Irvine prioritizes medical pre-meds, I guess. And that just kind of speaks to, you know, the research opportunities and, you know, the extracurriculars, volunteering and things like that. So that's what really attracted me. And, you know, just from there, just, you know, that there will be an academic peer support group. So I think that was also another thing that, you know, really kind of pushed me towards UC Irvine. And I think for Keck grad, where I'm at now, you know, graduating from UC Irvine, I really wanted to enhance what I had, not just a biology degree. So the thing about my grad school is that we really emphasize the integration of science and technology, and science and the pharmaceutical side of things and the business side of things. And I think that's kind of something that even like, especially now more than ever during this pandemic, like tech is becoming more and more a part of our lives. And I think that, you know, we as pre-meds tend to kind of, oh, that's not science, I don't need to know about that. Oh, that's not, you know, like bio, I don't really need to know about that. Like, I feel like there's a tendency for us pre-meds to kind of stagnate into like a box of, you know, like medicine. And that's really not the case. And that's not, I don't think that that's where the world is really headed towards. And so I think that now more than ever, the integration of science, tech, business is really, really important. So that's why I chose the school where I'm at now.
So I chose UCLA when I got accepted into I applied for 4 UCs. I think I got accepted into the 3. And so I chose UCLA because when I visited the campus, I recognized that this was something more alike to what I would want. It was a lot of activities going on. You could see there's a lot of student engagement. And I really wanted that in a college rather than being purely academic based, because you eventually get really burnt out from that and you feel so tired from just studying and sitting in your dorm. So I really needed to have that sort of break, and UCLA offered a lot of those activities that I could be a part of. And I knew that there's a lot of medical opportunities that I could be a part of, such as the Ronald Reagan is so close by, and I was able to volunteer there and get a lot of great opportunities. So a lot of it was also location based because I wanted to be near my home. And
this is actually a question specifically to Cynthia, if you know. Does UCLA allow psychology majors to take biochem classes? Do you know?
yeah, so you should be able to. And you also have to keep in mind, if you're going the pre-med track, you will have to take those classes eventually. You need like a year of bio and all those things. You can search up the prereqs online, but you should be able to. But the upper divs, you might have a little struggle because they tend to reserve that for those majors. But if you're psycho-bio major, you should probably have an easier time in integrating both the medical and the psych. So
I think one of the last few questions is, what is the hardest part of studying your major? Or easiest, you could take either way. You know, obviously you do enjoy it, but like the hardest and easiest parts of studying your major specifically.
Gosh, I think like, you know, the hardest part is just kind of what we all expect. You know, obviously, you know, the content, the material is difficult, but I think what's even harder is staying motivated. I feel like, you know, no matter how strong your motivations are, you know, going back to my childhood is the reason why I want to go into medicine. Like, no matter how strong that urge is, everyone has, you know, rough days or weeks or months. But I mean, yeah, just keeping yourself motivated, having a really solid support group is like my biggest piece of advice. The hardest part for me was definitely keeping myself motivated, but you know, my support group was really there for me, and those are the people that you lean on. And I feel like pre-meds have a tendency to kind of cage themselves in with other pre-meds, but having friends outside of your major is a really, I think also it could be like a really big help, just like mentally. Sorry, that was a really big tangent, but the hardest part, yeah, just staying motivated. Easiest part, I think, is just always being intrigued by what you're learning. I think no matter what like class I will say, if you go to UC Irvine, it's the first 2 years are very dense. Like they're very molecular based. For me, my upper divs were the best part of undergrad. I thoroughly enjoyed all of the upper divs I took. I took a lot of neuro classes. I took a lot of immunology classes, classes where I really got to see just how great what I was learning is. And I think that kind of motivated me even more to, keep going and stay, I guess, like on track and stay engaged in what I was learning.
I would also agree the hardest part is staying motivated, because especially getting harder being at home and not having your support system in person. But talking online with a lot of people definitely helps. But the easiest part is, like Jessica said, being engaged with the material. It's so amazing learning the material, and you get so enthralled with like, oh, so that's why this is what happens in my body because of this, what I learned. It's honestly so rewarding to learn all these new materials, and I really enjoy doing that. So easiest thing, just learning the material. But at UCLA, I would say since I'm kind of like a bio major, there's a lot of review. So you always have to constantly remember your past material. So you can never just like, hey, I finished this class, throw it in my head. You always have to try to remember it and always go back on that material. So just keeping on top of your work is also very hard.
If I may add, if you guys major in bio and you're going to go the medical pre-med route, please keep your notes for the MCAT. They're so helpful. Like no Kaplan Princeton review book for the MCAT will prepare you as well as your undergrad classes did. Please keep your notes. Thank you. Just keep them.
I think the last question before we go on to the closing ceremony, just a general question about college admission again, is how much essay writing did you do in college? And also for UCI, is the MCB an impact major? Is it possible to apply if there was a bump in the AP Bio test? If you know anything about that.
MCB, molecular cell biology. Is that a major? I don't know. Was that for UCLA?
Yes, I think he meant molecular cellular biology.
Oh, yeah. I see. Yeah. So the way biology works, there's general biology, which you can still major in. And then within biology, there's like sub majors within biology that you eventually concentrate in, I think your second or third year, one of those two. Is it still possible to apply if there's a bump? I believe so, yes. But so you don't apply for those specialized majors when you apply to UC Irvine. You apply to UC Irvine, I believe, as just a general biology major, unless they changed it in the past couple of years. And so if you had bumps in your AP Bio test, I believe it's okay to still apply. You'll just not get any credit for those college courses. I could be wrong. They might have updated it. I'm not really sure. It's been a while. Yeah. How much essay writing did I do in college? So for me, going to UCI, we just had a 1 year writing requirement. And after that, a lot of my writing was lab report writing, which I will say did not really help in terms of grad school, med school application writing, because you have to go from writing college apps to writing a bunch of lab reports to writing beautiful, flowy, elegant, med school apps again. So that transition can kind of be hard, but I recommend reading as much as you possibly can if you have time, even in undergrad. So yeah, I guess that's it in terms of essay writing.
For my essay writing, it's quite intensive. So each quarter I would have to do probably 2 to 3 papers, but I would take, I'm going to be taking about 3 classes in my overall undergrad career. So it's a decent amount, but there's a lot of resources, like an undergraduate writing center, and they help a ton. So definitely utilize your resources when you go to college, because that's my number one tip. If you just try to put all the workload on yourself, you're not going to get anywhere. You always need help. Always reach out. No matter how good you think you're succeeding in class, you should always try to get help.
Okay, well, thank you. Oh, sorry, Jessica. You
Sorry,
want to
no,
say something?
I just wanted to add to what Cynthia had said, because I just think it's so important. I'm sorry if we're running out of time, but definitely, like, as pre-meds, it's so possible for, and just like STEM majors, I feel like it's so easy and it's so ingrained in the STEM majors for us to just kind of like always just focus in on ourselves and not really ask for help. And asking for help is like, oh, you're failing, oh, like, you know, shame on you. But I feel like it's so old. Come on, like, it's like, you know, people are there to support you. You really have to just get help when you need it. And every school, no matter what you see, not even UC, like any school you go to will have help centers that are there for you. The school does not want you to fail. Like, they want you to succeed. They want you to graduate. They want you to, you know, do great things. So really use those resources. And I want to emphasize what Cynthia had said. So
Yeah, and also, sorry, really quick, do not underestimate college. I came in with a huge thing saying, I got this, like I succeeded in high school, I'm here now. No, you need to prepare yourself for college. Like, sorry if that sounds terrifying, but I'm giving you the true reality. You need to know that you're going to be surrounded by people with the same like caliber as you, and you have to be prepared and be willing to dedicate your time to studying and understanding material.
I'm so sorry. Can I add one more thing?
Go ahead, go ahead.
So this is specific to, I guess, what we're going through now in terms of COVID-19. And just, I know that a lot of colleges, a lot of medical schools are asking this. What have you been doing during your time off during COVID-19? How has it impacted you? What did you do differently? How has this impacted your application, your academics, your studies? I, you know, really feel like it's easy to just, like, it's been hard for everyone, you know, everyone's been working from home. Everyone is, you know, studying from home. Everyone's doing school from home. Everyone has faced, you know, I guess like blocks in the road. Life is different for everybody. So if you go into that prompt, which I can guarantee colleges will ask you, how has COVID affected you? Oh, you know, like my school went online. Oh my gosh, like, you know, like it's so hard to focus at home. Like, it's true. Yes, like, it's perfectly valid, but everyone is going through that. What have you done differently? How have you used this as an opportunity? You know, you guys are in this conference right now, this virtual conference right now. Like, this is maybe this is the future of telemedicine. Maybe this is how, you know, I think like psychiatric visits will go. Maybe this is how, you know, primary care visits will go. Maybe this is the future. So I think, you know, looking at college admissions as you are not asking them to help you, you are their asset. You can help the colleges, you can be an asset to the colleges. So I think like approach that COVID question and that COVID response in that way. Be very proactive in your response, and yeah, best of luck.
Thank you so much for coming and speaking about your experience. If you guys want to get involved in the program that both Jessica and Cynthia are, Team HBV, you guys can search that up online. But once again, just wanted to say a huge thank you for coming and speaking. Hopefully you guys got a little bit more insight on what it's like to kind of do bio in college, but we're actually going to transition to our closing ceremony as this is the end of our convention. So Diana, why don't you go ahead?
Awesome. Thank you so much again, Jessica and Cynthia, and well, all of our speakers, many of which aren't here right now. But before, so just to kind of give you guys a sense of what's going to happen right now with the closing ceremony, I'm just going to say a few things, and then we'll announce our competition winners. That'll be pretty quick, and then the prizes aren't picked yet for each person, but we know which prizes we're giving, so we can also mention those. And then after that, we are going to meditate, and then we're just going to hang out and talk about whatever you guys want to talk about, your favorite parts of the convention, or what fields of STEM you're interested in. And so to just get started, before I recognize all the competition winners, I wanted to thank everyone who attended, listened, or spoke at STEM World, especially the people who stayed for almost 22 hours. Very impressive. So that's specifically several of the STEMI executives. So Catherine Liu, Sophie Takmopoulos, Aryan Mathur, and Arun Yadavali, and Faith Han. You guys have really powered through. Like, we've been on the Zoom call since 7:30 a.m. So very impressive. Give me a second.
Oh yeah, and then for Jessica and Cynthia, some people are asking for your contact information, like an email. So if you can just put that in.
That's totally only if you are comfortable, and also you are free to leave and turn off your video. Sorry, I couldn't privately chat you because I couldn't find you, but yes.
Oh yeah, you can search them in the private chat, but it's fine. Okay, yeah, thank you guys, Jessica and Cynthia again. Yeah, so, as I said, we woke up at 7, we called at 7:30, and now we're here at 6 p.m. and we did that both days, which is really impressive. Yesterday, we actually ended at 8 p.m. So that was also really cool. And in addition to the STEMI executives, I've also seen several individuals in the Zoom session for just countless hours, and many of which were like super active and asking questions and engaging with the speakers. So, a special thank you to everyone who's not even associated with STEMI, and then chose to participate and just stay with us for so long. Yeah, and I also just like to briefly mention what we really hoped that you would gain in attending STEM World to those who came as attendees. And I'm personally very confident that I gained what I was hoping in many ways. So I think this convention was geared specifically towards high schoolers, but I know a lot of the people who joined us were not high schoolers and were in a very different age range. But even so, I think that oftentimes for specifically high schoolers, and specifically me, when I attend a class, I gain a lot more technical skills, like hard skills, than I do inspiration and motivation to pursue a certain subject. Like with math classes, doing Common Core in middle school, and up to AP Calculus, which is when I actually started to get interested in math. Until then, I thought that math wasn't, super valuable. Like, it's not going to help me cure a disease. What am I doing? Spending all this time out with algebra, and I was very, very wrong. Because a lot of times when you're taking these classes as a middle and a high schooler, you don't realize the full impact and the significance of the subjects you're learning. And if you tuned into our first speaker, Dr. Con Henry, he was talking about how the Pythagorean theorem, which is something that everyone learns in grade school, is actually used to explain many of the mysteries and some super intricate concepts in the universe. And so I think especially with this event, I got to see how, skills that you think are very simple and like mundane can actually be super applicable in the world and are driving a lot of the innovations in science and technology. And the last thing that I really hope that you gain is, exposure in subjects in STEM that you're not super comfortable with. For me, I was very fixed on biology. I want to be like a computational biologist. And after listening to all of those physics talks that were just absolutely amazing, and all those math talks as well, those blew me away. And computer science. Basically every subject that I was like, this is an okay subject. After those talks, I was like, this is amazing. I didn't like black holes colliding at the edge of the universe. That's amazing. So, I'm getting a little philosophical, but I really enjoyed and I really enjoyed the privilege and the opportunity to hear from these amazing professionals, people who have dedicated their life's work and like thousands and thousands of hours to studying STEM. And they came to speak with us for like no charge, for nothing. They just came to inspire us. So yeah, I really like to thank them. They're probably not watching this because, but they were really amazing. And I hope that you did also, get a better grasp in some of the concepts that we were teaching, maybe gain insight or inspiration to pursue something you weren't super familiar with or you didn't really care for. before this convention. And so that's my little spiel. And now I'll announce the competition winners, because this is called the award ceremony. It won't take very long because we're just going down a list. And we're not going to go yeah. So for the physics competition today, I'd like to congratulate Steph G, Matthew G, Eris Sedorje, who's actually joining us from Frankfurt, Imtiaz Srinjoy C. These are just the names that they enrolled in the Kahoot with. So Al Kafi, Claire Yang, Raha Kumaresan, Ishan Jaluri. So sorry if I mispronounced anything. This is our first encounter. And then for math, congratulations to Matthew G, Mahir Desai, Dylan Shu, Jiakang Chen, Michael from SWHS, Claire Yang, Elliot Chen, Matthew Sulistij, so sorry again, Imtiaz also. Oh, congrats on everyone who won both of those competitions. I saw a few overlaps. For chemistry, we have 2 more to go. Chemistry, we have Steph G again, Anna Pereira, Alma Sedorje, Srinjoy again, Nikita Valajev, Claire Yang, Julia Sun, Janine Lay, and Imtiaz for the 3rd time. Okay. And for biology, last competition, Tamara Gruslova, Srinjoy C, Imtiaz, Michelle Serbin, Ria Alurkar, Montana L, Joshua Sujo, April Z, and Harriet Chen. All right, I'm done with all of those names. So big congratulations if you won. Our competitions, as I said before, they were written by high schoolers, but they were still pretty hard. So, kudos to you for joining a competition on your Saturday and Sunday. Okay, those are, and just because we're going on this theme of thank yous, a special thank you to everyone who organized the events. These are also overlapping names. Faith Han, especially, Devon Shaw, especially, Aryan Mathur, Arun Yadavali, Catherine Liu, Sophie Takmapoulis, especially. Those were all of the names I also mentioned for the people who stayed like almost 22 hours. Yana Samoilova, Brianna Doe, Yulia Anashkina, Natasha Lee, Rahul Sundar, Catherine Zhou, and Catherine Liu. There's 2 Catherine Lius. Priyanka Kalidindi, and our competition writers. These are the last thanks. Catherine Liu, again, Harshdeep, Kailash Ranganathan, and Christian Kim. The very last thank you, I promise, is to our sponsors. They are the only reason that we were able to actually garner prizes for all of you competition winners. So, a special thank you to Carry the Vision. We actually have Ann Fisher from Carry the Vision with us today. And also to Next Step, which is a service that helps with college admissions. So if you're interested, I posted several times in the announcements channel, and I'll repost this night today. Yeah. So thank you guys. Thank you for everyone who supported STEM World, who came and listened to all of our speaker talks. And I am finally done with my spiel. So now we're going to meditate. And afterwards, again, we're just going to hang out. And if you want to talk about anything, if you have any suggestions to improve STEM World, that's the time to say it. All right. And I will hand over the floor to Anne.
Thank you, Diana. Wow, it sounds like it's been an incredible weekend. And the way we're going to close is with meditation, which is interesting if you know the science of that. It's